Hello. Okay, let's see how this goes. Uh, Welcome everybody to this year's CubeSat workshop. New location, but as much fun as previous years, we hope. I hope you like it. We think it's pretty nice. But as we get started, I would like to introduce a special guest we have to welcome you all to Cal Poly. The Dean of the College of Engineering, Jing Mar, wants to say a few words, so I'm gonna let him have the mic.
Thank you, Jordy. Good morning. I'm Dr. Jim Maher, the Interim Dean of the College of Engineering here at Cal Poly, and I'd like to welcome all of you to the 14th Annual CubeSat Developers Workshop. The workshop has been so successful that we had to move it to this lush new venue. I think it's really appropriate that we're here at the Performing Arts Center because CubeSat represents the art of engineering at its most creative, and you are the conductors of their performance. I've kept my eyes on the Cal Poly CubeSat team, known as PolySat, since their inception 15 years ago. I should say that I've kept my eyes on them and close eyes on my test equipment. Around the year 2000, PolySat members started showing up in my vibrations lab to test their deployment system. When it came time for me to teach vibrations on Thursday, I seemed to always be missing accelerometers and cables. Someone, me, told them about the importance of calibration and maintaining standard test procedures and control over the test equipments. But I forgot to tell them about my laboratory teaching needs. Our student clubs here at Cal Poly go by two mottos: learn by doing, which you'll hear a lot, and it is easier to ask forgiveness than to get permission. The program has grown from CP1 and CP2, which unfortunately had rocket failures, to a program now that has 5 satellites that are on various stages of development all at the same time. It's really quite impressive. PolySat here is celebrating 10 years since its first successful deployment. As I look at the registration and see all the companies and universities and students represented, I'm so impressed with how far this program has come. Indeed, the sky is not the limit. This workshop has been organized by students, which I would like to thank, and it is the largest conference in the world dedicated solely to CubeSats. We expect an attendance of 500 people, and there's over 20 countries that are represented here. I hope you find your time here enjoyable and productive, and I wish you all the best. If there's anything we Mustangs can do to make it more useful, let us know. Welcome to Cal Poly. Fly high, have fun.
Yeah, Jim was great when we had emergency testing needs, and sometimes we even asked. So welcome everybody. Let's get started. We have a few informational slides just to get everybody a little familiar with the venue. I know that I need to. So let me see what we have. And this should work. No, it doesn't. Can you guys forward the slides for me backstage? Thank you. So if you see somebody with a blue lanyard, that's one of our students or staff members. So if you need any help, find the blue lanyards and we should be able to direct you to whatever it is that you need. So that's something to keep in mind. They're very strict about food and drinks except water in the auditorium. So please don't bring them in. If you want to watch the presentations and have some food, there is the pavilion room, which is downstairs. If you exit left and then go downstairs, there's a room set up with a video stream and tables, and you can sit there and eat and chat and be loud and work on everything. There is Wi-Fi that should be up and running. If you have any problems with it, let us know, because we're We had some problems yesterday, but I think it's working fine today. So just let us know if there's any issues. And then to remind everybody, we have the first floor as we get out of the hall is some booths. The second story is more booths, and then there's a third story with all the posters are. So I encourage you to go up there. The views are pretty spectacular, so it's worth the trek up. If you don't want to go up the stairs, there's an elevator, but make it to the third floor and see all the posters. Next. Dinner tonight at Slow Brew. I think there are maps on your package. From 6 to 10. It's a new venue in town. We're testing them out, but we have great expectations. The food is supposed to be really good. The beer's great. So join us, and it should be a fun time. Next. We have an app. So go download the app for the conference, and you'll have all the information you need. There is a QR code, but you can also go to the App Store and just look for CubeSat Developers Workshop, and it should come up. So that works. One more, I think there is one more. Yeah, that's the just an idea of what the map looks like. That's the main lobby and the posters. That's the second story. That's the third story with the posters all the way up. Oh no, that's the second story. And then the third story is posters. We just changed that last night. We were running out of space. There is a number of meeting rooms in this building that you can have access to. Just let us know, and we'll put you on the schedule, and you can have meetings and talk with people and all that. They're all kind of backstage, which is pretty. Don't go in there; you'll get lost. I still do. So it's a bit of a maze back there. But the students know where all the rooms are, and there is a sign-up sheet, and you can sign and figure out what's going on. I think that's it for announcements. And then the bathrooms are outside the doors on the bottom floor, and then there's another set of bathrooms on the second story, so you should be able to find those. Next, that's it? Perfect. Okay, so we had to move because we were growing so much. As Jim said, we're expecting close to 500 people this week, so it'll be really good. So I'm going to kind of ask you where you come from, like we do every year, just to see who we have here. So the first question is, how many people are here for the first time? Wow, so you have no memory of where we were last time. So all this talk about how wonderful it is to be here makes no sense to you. I was just talking to myself. How many people have been here for more than 1 year? More than 5? More than 10? Wow. How many people have been here every time? Yeah, there's Dave and Kyle and Bob, me. But there's a few of us that done that on all of them. Next question. How many people from academia? Carrie, you count. Thank you. Industry? And who's here from the government to help? Awesome. One more question. How many international people from outside the United States? Oh, wow. So we have everything. We have everything. We have a ton of new people. So that's really exciting. So we have a really, really good week plan. And as you know, the theme this year is global phenomena. And one of the things that we've been trying to accomplish for a couple of years is to bring somebody from China to find out what their CubeSat programs look like. And last year, a Chinese new launch vehicle launched the first 12U CubeSat, somewhat to our surprise. I'm trying to find the name, and you have to forgive my Chinese pronunciation. Wenchel, if you want to come help me, that's work. It's the star of Aojiang, and it was the first 12U CubeSat launched ever. So we kind of decided that was pretty impressive, and we really would like to know what's going on. So we found that the Shaanxi Engineering Lab for Microsatellites was the team that built that CubeSat. So we invited Dr. Yu Xiangzhou and that's probably wrong, to present and tell us about what they've been doing. He's the vice director of the Jiangxi Engineering Laboratory for microsats. And they have a number of missions besides the 12U. They're working on a 2U. They've worked on QB50 programs and all that. But we asked him to tell us about their programs and a little bit of what other things are going on around the country so we can learn about what's happening in the CubeSat world in China. So without further ado, Dr. Yu, he's in there somewhere. Come out and join us. Thank you so much.
Good morning, everyone. I'm very interested to be here. This is my first time to America, also first time to this place. Now, I will give a very short, maybe short, brief introduction of the status of university nanosatellites in China. My name is Yu Xiaozhou. Maybe pronunciation is different, but you know, Chinese is very difficult to pronounce. You can see 4 pictures. These pictures are taken in my lab. Today's contents, there are 3 aspects. First is nanosatellite research in China. Second is CubeSats developed in my university. And the third is flight result and the lessons learned of my team. This is a map of China. My university is in the heart of the country. And except my university, another university, Harbin Institute of Technology, also built CubeSats. First, we will introduce several universities that have launched CubeSat. And the third university that have launched CubeSat. Except CubeSats, there are many nanosatellites that have been launched. First, oh, there's something wrong. 3 universities that have launched CubeSat, and there are still 3 universities that will launch CubeSat. There are maybe something wrong with this sequencer. It's the first time to be used here. Oh. No response. Something wrong. I don't know why. The remote has no function.
The remote is not working?
No working.
No, just ask for the next slide and we'll switch it in there.
Okay.
Let me try it and then try to fix it. But it may be out of battery. But if you say next slide, we'll just switch.
Okay. Just go back to the Chinese map.
Go back one.
Okay. In Chinese words, some good things very had bad beginning. Everything is first for me and for the remoter here. Can you help me to go previous to Chinese map? Maybe the computer has also problem. I want to know. Go to the 4th slide. Can you help me to the Chinese map? Okay. Finally, we go to the right map. We can see how to. Oh. Okay, maybe we go to from this page. I go to the backstage, and I think everything's okay. Okay, finally, all the university come to us. The top is Harbin Institute of Technology, and except that, there are several universities do the research of nanosatellites, but only 3 have launched CubeSats. It's Northwestern Polytechnic Technical University, Harbin Institute of Technology, and Nanjing Institute University of Science and Technology. Except these 3 universities, there are additional 3 universities will launch CubeSats. They are Wuhan University, and Beihang University, and the other one is National Defense University of Science and Technology. The other 3 universities.
Let's try this again.
Ah, okay. Okay. And except these 3 universities, only 3 universities just send nanosatellites. And we will just briefly introduce the universities that had launched CubeSats and nanosatellites. Okay. Slow. Okay, it does work. Good. HIT. We see HIT, the name is Harbin Institute of Technology. And this team do a lot of big satellites. It's over hundreds. Except that they have launched 2 nanosatellites. One is Lilac Satellite 2. I don't know the meaning of this name. It's not Chinese name, maybe not English name. I don't know the meaning. And that nanosatellite is here. We can see it's a rectangle nanosatellite. It's about 12 kilograms. It's not CubeSat. And the second one is the LACSat 1. And it's one of the QB50. So it's a 2-unit CubeSat. The main purpose of this CubeSat is doing the atmosphere research. And this team also do some transceiver and the CMOS camera. Another university launched CubeSat is Nanjing University of Science and Technology. And this university made several CubeSats in the 3 years. They launched first is NGU ST1 and NGU ST2, Yang 1, Canton 1, only in 3 years. The main function is just the AIS receiving Earth observation and aerospace education. There are 4 pictures of HIT, and the other 4 pictures of NGUST. We can see 2 CubeSats of NGUST. The students is doing the work, and the team also just dozens of students. Ah, good, it works also. And in this page, I will give a very short introduction about the university that do the nanosatellites. First is Tsinghua University. This university do the first nanosatellite in university, and that is nanosatellite 1. And the second is nanosatellite 2. Both of the nanosatellites is over 10 kilograms. It's bigger one. We can see the nanosatellite 2. It's about 30 centimeters. The mission is used for cameras and MEMS technology. These teams has very good at MEMS technology. They do the star trackers and some very small sensors. So they use the platform to test their product. And another is Zhejiang University. Zhejiang University do the nanosatellites. It's just like a CubeSat, but a bit bigger. It's not a standard 1U CubeSat. And first launch is ZDPS-1. Then after that, they send 2 nanosatellites. That is ZDPS-1A. This project has 2 nanosatellites. It's just around 2 kilograms. It's just also small, but not CubeSat at all. The mission is just S-band communication. ZGU most of students of AGU and teachers are doing the communication device development. So they just use this nanosatellite for the test of their sensors and for their devices. Except the nanosatellite use this communication device, communication subsystems. They also, a lot of big satellites in China use this communication system. I remember there are over 10 big satellites has used this. Work. Okay, just to my university, it works. The CubeSat development in NPU and in China, it's very recent years. For me, my first time contacted the concept of CubeSat is about 2010. And then, after that year, I hold a CubeSat structure design competition in my university. Why we do the competition of structure? Because for myself and for a lot of teams, structure is very easy. So the students, it's easy to do it. We can see animation. This animation is not a very good one, but at that time, for the students, it's a big success. And after 1 year, I, with my colleagues, hold the Aoxiang Cup CubeSat design competition in my province. And at that time, in my memory, there are maybe 300 or more students joining this competition. It's a success indeed. This is the final of that competition, and the students get their reward. Okay, after that, we just cooperation, had cooperation with a lot of institute and with IIF and with Chinese Astronautics Federation and other together to hold a national level flight vehicle competition. This competition is very successful indeed. We can see the teams that join the competition. This is only the final review, and except that, a lot of students and universities, over 30 universities around China join this competition. But I have to say, not all the competition is for CubeSat, and a lot of other competitions, such as a spacecraft and a big satellite and a lot of things together. But CubeSat is also a very important part of this competition. Besides the competition, there are many presentations in China about the CubeSats. And each year, there are over 10 big-level CubeSat presentations in different countries, in different universities will be given by me, by my colleagues, and a lot of scholars in China do the CubeSat research. And let more students know about it. Brief introduction of my university. This is the picture of my university. It's near the hill. It's very similar to Capoli. And the name is also similar. We all have Polytechnic. And it's my team. And we can see the left one, bottom left one, is we mounted the 12-unit CubeSat onto the launch vehicle. And our research our launcher team in the launch site, it's the second one. And we can see the ground station of my team is a very big dome on the top of the building of my college. And we delivered our 2-unit CubeSat in the Netherlands. This CubeSat is one of the CubeSats of QB50. Another very important information, please remember, the center of the Chinese is our university, and another is very important. Good place, Bell Tower. Can you help me? Okay, city wall. The first lady of Obama's wife just ride a bicycle around this city wall. So I mean, this is very important. Maybe future, some of you go to my university and just ride a bicycle around this city wall. Can you help me again? It's a Dayan Tower. It's a very famous place. Maybe over 1,000 years. It's very, very old. And I think most of the audience here know this. It's the buried army. It's very famous. Someone told me it's 8 miracles in the world. But I think it's very interesting. I have been there for over 10 times. So my university do 3 aspects. Main aspects is aeronautics, astronautics, and marine, just a pass. Spacecraft research in my team. My team is about 28 staffs, and average is around 34. So for myself, I'm one of the oldest person in my team. And we have participated in a lot of big projects in Chinese. Before CubeSat, our team just do the research of very big satellites and spacecraft and other things, such as Shenzhou spacecraft, Beidou navigation satellite, Chang'e lunar orbiter, Fengyun 2, Fengyun 3 satellite, and a lot of satellites. So before CubeSat, we do that kind of things. And we have a lot of experiment conditions, such as ground station, clean room, and different kinds of tables, and vacuum chambers, and a lot of things. All the tests of the CubeSat is just tested in my lab, not other places. We have all the facilities to do the research of CubeSats. I will give a main timeline. First, it's 2010. It's the first time I know the concept of CubeSat. And the project came from a graduate project. At that time, the students want to do this, so I and the other colleagues do these things. And then come to 2011. Our CubeSat joined the QB50 project. And at that time, my hair is black. And time goes. Time goes, but it doesn't go. Okay, and at 2013, our 12-unit CubeSat was selected as one of the payload of Changzheng launcher, Changzheng 7 launcher. This launcher is the first time launched. And several days before, the Chinese cargo ship Tianzhou 1 is used this launcher. And my CubeSat is the maybe first payload, first one of the payload of that launcher. Time go. Go. Okay, to the time. We can see. No sound. I go to that launch site.
电发射场点火升空，约603秒后，载荷组合体与火箭成功分离，进入近地点200千米、远地点394千米的椭圆轨道。长征7号首次飞行圆满成功。长征7号运载火箭为2级检。
And at that time, in fact, it's a very big challenge to my team and the 12-unit CubeSat. Why? Because this is a new launcher. And the launcher team make it tricky and give us a very, very harsh experiment condition. And after launch, they told us, they gave us very large. But before launch, they told me, you must obey. This is the deadline. So, upset. After that, in 2017, we launched the Xingyun 1. In fact, it's a backup of QB50 project. So I will combine together with QB50, that CubeSat together to make a brief introduction. Okay. Okay. Ocean 1 was launched this month. And now it is in the International Space Station. And the first 12-unit CubeSat, the main mission of the CubeSat is verification of 12-unit CubeSat platform. And besides that, we have made some very interesting payloads, such as polarized sunlight navigation and other things we want to test. And another important is education, not only for students, but for the young scholars also. Wait. Okay. Help me. Okay. First, subsystems of 12-unit CubeSat is structure. It's a 12-unit structure. It's power system, and OBC, ADCS, and we can see all the pictures inside all the pictures. It's subsystem of my team's CubeSat. All the systems are made by our students and young scholars. Communication system, and 3 payloads. First is polarized sunlight sensor, and second is very small magnetometer, and the third is FPGA-based onboard computer. Help me. Okay, wait. In the slide, you can find the dimension of the structure. It's around 1.5 kilogram. And the dimension of the structure, and the material of the structure. It's in the 12-unit CubeSat, there are 2 onboard computers. First is the main onboard computer. This is the main onboard computer by the students. It's a very interesting structure. It's a 1 monitor CPU and a host processor. The host processor is ARM-based. Okay, there are 2 host ARMs. And use a voting architecture to get the final write command. And a lot of interfaces, some as CAN, SPI, I2C, and a lot of things. Attitude determination and the control system. The active sensor of the system is just a sun sensor, magnetometer. And the actuators is 3-axis reaction wheel and a magnetometer by students. And it's a new GPS BD receiver to get the information of the orbit. Oh. Oh. It's an animation. Can you help me to that animation? Okay. is very good to test on the ground. Many times you do not need to replace wires or other things you can test, but this pod, we test, I think, maybe nearly 100 times just to, on the test table to test it. This structure is sometimes it's vulnerable, but finally we solve this problem. And developed subsystems by my team is such as a pod, onboard computer, structure, GPS, BD, magnet talker, electrical power system, reaction wheel, and wireless sensor is also building by my students. All the subsystems not only used in our CubeSat, but also another 6U CubeSat has used these subsystems. This is another 6U CubeSat developed by a company in China. They used our subsystem. And except that, recently, several CubeSats have launched a contract with my university, and they will use my subsystems. Ocean-1. In fact, why is Ocean-1? Because this is indeed the first CubeSat project in my team. This is the animation of this 2-unit CubeSat. You can see. It's a simple one comparing with the 12-unit CubeSat. And this project is funded by the EU Frame 7, and very long before, and over 23 countries and regions take part in this project. The project is led by Van Kam Institute, and except that, other universities and institutes join this project. The main mission of the project is atmosphere research. And our university is only one Asia coordinator, and the first initiator members, the initiator members, one of the initiator members. Xingyun-1 and Ocean-1. Xingyun-1 is used the backup satellite of Ocean-1. It's similar. Most of the systems are the same. The payload is different. One is QB50 provided to us. The other is another communication bar. And the power systems are similar. Can you make it go to? Okay. ADCS is the same. And the COM board is same. Okay. Structure is similar. And the pod, in Xingyun-1, we also tested our 2-unit EMU pod. It proved the pod is very successful. Flat result and the lessons learned. Finally, all the missions of Star of Ocean has accomplished. And we get the altitude data and get the science data and other things. My team is doing the research of the science data now and get some preliminary result. The data of Xingyun has been received, but now the Oxiang-1 is still in International Space Station, so no result. We are just waiting the final result. It doesn't work. Okay. The lessons learned for our team, I think, is 5 aspects. First is EMC tests. For us, this confused us for a very long time. Only the GPS interfere with the other systems, to us, it's a very big headache. So we get a lot of energy to solve this problem. And the ground experiments, for our university, we have a lot of facilities. So we do a lot of ground experiments. This is very important. If you want to have a very high performance system, you must do the ground experiment as many as possible. And third is chip selected. We get a lot of documents and read a lot of them. And so we select the chips. A lot of the chips has flat heritage. We use it. And the radiation for the low Earth orbit system, the radiation maybe is minor, but sometimes we should pay much attention because the radiation will make the system confused. And so we make a very complicated onboard computer to solve this problem. Finally, it proves that the onboard computer works very well. And thermal analysis, we can see in the bottom picture, the pod has a thermal system to protect it because the system of the pod of our system will stay in the vacuum for a long time. So we make a very detailed analysis. And I get some lessons from other teams. They told us they do not do a very detailed thermal analysis and get very bad results. Okay, the animation, finally. It's my team. The time is not correct. This year. In fact, only one problem is CubeSat, not so many. That's all. Thank you.
We have time for questions if you guys have a couple of questions.
computer. One is ARM-based, the other is radiation tolerant. It's FPGA-based. And the ARM-based onboard computer reboot several times. You know, ARM is very complicated and is vulnerable to radiation. And the other system, radiation-tolerant board, works very well. No radiation, no reboot at all.
There was one more question.
The budget, good question. Fortunately, all the facilities we have bought get funding from countries. I think the facilities around
back. Yeah, and actually, now that I got you all thinking about 12 U's, that there's a 12U spec coming. So watch CubeSat.org. I think the 6U is solid, and we're gonna work on the 12U for now. So we have a break. We're back here at 12:15, 12:20. So go get some coffee, and I'll see you in a little bit. Thank you. Did I say 12? I'm sorry, 10:15. I was in Central Time.
part of my talk.
I'll be speaking afternoon, yes, yes. I'm Sona Hosseini.
It's a scratcher.
Yeah, so go ahead and stand at it, or yeah, go. So just peel it off, don't be afraid.
Okay.
Yep. And just don't cover, sorry, there's one more rule. There is a receiver is actually broadcaster right there, so if you cover that, your signal's gonna go down and there's a possibility that's gonna cut out. So nice and center, nice
All right.
solid hold.
Testing, testing. There we are. Okay. I like that.
Yeah.
What about this, to move the slides? Click the
They should have
slides.
an advancer for you.
Okay, so.
Do you have the option to put the other one?
Sure,
so we can
that's
walk
what I
around?
just mentioned, yeah, the lavalier.
Okay.
So this one's kind of funny.
I'd like to welcome everyone back and thank NanoRacks for supporting the previous break. Our next speaker is Harlan Spence from the University of New Hampshire. He's going to be talking about some lessons learned.
Good morning, everyone. It's really my honor and privilege to be here today to talk to you about a science mission, a couple of science missions we've been doing with CubeSats. And as I like to think of it, they're little packages but provide big science. And so I would especially like to thank my colleagues here today, Dave Klumpar and Sonia Smith in the back, in the cheap seats, who've been involved in these missions, along with colleagues who aren't here, Byrne Blake at Aerospace Corporation, the entire Firebird and AC6 teams, a team called KISS, which I'll talk about at the very end, and Therese Moretto at the National Science Foundation, who really enabled the Firebird missions. So I'll be talking about some of the science, some of the lessons learned, and going forward. Speaking of which, there we go, going forward. So let me start with a little bit of background. The next decade really has some significant challenges in terms of funding for science missions, but also, I'd say, some interesting opportunities. And these have been very well clarified in 2012 in a document called, commissioned by the National Academy of Sciences, called the Solar and Space Physics Decadal Survey, which noted that there would be a very low cadence of flagship missions, the kind of missions that accomplish the big science that we're accustomed to. That's true in solar and space physics. It's true also in earth science, planetary science, and astrophysics. NASA budget is very much constrained. But that same decadal survey pointed out the emergence of CubeSats and small sats and recognized that the value of those is enormous in that you can do targeted scientific discovery at the same time as you're training the next generation of scientists and engineers. So today I'll talk about two of these missions that are in that category, Firebird and AC6, which are, I would say, the first ongoing example of these kind of CubeSat missions. So I'll review these missions, provide a status update, and outline some of those big science questions that we're answering with these little missions, and finally end with one important lesson learned, and that's for all of the science missions you can imagine, you need a bigger straw, and I'll explain what that means. You probably can get it. So the science we're tackling with these missions are a phenomena known as relativistic electron microbursts, and this is a phenomena associated with the Earth's radiation belts, imaged there on the right. The colored contours in this donut pattern are energetic charged particles trapped in Earth's magnetic field that extend all the way down to the atmosphere, and some of the electrons in the radiation belts hit the atmosphere and produce interesting effects. Despite it being the first discovery of the space age by James Van Allen, it still remains mysterious, particularly electron microbursts do. So they're important to understand for two reasons. The first really has to do with they're a potential major source for emptying the radiation belts. So as we fly spacecraft through the belts, we want to be able to understand the radiation effects there. And they also are important for affecting the atmosphere. They produce ozone chemistry in the atmosphere, and they potentially are giving rise to long-term changes in the upper atmosphere as well. And right now, that physics is not included. So we started studying these in the 1960s from indirect balloon X-ray measurements. Oh, here we go. Forward is not quite as brisk as I had hoped now. Could somebody backstage please advance? Thank you. There we go. They have been studied really for quite a long time by the SAMPEX mission, which was a small explorer, the first of the small explorers. But the problem is you have a single spacecraft, and when you're studying a time-varying phenomena while you're in orbit, you don't know, was that something that changed in space? Was it something that changed in time? Or was it something that changed in space and time? Could someone advance, please? Thank you. So we have this ambiguity with a single spacecraft. So it really called for a new way of approaching the problem. And on the next slide, if we could advance, thank you. We have two spacecraft missions, CubeSat missions. The first is called Firebird. focused investigation of relativistic electron bursts, intensity, range, and dynamics. It's a tortured acronym, I know. There are two 1.5U CubeSats that fly in close proximity, moving through this phenomena at low altitudes to assess the size scale, the time scale, and the energetics of this phenomena. Can I have the next slide? And the questions that are asked are, what are the size scales? Very simple questions. And what is the energy dependence? And on the first question, we do an excellent job for a short time when the spacecraft are close together, and then we do a pretty good job later on. And in terms of the energy dependence, we do an excellent job. Cube 6, this is a mission out of Aerospace Corporation. This is two half-U CubeSats that have dosimeters that are really looking for the same kind of questions. And if you could advance one more click. They're really good at the spatial scale because they use dynamic positioning of the spacecraft to probe the size scale. Next click, please. These two missions, which are very low cost, multi-point, that's key, you have to have two, at low altitudes, are highly complementary to a flagship NASA mission. I put a big dollar sign in NASA there because these are billion-dollar type missions. Actually, this was shy of that. But an enormous investment of money. For $1 million or less with these missions, you get an enormous return on investment. Next slide, please. Next click. And that last point makes that point. Click again, please. So just click through this whole slide here. One more, and then stop. Good. So the NSF sponsored these Firebird missions. And we did two versions. We had Firebird 1 and Firebird 2, and Roman numerals. And then you can see the 4 flight units, Flight Unit 1, 2, 3, and 4, from left to right. These were, it was a joint project with University of New Hampshire, Montana State University, Aerospace Corporation, Los Alamos, and eventually Stanford as well, and now Johns Hopkins University Applied Physics Lab. Could I have the next slide, please? This is an overview of the launch of Firebird 1. It was launched with an NRO special payload with a great acronym there and a great logo. Nothing is beyond our reach. And you can see reaching in at the bottom is the hand of one of our graduate students holding the payload. It has two solid-state detectors that measure relativistic electrons mounted at one end of our 1.5U CubeSat. Unfortunately, Firebird 1 didn't accomplish all of its mission because the two spacecraft didn't operate at the same time. They both operated, but one kind of took a long time to wake up, and the other one had a power system fail over time. And so even though they worked independently, they did not work together, which was a key aspect of the mission. Next slide, please. At about the time of the failure of the second of the two operating Firebird 1s, the Cube 6 was launched back in June of 2014, also into low Earth orbit, high inclination. These had 3 dosimeters per spacecraft. In each of these were never flown before. There's a picture of the payload there, about the size of a dime, the dosimeter. There were 3 different varieties, perfect amounts of clicking, thank you, one more click. And they are relatively slower sample rate than Firebird and relatively crude energy spectra, but they use differential drag to control the spacecraft in-track separation, so you can really probe the size scale beautifully. They are still in operation. They've been going for 3 years with beautiful data, and one more click, you'll see a panel appear up top that shows the 2 spacecraft measuring the precipitating electrons from the radiation belts as a function of time over there, about 4 or 5 minutes worth of data as the 2 spacecraft traverse the same region one after another. So first time that we've ever had those 2-point measurements, which are critical for the science. Can I have the next slide, please? So we learned lessons from Firebird 1, and we, for 20 cents on the dollar, we went back to NSF and we built another 2, launched them now in early 2015, again from Vandenberg, this time on a SMAP launch. If we could have a next click, please. Here's the beautiful launch view of the Atlas going up. There's the 2 Firebird, one more click. These were improved versions. We learned lessons in re-engineering and building in terms of the power system and so forth. This was designed for a few-month mission. We're now 2 years plus a few months, so it's way outlasted its expectations. Next slide, please. Again, high inclination orbit and at low altitude, a single ground station at Montana State University. Next click, please. We get a couple of passes per orbit, and if we can click through to context data. So we collect low time resolution data just to give us a sense of what the radiation belts are looking at. Produces a minimal data volume. One more click, please. Shows an example of that. This is a Mercator map of the Earth. The yellow kind of bands you see at northern and southern hemisphere are the horns of that radiation belt. If you click one more time, I'll remind you what those look like. The horns of those belts touch the atmosphere. And where they touch the atmosphere, they kind of paint this, this region with those relativistic electrons. The bright spot there over the South Atlantic is the South Atlantic anomaly. And so that's where particles hit the atmosphere as they drift around the Earth as well. Could I have the next slide, please? So the context data is interesting, but the most compelling part is the high resolution data, because that's where we see the microbursts. We need high time resolution, we need high energy resolution. We have 2 detectors. We generate a huge amount of data on board. And our ConOps is scientist in the loop. So we look at the context data, we try to figure out when and where there might be microbursts, and then we store the data on board, and then we have to painstakingly download it a little bit at a time. So we're looking for a needle in a haystack, and we only know what needles to look for that we think we know. So we know we're missing things. Next, there we go. Big lesson learned. Here's our soda straw. We're pushing watermelons through a soda straw, and we're failing horribly. We know that. We really need more data down to be able to accomplish the science at the highest rate. Next slide, please. Here's an example of the kind of science we can do. Even with these very minimal cost payloads, this is a discovery. This is a science class discovery. We've been able to, for the first time, Flight Unit 3 on top, Flight Unit 4 on the bottom, a traversal here that's lasting a few minutes, looking at relativistic electron precipitation. If you only had one and you'd pass through that, you would have no idea if it was temporal or spatial variation. The second one comes by 3 minutes later and sees exactly the same thing. Pretty much every mission before would have interpreted the top panel as temporal. It's spatial. I mean, that has a huge implication for what these things are, what causes them, and it's causing the theorists to sort of lose some hair. Next slide, please. So here's a summary of some of our big discoveries. Again, big things come in little packages. We've been able to, for the first time with Firebird and AC6, disambiguate this spatial temporal uncertainty. We have provided the first high time and energy resolution of relativistic electron microbursts and looked at, with this high time resolution, be able to look at the dispersion shape of the microbursts. All of these tell us about the source of them, what's happening out further away to produce these phenomena. And here's several publications that are just now coming out with the first science results in the last, starting in 2016 and now in 2017 as well. Next slide, please. So let me now shift gears a little bit to the soda straw problem, because for me, a lesson learned is that if we had had optical communication, we would have been able to have a 100-fold increase or more in terms of what we're able to do with this mission. So when we start looking at the data rates, the kind of data that we generate, we quickly get to very large numbers. And if we had known up front that we could have gotten those data down, we would have operated even more aggressively the instruments and data storage and so forth. So even with this small mission, as many of you know, you can generate an enormous amount of data, a few gigs per day, gigabytes per day. Next slide, please. There is an ongoing effort that David Klumpar and Emily Clements, who will be giving a presentation here shortly, are part of through the Keck Institute for Space Science, where we're looking at optical communication as an enabling technology. And as I think you'll hear maybe from Emily and others, this is a technology where the TRL is improving, and I think we're on the doorstep of really a transformation in terms of the kinds of data rates that we can get down. So if you have questions about this, please see any of us, and we can tell you more about that. So next slide, please. Let me just end with a summary and conclusion. I would say that you just click through to the last bullet there, perfect. These small missions will never replace the flagship missions, but in a balanced program, there's a real place for these small missions because the return on investment is enormous in terms of the science per dollar. And it's a very fast cadence. You can actually do experiments. You can change things in flight. It's really terrific as a scientist. They're standalone, but they're also complementary to the big ones. So when you fly it with a big mission like Van Allen probes or magnetospheric multiscale, you can really amplify the return on both missions. And that last bullet really is a plea to our funding agencies and to this community, the science community and the engineering community, to be looking at funding to support those kind of efforts that are enabling the technologies that will make these kind of transformations. I've pointed out optical laser communication. There are others as well, but I think it's important for the agencies to hear that. And final slide, please. Last slide, please. This is something I show at the end of every talk because when I first started doing this, people said, "You're crazy, you can't do any science on CubeSats, it's a waste of your time. Why are you wasting your time and money and effort, blah, blah, blah." So we just quietly went ahead and did it, and so this is a quote somebody came up with once. It's an anonymous person, but I really love it. So thank you for helping us do it. Thank you. Hello, Mr. or Mrs. MC. I guess I will take questions. Yes. Yeah, it's a great question. The question was the balance or trade-off between getting all the data down and doing onboard processing. It turns out we actually tried some onboard processing here of automatically detecting microbursts and then sorting them according to how good they were. Our algorithm wasn't terrific, I would say, in part because of how we were operating. So we tried it. It didn't work so well. We would do better next time. On this KISS workshop that I talked about, we're actually talking about constellations of spacecraft that are communicating and using the network sort of as a large supercomputer to do onboard processing for that kind of purpose. Because when you start adding up all the nodes, actually the compute power is pretty considerable. Great question.
Can you elaborate on your laser concept?
I'm probably not the best person to do that from a technical point of view, but so are you thinking on the technical side or what you could do with it from the science side or both?
What kind of data rates do you expect? How do you deal with ground stations and clouds and all the things?
Yeah, so the surprise to me is that cloudiness is not such a tremendous problem. Provided you have enough number of ground stations, you don't need a huge optical system to do this. That's the other thing that surprised me. I think Emily Clement will talk a little bit about that in a couple of talks. If not, maybe we can chat offline and bring a couple of other people in. It's sort of not my main thing, but I'm trying to get there. Other questions? Yes, please. So on the Firebird satellites, it's a very simple system. Dave, can you help me out? What was the processor on Firebird? Thank you.
Thank you, Harlan.
Please welcome Mark Murbach from NASA Ames Research Center.
I think let's pop it out. Good morning, all. It's a real pleasure to be here, and this is a beautiful venue. This is glorious. I'm very happy to be here. The title of my talk is the NanoSat Exobrake Experiment, and we'll give you the status of our current flight, which is overhead as we speak, and the subsequent experiments where we're going with this. I'm the principal instigator of a variety of very, very capable people, four of which are in the audience. So we have Ali Guarneros and Austin and John Wellis in front of me. And I thought I saw John Hines back there, who's also one of the originators of this. And thank you, John, wherever he is. I guess I control the slide, don't I? Okay. Forward. Okay. I'm going to go through this fairly quickly. It's a condensed version of a longer talk, so if you will bear with me a little bit. This will be available in the downloads. But first of all, what is an exobrake? One of our interests, part of my background is reentry physics. So the exobrake is a simple drag-modulated deorbit system based on tension elements, otherwise a cross parachute that flies in free molecular flow. And so we've been at this for a while. So you have there's a laser pointer here. Let's try to see if this works. Voila. So obviously it's a lot smaller than the ISS, as you can tell, but it gives you an idea. So we're in the flight now. We're actually I'll jump forward a little bit, where we actually take two of these elements. We are able to warp the cross parachute, and then the intention is to command and control so that we hit a target at the von Karman altitude, and you'll see this. Okay, so I put this down and I pick this up. All right. So very quickly, and just for a few minutes, I want to describe the talk is mostly about the exobrake, but I would like to describe the considerable effort that we put into the nanosatellite itself. It's based on our technology education satellite series, of which this is a TechSat 5 on the upper half. We also launch a variety of sounding rockets, so each time we are able to rapidly develop some article or subsystem involved. Also on the bottom is the evolution of our original PhoneSat series. And so what we have now is a very capable avionics set that I'll describe momentarily. So our mission objectives by this time was to try to do the first of several modulated experiments. We want to spread the risk over several flights, and then each time we basically add elements to it that we want to test in future flights. We need to understand the uncertainty of the thermosphere well enough, particularly the F10.7 variable, to see if we can have enough control authority to hit a target at the von Karman altitude of 100 kilometers. So we've done this before with what we call a fixed exobrake, and you can see TechSat 3 and 4 there. And then what we did is we started to model it with various thermosphere models, the most recent of which is the Jaquet-Bowman 2008. So we do that. Forward. There we are. Okay, very quickly, the anatomy of the satellite, and we'll have one available. In fact, I think somebody very kindly put there in front of us. And so the way that we construct it is also very interesting. I won't belabor it, but it's based on an extrusion. So we have a modular way of constructing this, and it's very efficient. But basically, the avionics section is a cartridge loader technique here, and then we have panels that we put on the side. The exobrake itself consumes the volume, the latter half of the satellite. Very quickly, the system architecture is this. We have a TechSat and what we call a PhoneSat. The PhoneSat is based on an Intel Iridium platform, and this is probably the first flight. We're so far quite impressed with it. And our avionics, you can see the different microprocessors we have on board. So our cerebellum, our primitive part of the satellite is based on the Arduino Pro Mini and the Teensy. And then we've been running the Intel Edison, which we want to use in the future to actually put our autonomous control system so that we can actually deorbit in an autonomous manner. This is what the stack looks like. Again, it's fairly easy to assemble, put together, and test, and we've had pretty good luck with it. So far, all of our flights have gone and are processed through the ISS. So learning how to do this from the first TechSat flight that we flew 5 years ago, we've improved our techniques so that we're a reflight series, but we pay very careful attention to make sure that we over-test it and that we fly on that platform. Another novelty is that we've pioneered, I think, the use of the Iridium system for our quick command and control. So we've had very good success with this with our TechSat 2, 3, and 4. And we basically are able to, part of our requirement is that we need at least one packet down per orbit and be able to uplink once per orbit. In our TechSat 4, our uplink was 25 of 25. So typically we get at least 5 packets per orbit. Each packet is 340 bytes per burst. But also one of our clever colleagues had developed a system, it's a Wi-Fi system based over here such that at 0.7 watt RF, we can get about 3 megabits per second to our ground station at Wallops. Lastly, John in the audience, we've been developing a wireless sensor module that I have in my pocket. John's reluctant to give me the new ones because I tend to take them home and I wash them in the washer. But anyway, these are quite capable, and we're in version 4 of this. So we have one on board, and then in the next couple of satellites, we'll be flying these in different configurations also. And that's basically an evolution from my first suborbital effort on the left to where we are, and a picture of my lost keychain over there. Our packets from the current satellite are as follows. Basically, the wireless sensor module, the GPS, the health data, everything was functioning. So we were on a first onboard timing sequence. So we showed that everything was working quite well. Now, what had happened since is we got aggressive on the design of our exobrake. So it popped out 30 minutes after flight. And we're in a slight metastable state that was unintentional, that we're flying with an angle of attack. If my Iridium number 1 antenna is here, we're flying in a pitched nose-down position like this. And so we analyzed to understand what was going on. This is the patch antenna pattern. We should be pointed in the flight velocity vector in this direction, which is how we've been able to very successfully get our packets up and down before. Right now we're down at about -90. Now we're slowly creeping up to -75, -80. This is the number of packets per day that we're currently receiving. This is a little bit old, but over time we're actually pitching up as we should be. Okay, and then with some of our STK simulations just shows where we are right now. And then basically at 300 kilometers is when we expect to be able to retain full functionality and start uploading our commands again. So a major effort of this, and part of our Langley team and also at Ames, we were developing these detailed aerodynamic models. We have an aerodynamic database of how this works. It's represented by this, for example. This is a free molecular flow code that we have, and we vary this at angle of attack at different altitudes. So we have this in our database. And then what kind of drag do we get? So if we look at drag versus altitude in this ordinate, then we basically we're jettisoned here at 400 kilometers, and we slowly traverse this. Then we cross the threshold of Hall effect thrusters, and finally the von Karman altitude. Then we're developing newtons per meter squared. So basically, it's an analog of an electric propulsion thruster that we now can control. We can throttle it by essentially warping the exobrake. With our current simulations, we see this, that we have an entry interface here at 7 kilometers per second. We release a rock or a return payload, and we're able to hit UTTR. This is what we're trying to eventually show in subsequent flights. Right now, we're just trying to land at 100 kilometers and watch it essentially burn up. In the future, near future, we have the TechSat 5 is the same as a 6 with our essentially additional features that we're developing in a different ops concept, and that we'll deliver this in July of this year. And this is a 2U that we also have developed, and this is interesting because it has a exobrake at about 1 kilogram per meter squared, which is a 7-day deorbit. So we plan to fly this later in the year. And then we're also approved to fly TechSat number 8, which is a linear 6U. And by this time, we put a high temperature exobrake in so that we can penetrate we'd like to survive down to about 90 kilometers and then make measurements. And all along, and I didn't mention, but the funny white thing, sorry, I didn't mean to flash my team over there, was we have an ablator at the front end, so that gradually we want to probe deeper and deeper and be able to use that. Some other renditions that we have here. And just a quick summary. So the exobrake is we try to show it to provide a fairly simple and safe, according to the space station, means of doing a deorbit for disposal or for targeting, perhaps sample return. One quick note is why the tension device, why we do that is because the normal, the drag sails, for example, at the lower altitudes they're going to buckle. The ballistic coefficient is going to change dramatically, and it's going to fly long. You'll overshoot the target. So there's a reason why we have a fixed and knowable geometry, and that's what we're testing. We're essentially testing our aerodynamic database. So this, we're currently engaged in the first full modulated experiment, the first of 3 that we have planned. Just as a quick note, this is practice is very important. When the Corona program was first initiated in the early 60s to return film canisters, it took them 13 tries before they began to be successful. So with this rapid development, we should be there by 2 or 3 flights. And then I introduced very quickly our TechSat PhoneSat bus. It's very capable. We have a unique comm capability that we'll present in full detail at the SmallSat conference. But I think we're perhaps the only group that can essentially command our satellite through email, and that's been very successful. Anyway, our system is very flexible, and because we work a lot with academia, we can very easily incorporate other experiments, subsystems, or sensors. And the development risk is, of course, spread over multiple flights, so we try to get as many flights as we can, make appropriate incremental development, and do it rapidly. So that's been successful so far. I talked about the TechSat 678. We're also looking at a couple of other platforms. We take all of our brains and we take it to a small satellite size where we can experiment with larger experiments that are of interest, and also systems with much higher data rate. We have an active suborbital program as well. And lastly, next week we actually go to the interplanetary CubeSat workshop, and then we talk about extending our technology to the surface of Mars. So that's the next question. How do we do this? How do we close the communication link? And it turns out there's ways to do that, and it results in very, very interesting science. So I'm very excited by the work. So that's all I have at the present. If you have any questions, I'm happy to entertain. So the question is, how do I model the drag coefficient? So we use this DSMC analysis code called DSMC analysis code. And so we run this in, it's a free molecular flow code. Actually, we can run this down to almost to continuum. We have another code that we're experimenting with that models this at continuum flow, so we can actually capture it all. Then, like any other aerodynamic database, we have this at all angle of attack and angle of well, pitch and yaw, and so that's in our base, and then that's how we're modeling. So we know how the drag coefficients and eventually stability coefficients change with angle of attack. Yes, sir. So that's a great question. Do we have a way to determine whether or not the exobrake is lying to us and is not in the actual shape that it is in? So the answer is yes. So part of our PhoneSat bus, it actually has 2 video systems, one looking up and one looking down. And the intention is that, or actually we're experimenting with this time, it's baselined in our next satellite to do specifically that. So we can get the images, and we have 2 means, either through Iridium or through our ISM band Wi-Fi link down to the ground to get those images. But that's exactly right. So the question is, how do we squeeze the uncertainty of our system? Yes, sir. I'm sorry, in which processor? The Intel Edison? So, so the first question is, do we plan to burn up at 100 kilometers? And so right now, I'm about to be answered. One more question. Okay. so we basically have to promise that we're going to, thou shalt burn your satellite up during entry. So we through this, our ODAR reports and everything else. So we have to deliberately do that. But we are experimenting with techniques, and in fact, flying in a blader at the front end to measure recession rates and the overall heating. As far as the Intel Edison, we took that through our thermal cycling. It's behaved pretty well so far. Again, more experience will confirm that or tell us otherwise, but we've been quite happy with that platform. Okay. Anyway, we'll be around. Our satellite part of it will be on the booth, and we're available for questions. But thank you for your very kind attention, and again, thank you to our excellent team. Thank you.
Thank you, Mark.
That's not mine, so I'll leave it there. Okay.
Yeah, that's good. Next up, I'd like to welcome Robert Beddington from the University of Singapore.
Hey, thank you. And thank you to the organisers for allowing me to come here at quite short notice. So I'm from the Centre for Quantum Technologies at the National University of Singapore. I'm in the Spooky Lab group there. And we're working on technologies to allow quantum key distribution with CubeSats. So QKD satellites got a lot of attention this year because the Chinese have launched what's really the first quantum key distribution satellite. And this is a pretty big 600 kilogram satellite with all the bells and whistles for doing lots of kinds of quantum key distribution demonstrations and experiments. We don't know a whole lot about it. There's a certain amount of secrecy around it, kind of understandably, but it's generated a lot of interest within the quantum communities in the rest of the world and amongst the big space companies who are now interested in trying to implement some of these technologies. And why are they so interested in this? Well, the vision, the dream of satellite QKD is that you can use your satellite to distribute these symmetric encryption keys between any 2 points on the Earth's surface, any 2 optical ground stations. And the thing about these symmetric encryption keys is they offer much greater security guarantees than any of the kind of public key cryptography which we use over the internet today. And this is because these symmetric keys, which you just use once, are based on completely random numbers, and we can guarantee they're random numbers through the quantum processors which produce them. And mathematicians, at least, can make the statement that these are secure forever because there's, in comparison to the public key cryptography, which could be broken by a sufficiently powerful computer, maybe a quantum computer in the future, or some alien's computer, or they're not provably secure in the same way that symmetric keys are. And this is interesting to some very security-conscious customers. They also, through QKD, offer this additional feature that you can have, that quantum physics will allow you to make a statement on the privacy of the key that's been shared. So this means that if you and the guy which you're sharing a key with are the only 2 people that have made measurements on these photons, you can detect that, and you can be assured by quantum physics that only you and your communicator are the only 2 people that know them. So you can tell, basically, if there's an eavesdropper on the line. And this is just on the line generating the key. So if there is an eavesdropper, just don't use that key and produce a new key. And the physicists get excited about this as well, because it allows these quantum entanglement tests allow them to probe their theories of quantum entanglement over long distances and quantum entanglement in varying gravitational fields. And it allows various theories to be tested. So what we need to do this with satellites, well, there's a number of different ways of arranging this. So this slide here is actually showing some of the different options. But the one which we're most interested in, and a lot of other groups, including the Chinese, are really targeting, is having the QKD photon source in space. And we're talking about using entangled photon sources because these are the more interesting, more secure ones. Having these low-loss optical links, so you're sending individual photons which are time-tagged from your satellite down to your ground station and measuring quantum states of these photons. And you use the satellite as a trusted node to manage and exchange the keys between the ground station locations. And what our group is claiming, and a number of other groups now as well, is that we think you can do this with CubeSats, and you don't necessarily need the 600 kilograms satellites like the Chinese have just launched. So at CQT, we're very much focused on creating the entangled photon sources, which is the core technology which allows this to happen. Basically making this laboratory setup space compatible and fit within a CubeSat. And we really see there's kind of 4 stages to the development from the laboratory into a working demonstration satellite. So first of all, we need to demonstrate that we can make pairs of photons in space. The next step, once we have our photon pair source created, is to work on making entangled pairs of photons, so 2 pairs which are entangled in their quantum states. Once you've mastered that, we can make high brightness, so lots of entangled photons in space, because if we're beaming these from space to ground, then most of them are going to get lost in diffraction losses and absorbed by the atmosphere. So you need to have a lot of them to make this worthwhile. And then once you've got those 3 steps mastered, then you can start adding in the optical links and the time tagging software and all the elements required to make a full QKD demonstration system. So, oops. This is supposed to be a video, and maybe someone backstage can click on it to make it play. Maybe they can't. Is anyone backstage? Well, this is a video that was working before, but it shows the source mounted on a PC104 board. You have a laser diode down there, and you have some crystals, and these are the high voltage power supplies. And it would be really pretty if this was working, but never mind. So the laser basically generates blue photons, so 405 nanometers, and these enter these crystals here. The crystals use a process called spontaneous parametric down conversion, and for a blue photon going in, every so often this is down converted into 2 red photons at 860 and 760 nanometers. And these 2 photons form your photon pairs, which are then used for your quantum communications. So in this setup, we're just producing the photons on this side, and we're detecting them on this side. So we produce them here, and then we verify that we've created 2 photons, and in later modules, we'll verify that they're entangled here. In a full QKD demonstration system, you would mount a telescope or some kind of transmitter optics onto one of the exits here, so that one of the photons would be measured on the spacecraft and the other one would be sent down to ground. But as I say, at this stage, we're just developing the source, making sure it works in space, so we're detecting both of them in space. So if you want to think of it as 2 people communicating, then there's one person there and there's another person here. So the first step, as I said, was creating pairs of photons. So this is the SPECS CS missions. These have been launched. This is what the device looks like. So we have the optics all in that black box there. So these are the crystals, the laser diodes, and the avalanche photodiode detectors. The high voltage power supplies there, which provide 100 volts or so to the detectors. Then on the back of the PCB, there's all the electronics to control it. There's a microcontroller that runs the show. And this all fits into about a third of a U. It's one PC104 board. And it allows us to work on the kinds of optical alignment techniques that we'll need for a fully entangled system. It allows us to generate the electronics. We have to play some tricks with the avalanche photodiodes, because to get them to work stably in a fluctuating temperature, you'd normally use coolers, but we don't really have the power budget for that. So we have some tricks that we play to measuring the pulse height that comes out of them, and then adjusting the bias voltage to keep them operating stably. So we've launched a few of these SPECS CS, these correlated source devices, on a balloon test, on the GOMEX-2 satellite, and on the Glacier satellite. This is an US satellite. So this last one is still in orbit right now. It's working well. We're getting some useful data down from that on the performance and how it changes over time. This GOMEX-2 was quite interesting because it never actually made it to space. It was one that exploded on the launch pad. But as you might be aware, this was one of the satellites that was actually recovered sometime later. It was found on a beach. In fact, they've got it outside at the GomSpace booth. You can see this satellite. They turned it on, and everything was still working, including our photon source. So we actually got quite a lot of publicity and papers out of this. So that's the first stage. The second stage is to make the same thing again, but with entangled photons. So we want to have these quantum spooky correlation between the photons that allows us to produce this very secure QKD. So the first step with the Spooky 1 mission, that's the low brightness entangled source. Spooky 2 is the high brightness one. So we're currently building Spooky 1. That's nearly ready to go. They'll be launching sometime next year. You can see that the source is quite a bit bigger now. It's now taking up 2U within the spacecraft, because there's extra components in there, and it's more powerful. The spacecraft is one which we're building at CQT, and it's basically using GomSpace components that we're buying in and assembling. And that should be the first entangled source on a CubeSat. The Spooky 2, the follow-up mission, a couple of years later, will demonstrate the high brightness, the kind of QKD-ready source, the one that will be bright enough to do space-to-ground QKD if only it had the optics attached to it. That's the plan. So there we go. So the final stage after the Spooky Sats is the full demonstrations of QKD. So for this, we require optical links. So those have already been mentioned this morning as something which people would like to develop for CubeSats, these laser communications. It's the same kind of thing that we're talking about for this. I think the next talk is very relevant to this. And so space to ground is one option. So I showed you in one of the first slides, we saw the CubeSat in space talking to the optical ground stations. Another thing we can do with this is inter-satellite quantum key distribution. And this is a mission study which is being led by the University of New South Wales in Canberra. And they've come up with this plan to have two 6U CubeSats mated together to form a 12U, which then deploys, performs QKD between the two satellites as they're mated, and then separate apart and drift apart. There's like a telescope in the middle here, and they can perform QKD at varying separations as the spacecraft drift apart. But we're, as I said, the Chinese launch has really generated a lot of interest in this technology. So we're really kind of growing the team at the moment. Got a lot of projects coming online. And we're here to try and seek more engineers. We'd like to recruit some mechanical, thermal engineers, particularly, electrical engineers as well, and anyone who feels they might be interested in developing these projects. We want to hear from you. The team is about 15 people at the moment. It keeps growing. There's about, I suppose, a third of us working on satellite things, and the other 2/3 working on the science payloads, but there's a fair amount of overlap and crossover between them. The kind of projects we've got coming up, so the spooky sats which we're building right now, there's work to be done on those. Satellites with optical links, like we've been talking about, and also QKD with other platforms. We have people approaching us wanting QKD with drones, ships, airships, all these sorts of things. Of course, you would have to move to Singapore, but Singapore is a very clean and prosperous place. It's one of the 4 Asian tiger economies. It's a nation state within a city on an island. So it's fairly high density living, but they call it a city in a garden. It's a very green place, and English is the major language, and a lot of the expats enjoy taking the weekends off, going to Bali and Thailand and all the local places, which are also really nice tourist destinations. So if you want to find out more about that, I encourage you to look in your goodie bags. There's an advert there from CQT which tells us more about what we do and the engineering position. And yes, with that, I'll take any questions. Thank you. Yes.
Do you know how you're going to tackle the problem of getting really bright source?
Yes, the question is, how are we going to make a really bright source? So one of the key problems with making a really bright source is not making it bright, it's in detecting the photons. Because if you just turn up the power on your laser, you'll get a lot more photons coming out. But the problem is that you need to be able to detect all of these photons individually and measure their polarization to be able to correlate what you have on the spacecraft with what you have on the ground. So that's really the limit at the moment. And the detectors we're using are not cooled detectors because at this stage we don't think we have the capacity for the power and the thermal issues that come with cooled detectors. So we're working on actively quenched APD systems. At the moment, our APDs are passively quenched, and this slows the rate at which you can count the photons. So at the moment, we're limited to, I think, about 500,000 counts per second or something. With the active quench systems that we're developing, we think we can get, well, we can get up to about 2 million counts per second, maybe a bit more. The problem is trying to get this to work with our stability compensation schemes, so this scheme for measuring adjusting the bias voltage to compensate for the temperature drifts. But we're getting close to getting that, but that's the bottleneck, I think. Any other questions? Okay, no time. Thank you.
Thank you, Robert. Please welcome Emily Clements from MIT.
Hi, I'm Emily Clements. I'm a PhD student at MIT. I work with Professor Carrie Cahoy. I'd also like to thank the whole NODE team. So I'll be talking about integration and testing of the Nanosatellite Optical Downlink Experiment, or NODE. So I'll kick things off with a question. What if your small satellite could downlink 100 gigabits a day? 100 gigabits is a huge amount of data. That's taking a photo every second for an entire day, or hours of GoPro data, or 100 hyperspectral image cubes. And these hyperspectral image photos are just, or image cubes are from a UAV, but I think the next couple talks you'll be hearing about doing hyperspectral imaging from CubeSats. So this is a real, possibility. And so really, what could essentially unlimited data downlink enable? So there's a huge push right now across the CubeSat industry to improve the data rates that CubeSats can manage. So right now, under current UHF and S-band systems, it's really tough to get even beyond a gigabit or 10 gigabits of data down in a given day. And this is really because of resource constraints. So in order to increase data rates, you need large ground stations, or more power, or more spectrum, or all of the above. And just to give you a sense of what I mean by large, so I've got a couple of, so I'm showing a couple of antennas here. So on the left is a UHF antenna at Wallops, that's 18 meters. On the right is an S-band antenna, and that's 11 meters. So these are really big, and so if you want to have a lot of these, it's pretty tough to build your own. So there are people working on this. There's a lot of cool work being done in both X-band and Ka-band, so just wanted to give a shout out to them. But at MIT, we're taking a bit different of an approach. We're looking at laser communications, or laser comm. So the advantage of laser comm is that it's more power efficient for a given swap, a given size, weight, and power, just because of how the link budget works out. And additionally, there aren't any spectrum constraints. So while RF is constrained in how much bandwidth you can use, there aren't the same regulations for laser comm. So it makes it much easier to scale to very high data rates. But in order to get to gigabits per second, a lot of technology development is still required. And before I dive into all of the MIT work, I just wanted to mention there's a lot of related work in this area. MIT is not the only organization working on this. The Aerospace Corporation has the OCSD mission. There's University of Florida, BridgeSat, DLR, lots of organizations. There's also a lot of related work doing compact laser comm for UAVs at Google and Facebook, and that would also potentially be very transferable to small satellites. So really, this is a great time to be in this industry. There's so much research going on. So here is the roadmap that we are considering at MIT. So today I'm mostly going to be talking about Node. This is the upper left, so that's our current downlink effort. So Node, we're trying to get to about 100 megabits per second. The goal here is not that this is the end goal for data rate, but so much as proving out all of the technologies that will enable us to go to hundreds of megabits per second, or maybe even beyond a gigabit per second. So in Node, we're demonstrating fine pointing capability. We're flying a lot of COTS parts, which lets us take high data rate commercial telecom parts and get those data rates in space. We're also demonstrating a low-cost ground station. So you'll see a bunch about our amateur telescope ground station. And once we've proved out these things, then there are several generations beyond. So after Node, I think we can get to about 300 megabits per second. With this, we'd have faster electronics, we would have a high bandwidth receiver. We'd also work on extending out our ground network. I know earlier there was a question about clouds, and one of the keys to dealing with clouds for laser comm is being able to have a lot of cheap ground stations distributed all over the globe, so that if it's cloudy in one place, you can still downlink a little bit later in your orbit. So that really increases access time. There's also another project going on at MIT called FLARE. I won't talk a whole lot about it in this talk, but FLARE is a cross-link demonstration. It's demonstrating 20 megabits per second, and there's really sort of a parallel roadmap for doing laser comm cross-links. But we're really leveraging a lot from the parallel development that's going on for FLARE, for example, to do pointing control. And then eventually we're hoping to reach a future generation where we could take what we've learned from the current work and build out more advanced architectures like doing wavelength division multiplexing, for example. So now I'll go over an overview of the Node space terminal. So Node, again, is a low-cost payload. So here's an image on the right. So Node is just a payload. It's being hosted by a commercial CubeSat vendor. And so it's about a U total. It's about 11 centimeters long. It's about 9.6 by 9.6 wide and high. And it consumes about 15 watts. That gives you a sense of the swap. And as I mentioned, we have a big push to use COTS parts in the system, like commercially available telecom parts, but also things like our lens assembly. We're using a fast steering mirror to do fine pointing. We're also using a commercially available erbium-doped fiber amplifier. So really, there are a lot of COTS parts in this system. We're aiming to do between 10 and 100 megabits per second, where at the 10 end, we're using a very low-cost amateur telescope ground station. Up at the 100 megabits per second, we're actually cooperating with JPL's Octal facility, which is a 1-meter telescope. So I'll talk more about those on the next slide. And then just to talk through this block diagram on the bottom. So in order to achieve the really exquisite pointing control that you need for a system like this, our beam is 1.3 milliradians half power beam width. You need to have pointing knowledge, right? And so we are actually using a beacon on the ground. So the beacon comes in through this aperture and hits the beacon receiver. So that's just a little CMOS array of pixels. And then we have a COTS collimator that has both our actual data signal and a calibration source that's at, I think, 635 nanometers. So those bounce off of our fast steering mirror and then hit a dichroic. The signal goes out down to the ground, and the calibration source goes into the beacon receiver. So we can see the beacon spot, and we can see the calibration source. And if those start to wander, then we can see that we're starting to get misaligned. And so having this design really helps us sort of characterize what's happening on board our CubeSat LaserCom payload. Are things shifting from thermoelastic misalignments or what? So it's good as sort of an experimental setup. If you could advance to the next slide. I don't think the clicker worked. Okay, thanks. So as I mentioned, we're using two types of ground stations. So we're building an amateur telescope ground station. That's this 30 centimeter telescope on the right. Here it's sitting just on the rooftop at MIT. That's the MIT Great Dome in the background. So with this, we're expecting to hit between 10 and 50 megabits per second. We're using a direct detection system. So basically, we have a COTS APD. It's about 200 microns in diameter, and we're just detecting when we receive the pulses. So we're using PPM modulation. And then also, we're using a COTS IR camera and a fast steering mirror to keep that light on that APD. So basically, as there's turbulence in the atmosphere, using that FSM keeps the spot focused onto the APD. Then we're also using a 1-meter telescope out at JPL. This is the Octal telescope. So that'll let us hit our higher data rates. So with Octal, we're basically using the Node electronics, but the Octal optics. And also, we're able to use the Octal beacon, so that's what's giving us the pointing knowledge on the space terminal. So now I'll go into basically the Node INT. That's what this talk is really about. So on Node, we're doing a combination of component level, engineering model, and flight model testing. So a lot of this talk is really about the component model testing. So we've been doing a lot of functional testing, so testing board acceptance and starting to integrate the system. We've also been doing radiation testing. So a big part of flying COTS components, COTS telecom parts, is will these actually work in space? So we've been doing radiation testing. We've also been doing thermal testing. That's still underway. So we've tested the FSM in an oven, and we're also going to be characterizing fiber Bragg grading and the seed laser to just check for any wavelength misalignments during temperature shifts. And then another big question for flying COTS parts is, will it work in vacuum? So we're flying a COTS erbium-doped fiber amplifier. We're using the most compact one we could find, and that particular one from that company is not vacuum rated, so you'll see some vacuum results in a second. And then we're also getting into now our engineering model, so we're working on integrating that over the next few weeks and testing it in June, doing both vibe and thermal testing, and then same with the flight unit over the summer. So now I'll go into some of our testing. Can you hit the next slide, please? Thank you. You can go ahead and just play the video. So one of the big pushes for functional testing is proving out our pointing control system. So what you see here is, this is actually from the FLAIR system, but we're using the same closed loop feedback control on node. So basically this is a test on an optical bench, and you could see earlier the spot was basically wandering around. That was simulating on-orbit disturbances, and then turning on the control algorithm, the fast steering mirror just locks it on to dead center in that target. So basically we're expecting to get about 10 arc seconds, which is about 50 microradians of pointing control. That is much, much narrower than our beam. Our beam is 1.3 milliradians, so the goal here is basically design a very conservative system and prove out being able to point that finely, and then for future generations have a narrower beam. Thank you. So I mentioned we're doing TVAC testing. So we put our new photon 200 milliwatt erbium-doped fiber amplifier, or EDFA, in vacuum and tested it during some worst case mechanical testing. So basically we put it in the hot case, so that's about 30 degrees C, and we simulated multiple downlink passes, where each pass we ran it for 15 minutes, whereas a real pass would be maybe 10 minutes, including some warm-up time, so that's a conservative test. And basically everything went very, very smoothly. We didn't see any kind of power output drop. There's no issue with thermal conductivity inside of this EDFA. So that was extremely encouraging, that we're taking something that's really designed for Earth use and is working just fine in vacuum. We're going to continue doing some additional testing and let it run for a much longer duration, but so far we're very encouraged by these results. Next slide. Thank you. So we've also been doing radiation testing of this EDFA. So again, this particular EDFA is not rated for space, but we've been doing some radiation testing. So we tested it to 1 and 3 kRad. To give some perspective, 1 year in an ISS orbit would be about half a kRad. So this is looking at 2 to 6 times what we would actually expect to see on orbit. This was also an extremely aggressive test. We tested at 5 kRads per minute, so that's a huge amount of radiation in a very short amount of time. And this was also a passive test, so basically we put the EDFA into the chamber and then hit it with this radiation and then measured the power output afterwards and compared the before and after. So our results after simulating approximately 2 years of ISS orbit, so about 1 kRad, completely nominal operation, which is great. After 3 kRads, immediately after testing, we actually saw no power output from the EDFA. So that was pretty interesting. But we waited about 24 hours, and then it came back 100%. So it seems like there was some kind of annealing. We're still kind of working to figure that out. But that basically indicates that, at least for that level of radiation, that it might heal itself in space. So we're planning, our next step is to do active radiation testing. So basically, we would put the EDFA into this chamber and then do testing at a slower dose rate and monitor the power output as it's being dosed with radiation. And if we start to see the power drop, then we would end the test, but that would give us more diagnoses of what's going on. We've also been doing over-the-air testing. So basically, we took our flat-sat transmitter, we took a fiber-coupled collimator and mounted that on a tripod. So here's our flat-sat transmitter electronics. Here's our collimator sitting on a tripod, And then our 30-centimeter receiver is sitting in the back. And this dashed line is just for illustrative purposes. That's not the real laser beam. Our laser is at 1550 nanometers, so that wouldn't show up in a photo like this. So here we were using mostly test equipment for our receiver electronics. We used a Pentec for data acquisition, and a Thorlabs APD instead of our Flight Voxtel APD. But still, it gave us a good sense of how things are working. And so we can see ppm symbols here. So basically, the x-axis here is sample rate. I guess the units are kind of cut off. But what you're seeing is each spike is one of the ppm symbols. So we're sending a few symbols in a row. I guess these look like 15 symbols. And then here is a 15 followed by a 0. So it's separated by the guard time. So basically, we're able to check that, yes, we're sending ppm bits and receiving them. And so everything is working well. So that's pretty cool. And so next steps, we're going to be folding in our flight demonstration receiver electronics and repeating this test. I'm sorry. Thank you. Just to wrap up, this is a really exciting time to be working on communications for CubeSats and especially optical communications for CubeSats. The capability of doing high data rate downlinks is really improving rapidly, but there's still a lot left to be done. On Node, we're trying to advance the technology maturity of very low-cost systems, so our niche is really trying to do low-cost telecom parts in space. We've been developing both a space terminal, trying to get low power consumption, fine pointing control, doing a lot of testing of COTS parts in space. Also, we're developing this low-cost ground terminal to enable eventually building large networks for optical comm ground stations. And next up for Node, we're building the engineering unit to be tested in June and building and testing the flight unit over the summer. And I'll take any questions. Thank you. Question? Yes.
What size and number of ground stations do you envision for an operational network?
So that's a good question. So I think around 10 to start with. To give you a sense, there's a company, BridgeSat, which is doing some cool work in building out optical comm ground stations, and I think they're around 9 or 10. So there's definitely a lot of progress being made there. According to my own analysis, I think around the 40 centimeter is a pretty good, it's kind of the sweet spot. That's small enough that atmospheric turbulence doesn't distort your beam so much that it's hard to correct for it. It's also sort of the knee in the curve of telescope cost versus diameter. And it's small enough that it's a little bit easier to slew than, say, building up a 1 meter dish. Sorry. I'll have to get back to you on that. I'm not sure about that. Sorry, I guess I should have repeated the questions. So the questions were how many ground stations, how big, and are they going to be direct drive, or are we worried about fatigue of the ground station? Thank you. Is that it for? Okay, we maybe talk after.
Further questions can be directed to Emily directly. Sorry about that. So next up, thank you, Emily. Next up, we have Caleb Adams from University of Georgia.
Hello. So, my name is Caleb. I'm from the University of Georgia. You may not have heard of us before because we're brand new to this. So, next slide, please. We were founded in 2016 by a group of undergraduates. So pretty much me and my friends were like, it can't be that hard to launch a spacecraft. And it is. It's very hard. We decided that we were going to launch a 1U, and then that kind of got out of control once we started talking to faculty, talking about, getting more serious about doing it. And so we actually won 2 grants, the USIP grant. Could we go to the previous slide, please? The 2016 USIP grant, and we're part of CSLI 8 now. So that was released in 2017. I'll be talking about our Spock mission specifically. We just went past our PDR with our Spock mission. This is our spectral ocean color satellite, the first for UGA. And we will have CDR in May. So our system is slowly coming together. Next slide, please. So it's a 3U form factor. A common thing you'll see with our mission is we want to keep it as simple as possible. We want to use methods that we know work to accomplish our scientific goals. For example, we're looking at a very, at simply the visible and then near infrared bands to accomplish our spectral ocean color mission. So we're only looking from around 432 to 866 nanometers to perform a coastal analysis and of the resources near Georgia's coast. So there's kind of a lack of data associated with the Georgia coast and even some of the Gulf states. There are long-term ecological research centers in the area that do local research with the same types of data that we might have, but it's very specialized. So what we're hoping to do is get a broad idea of that type of data. Next slide, please. Can we go to the next slide? Okay. So we're monitoring coastal wetland status. And that can be done in a number of ways, but we're primarily looking at wetland biophysical characteristics. So this can include stuff like phytoplankton dynamics. And you see a map over here of toxic blooms that are occurring kind of all over the coastal regions of the United States and kind of Canada as well. This is to give you a sense of what's happening kind of around here in California. It's very similar on the East Coast. These toxic blooms can really damage local economies. Climate change is a serious issue with all of this. And we hope to kind of put data where there is none right now in our region. We're looking at primary productivity, we're looking at oceanic productivity, and we're looking at different sediment plumes in the region as well to kind of detect and figure out when these things are going to happen. Next slide, please. Okay, thank you. So we're looking at one island specifically off the coast of Georgia first. That's Sapelo Island. I don't know what's going on here. Could we go to the next slide, please? Thank you. Oh, gotcha. Thank you so much. Cool, so now I know the clicker's slow. So we're looking at Sapelo Island. This region is around 17 kilometers tall and then about 4 or 5 kilometers wide. We're hoping to get a 50 by 50 area of this region because it really helps us understand the local ecology. The way that we're performing our scan, we can get about 385 frames of that region to really accomplish our scientific data. But due to some inaccuracies in our system right now that we're working to kind of narrow down, we think we only need about 506 frames for a full mission success to really analyze this. And this is an island where we have those long-term ecological research centers that are partnered with our university, so we can really monitor data on a big scale and then look at the small scale data as well. Our hyperspectral sensor has a spectral resolution of 4.12 nanometers at its narrowest, and that kind of yields around 228 megabytes of data for a single scan of this island. So the pro of that is we have a high spatial resolution, but we kind of have a low SNR in the regions that we're interested with this. So one thing we're looking into is different binning schemes to kind of maximize the actual amount of data we can pull out, the amount of useful information we can pull out of our system. So if we bend to around a 20 nanometers spatial resolution, we can get a lot of good data as well, and it lowers the data that we have to downlink. So that simplifies our system, and it boosts our SNR. So that's nice. To give you kind of an overview of our payload, this optics housing system fits within a 1U in terms of its widest length. And then it's probably only about 15 millimeters tall. It has a diffraction grating in it. It has a monochrome CMOS, and it's very similar in terms of the data that we get to existing ESA sensors and NASA sensors that are a bit older. So we're kind of competing with late 80s and mid 90s type of NASA and ESA sensors. We get 120 meters of spatial resolution, as I mentioned before. And here you kind of see that there's another laser pointer, I believe. You see here is where the light would come in. I'll go over this in the next slide as well. So we have a simulation here of our optical system. Light comes in here, bounces off a mirror, goes through a single slit. That's simply for our scanning. It bounces off another mirrored system where it begins to collimate, and then we have a grating, which is blazed for 50 or 500 nanometers. It has 150 lines per millimeter, and then goes through a focusing system onto a monochrome CMOS. So this pretty much, and it's an adjustable lens system for calibration and such. So I mentioned that we're performing what's known as the push broom method. That pretty much means we're just going forward and scanning. Again, a tried and true method. We want to make sure that our mission can be successful. And basically what that does is we get black and white images of the wavelengths spread across our sensor as we move forward. And so what that might look like here is we have, one, what we would call a frame, and we have many frames as we slice through the scene, through time. We also have our spatial resolution sliced in this direction and the other direction. And then the wavelengths are dispersed from 400 to about 900 up here. Again, this results in 120 meters spatial resolution, which is what we want for our science data. And each pixel is about 1.03 nanometers spectrally, but the signal to noise is so poor on that pixel that we bin 4 pixels together to get that 4.12. And that's done by an FPGA on board, and this lets us produce a 3-dimensional data cube, which is really nice. So if we talk a little bit about our signal to noise, right now we're performing some tests and we're looking at some relative spectral response of our sensor in the lab to really understand how we can optimize what we have right now with our budgeting constraints. And this kind of gives you an idea of the bands we're looking at specifically when we kind of want to prioritize what we look at and what we downlink. You'll see the higher, near the infrared and in infrared, we're binning a lot more. So the bandwidth we're looking at is much wider. We don't need the signal to noise ratio to be that good in those bands actually, because we're only using that for calibration purposes. So that's kind of when the reflectance comes back through the clouds and the atmosphere, and we'll use that to correct the data we see in the lower bands. And we're working on, like I said, different binning schemes to try to optimize that. So in terms of the payload mechanics, it fits within a 1U, and the lens and housing and electronic system is all kind of black boxed into what we're designing. It's PC 104 plus compliant, which is great for CubeSats, and it has a total mass of approximately 0.9 kilograms at the moment. We're looking at various materials to ensure that we have a low thermal expansion, because that is something that we are concerned about and are going to be testing in our lab as well. You see here our housing, which we are currently developing and working on building a prototype of soon. In terms of our electronics, we're also taking a very, what you might describe as kind of safe route. We are working with Cloudland Instruments as kind of a subcontractor and consultant as we design these electronics. Essentially what we do is we read off our CMOS, it goes into the motherboard, and then goes onto our main processor in our PicoZ board, which is running a form of real-time Linux, a real-time scheduled Linux. And then the binning actually occurs on the analog board of the CMOS on an FPGA on the PicoZ board. And then at that point, we simply put it onto our bus and we move our data around and downlink it. Then the total power draw is about 17 watts, but we're only using that power draw for a short moment as we scan. And in terms of bus integration, we're using a Clyde Space stack. We do have custom interface boards that we are designing for our various components. For example, how we interface our what we're calling our core avionics with our payload. You see diagrams to your right about how all that is interfacing. And again, you see we're treating our payload as kind of a black box here. So this kind of gives you an idea of what we're shooting for here. I mentioned that our sensor is going to be similar to NASA and ESA missions of the late 80s and early 90s. So if you look at the Terra mission, we're really not that far away in some respects from the MODIS sensor on Terra. This is the type of data that our researchers at the University of Georgia use all the time, so that's one of the things we were shooting for. And if we're looking at SNR, we're not that different from Sentinel-2, which also uses a push broom method, and that's an ESA mission. So again, data that is very usable for looking at local ecology and kind of getting a better grasp on climate change in our region. And the same kind of goes for Sentinel-3. So we're going to continue to look at, to optimize within our ranges, to get as much data as we can out of our mission. And that's pretty much all I have. Does anybody have any questions? Yes. So he asked, why did we choose to use a diffraction grating instead of an array of bandpass filters directly on our CMOS? The reason is because we want to have, one, we want to have a variety of binning schemes, and two, it's a lot of what we do is cost directed. So we haven't necessarily looked into the full cost associated with that, but when we were designing our system, budget constraints were a huge issue. And this is one of the things we found to be the cheapest option that could still satisfy our mission requirements. For this system? This system, I think, is running around, it can go up to about 8,000 for the system. In terms of raw materials, there's a lot more involved with, construction and all that. Yes. Yes, he asked about for me to comment on how we're going to control our pointing and scanning. We're going to have sets of fine sun sensors mounted onto our solar panels. We also have like crude sun sensors, but I don't think we're using those for scanning. Because of the reflectance that's required for us to get good science data, we can only scan during the day anyway. So we will be able to, so we're assuming the sun is within certain angles already for us to scan, and then that should be enough for us to be able to perform that. We've also considered a horizon tracker, but we found that system to be a little less viable for what we would be doing. He has asked, how are we georeferencing? This is a current problem that we're working on right now. What we're considering doing is having a small finder scope with a very wide field of view, and then having some sort of thumbnail and having our optics mounted such that we know exactly where our system is based on that. But we are actually currently working on that issue.
Any further questions can be asked during the lunch break, if you'll be available. Yep. Thank you, Caleb. Please welcome Sona Hosseini from JPL.
Good morning, everybody. I'm Dr. Sona Hosseini, and I'm a research and instrument scientist at Jet Propulsion Laboratory. There is a critical need for developing miniaturized spectrometers for space. And I'd like within the next 10 minutes to introduce a new technology that was initially developed to fill an observational gap for extended faint targets in space. And I think these technologies are able to help scientists to not make some certain instrument trade-offs that they have been making in planetary science, astrophysics, and earth sciences in the last decades or so. So in this clicker problems. Perfect. So in the astronomical meetings, we've been talking about developing our technology for space capabilities. But in this meeting, we're interested in developing these capabilities for small satellites. And why? Well, because small satellites have lower cost, they're faster to build, and they're relatively easy to upgrade and send it back to space. What excites me about small satellites is they shrink the technology gap between what's our technology advancement on the ground and what goes to the space. And this is so powerful that it has driven a huge market in commercial as well as NASA applications. Well, I started developing this technology to study comets. I'm a planetary scientist and optomechanical engineer, and it turned out the technology that I've been working on was designed to use small aperture telescopes, but it benefited from very miniaturized, it can benefit from miniaturized payloads. And it has a cyclical information on its payload, so it can benefit from higher vibration and optomechanical tolerances. So let's see what we want to do. As a scientist, I can get my data in different ways. I can either take a picture or get a spectra. Now, these two images or these two data represent the same target, but they carry very different information. So as scientists, it's not about just miniaturizing our instrument. It's about using the instrument that would give us the information that we need. As a planetary scientist, I'm interested in getting a spectra, and not just on any spectra. I'm interested in getting high-resolution spectra to look at the line shape, isotopic ratios, and different information of the current of the photons and particles that I'm looking at. But at JPL, we are taking a different approach at this. If my targets are faint and extended, I won't be able to get any photons if I'm looking at a very small field of view. I should calibrate myself and my hand angle to see exactly where to hold this. So if I'm looking at a small field of view on my target, we would require a large aperture telescope. But if we're looking at a larger field of view in our target, then we would be able to gather more photons. And that's what we are doing over there. This is not consistent. My angle was the same. So let's see what type of spectrometers do we have. It's in instrumentation and specifically in spectrometry. It's a trade-off between field of view, resolving power, and bandpass. The high-resolution spectrometers we have been using so far, they're grading spectrometers. They're wonderful instruments, but in high resolving power, they have very small field of views. They have low throughput. That's why we couple them to large aperture telescopes to gather more photons. Spatial heterodyne spectrometers are optimized to have a wider field of view at high spectral resolution. And that's a technology that that we are building at JPL. So the basic mode of spatial heterodyne spectrometers do not come with a spatial information. We would get an integrated spectra over our field of view, but then it can be built in a one-dimensional spatial information. So a basic spatial heterodyne spectrometer is designed by having a grading instead of the mirrors and a microscope interferometer. But at JPL, we are building a reflective spatial heterodyne spectrometers. Why? Because I'm interested in going to shorter wavelengths. The instrument at the reflective spatial heterodyne spectrometer, we can use it at visible and UV, and we can go to shorter UV band passes because we don't have any refracting optics. How does this instrument work? I have, stay tuned. Okay. I have a symmetric grading that is not placed to a specific angle or a wavelength. By shining a wavelength, a collimated light on the grading, it's going to diffract in front of your eyes to 2 orders, plus or minus 1 order. And each order would go through the interferometer, reflects off the mirrors, and goes under the grading for the second time, and it diffracts off the grading for the second time and exits the interferometer. Now, for one specific wavelength, which we call it a heterodyne or homodyne wavelength, the entire interferometer is designed to be everything symmetric for this specific wavelength. And that's the wavelength that my instrument is tuned at. I have no path difference, no phase difference. I don't have any interference fringes. I don't have any data. However, if my wavelength is a little bit changed, then the grading is going to have a different angle for the reflected light. for the diffracted light from the first time. And then we'll get a phase difference that results in that results in our fringe pattern, and we can see by looking at the frequency of this fringe pattern, we can see what the wavelength is. If you look at the design of this instrument, it's a cyclical design. Now, this is beautiful in our purposes for space missions because it would have a higher tolerance for optomechanical vibration, everything, because my beams, both of my arms, are going through the same path. If a temperature changes or one of my optics are knocked off for any reason, it would affect both arms. And I would get my data no matter what, but I can see where the calibration has changed. So the results of my instrument are a set of interference fringes. By taking the two-dimensional Fourier transform of these interference fringes, we will get the power spectra, and from looking at the power spectra, we can get the spectra for our instrument. This data set is looking at sodium D lines. Now, sodium D lines are 5.97 angstroms apart. We're not talking about nanometers, we are in the angstrom space. And I hand-tuned from one D line to the other D line. So that's how high resolving power we are looking at. The resolution, the resolving powers are between 50,000 to 100,000 resolving power, which is the resolution of 1/10 of an angstrom and less. This data set shows about 49,000 resolving power, and it was taken from a prototype instrument that I built for a ground-based telescope at Lick Observatory in Mount Hamilton in Northern California. Here's the size of here's where the instrument was. This instrument, okay, it's not going back. So thank you. So my instrument was in the basement of the 3-meter telescope at Lick Observatory. And it was all designed on the top of this milling machine. Now, just to put it in perspective, in here, it's Hamilton spectrograph, and the same size of that is in the ground. That's my car, it's a Honda CR-V. So this instrument was used for exoplanet research for first time in the United States. It is still used by Berkeley and other researchers for exoplanet research. This instrument that's housed in this housing has the same resolving power as that instrument and has the same resolving power as the instrument that I brought here as a 3D printer. Now I'm going to say what the differences are, but we're talking about a spectral resolution. That instrument was coupled to two telescopes because it was in the coude focus of the two telescopes. The light would come in, hit a side rheostat, which feeds a 60-centimeter telescope in here. And then the 60-centimeter telescope hits the light to the basement of the telescope. Same thing happens with the light from the 3-meter telescope that goes to the basement, to the coude focus, and to the basement of the telescope. The benefits of using two different aperture telescopes is because I can keep the same resolving power, change the field of view in a space. Now, why do I want to change the field of view? Because my targets, if they're extended, that's perfect. They're going to fill my field of view. But if they're not filling my field of view, I'm adding extra noise to my data, which I don't like. So I would like sometimes to shrink my field of view to match it to my target. So in a small sat purposes, we can do this with 10-centimeter and 1-centimeter telescopes. So for the light path, light comes in from the telescope into our field of view. And then from a field of view, I collimate the light onto my grating. It goes to the grating, it diffracts to two orders, it rotates off the roof mirror and the flat mirror, it goes back on the grating, diffracts for the second time, and then I image the fringe localization plane, which is my artificial fringe pattern, on my camera. And this is a big setup. It's about this big at Lick Observatory. But at JPL, we are compacting this, and we are building it smaller. So we are looking at the payload models for using this instrument to doing high spectral resolution in space, either in real missions or small sat missions. And we are figuring out what the configuration for power would be, what the configuration for vibration and instrument performance models, and what the data rate it is. Since I'm getting the data from the entire bandpass all at once, my data rate would be considerably low, and which is of a good use if we are on the small sats. So if I want to put this in perspective of other instruments that are available right now, here it is. And we are missing a picture. Okay. Can I go to the previous slide, please? So that's a picture of a stress on Hubble, which is about like half a car. So these instruments have the same size. These instruments have the same spectral resolution, but look at the sizes. This was Hamilton spectrograph. Half of the same size of this housing is in the ground. This is Keck, high-res at Keck. I used to use this instrument for cometary observations, and it's this on Hubble. And this is my instrument that has almost the same resolving power. And Hubble went to space with lots of money. James Webb Telescope is going to space with lots of money. I think my instrument can go in space. Not very cheap, but slightly less money. And if I want to compare it with other instruments in the same size, grading spectrometers about the same size. They have, put it in perspective, UVIS on Cassini had a resolving power of 280 to 430. Alice on New Horizon, same instrument on Rosetta, is looking at the resolving power of 400, 500, 800. My instrument in the same size would have a resolving power of 50,000 to 70,000, 90,000. But there's a catch. It's narrow bandpass. So having a wide bandpass as a scientist, it's very helpful. Because if I don't know what I'm looking at, I like to see everything. Even in this low resolution, I like to see what are the main elements are there. But if I know what I'm looking at, for instance, if I'm looking at D2H ratio on comets, or if I'm looking at carbon isotopes, or if I'm looking at sulfur in Io plasmatoris, I would like to look at that specific region. I have worked with Eshel spectrometers and with scientists who have worked with Eshel spectrometers that we have this beautiful spectra sets. But the scientists, or my collaborators, or myself, we used to go and only take at these spectral lines and only use the very narrow band passes that we were interested in scientifically. So that's what my instrument would do. This particular design in here, and this is the real scale of the size. And I have printed out the light paths in it. It's optimized for a sodium D lines, 1.2 nanometers bandpass, a field of view 30 arc minutes. And I'm only looking at sodium D lines. But I can actually put these instruments in different channels. So I can build them in an orbital channel, or I can use them and channel them and put them in a vertical channel. So for an orbital channel, I actually do have these 3D prints with me. So if you're interested, we can talk about them and show them after during the break. So for this one, I can just have one rotation and put the whatever channel I'm interested in front of the input from the telescope. Or on the vertical channel, we can have different diachronics and have the band passes that we want in different channels. Let's say one channel can look at oxygen isotopic ratios, the other one can look at carbon ratio, and the other one can look at D2H ratio. Oh, this meant to be in the previous slide, but you can see the size of this instrument with about the same resolving power. So what do I want to do with this? I am personally excited of studying comets. Now, comets are primordial objects from solar system. By studying comets, we can figure out what was the physical conditions in solar system. As comets come by, the solar heating triggers the volatiles in the comets, and all these volatiles come up. And like H2O, CO, CO2, but many more that we don't know what they are. And they're so faint, we need large 10-meter and larger than 10-meter telescope to look at these faint spectral features. But using a spatial heterodyne spectrometer, I can actually look at the comet and look at this entire coma of a comet and get this very faint spectral features. Comets in real size, can you push next, please? They're gigantic. This is the real size of a comet, and that's the real size of sun. They come in hydrogen coma. They're large, and no one had seen the entire thing at high spectral resolution spectrometers, and I like to do that. So with that, I want to say, this is what I want you to take away from this talk. In order to go high spectral resolution, we don't need to lose our throughput. We can have the option of going to higher spectral resolution at high throughput. And spatial heterodyne spectrometers can do it in a compact size using a small aperture telescopes, 10 centimeter telescope, 1 centimeter telescope, depending on where we are looking at. The other thing is spatial heterodyne spectrometers have a compact cyclical layout. So they would benefit from a higher optical and mechanical and vibration tolerances. I am a scientist, would like to get these things to space to look at Earth's upper atmosphere, interplanetary medium, lunar volatiles, sodium tail of moon is of a great interest for me. So if you are in need of a science payload, please come and talk to me. With that, I would be happy to answer your questions. Thank you. Yes?
That was a great talk. I would love to hear more about the exoplanet direct imaging application. How do you think you could configure it in a application where you kind of want to do spatial sampling of your image plane and do spectroscopy like that? You're showing it with a comment, but I'd love to hear about it.
Yeah, well, the exoplanet application is a very, very interesting one. And I'm a little afraid of talking about that because I know how people and I myself can have a very emotional attachment to it. But one thing that's interesting in this design is I get no information in the middle of my bandpass. So I have proposed to our colleagues at JPL that, and we are looking at it, but no one had actually looked at it directly. So we are building this chronograph to get rid of the starlight, right? I have no information in the middle of my bandpass. So and then the resolving power is high. The resolving power is enough, theoretically, to actually look at the Doppler shift of this planet going around the sun. But if I put the starlight in just in front and center of my bandpass, this instrument would inherently block it. And then we can see if and this is all if, because I haven't done the signal-to-noise ratio calculations on it, but if we have an emission line from the exoplanet, then the theoretical resolving power would tell me I should be able to see it just going around the central line. Now, so my lab at JPL came together literally 3 weeks ago, and I have 2 students, and we are putting all these lab instruments together and building the lab prototype. But in my previous instrument, I have investigated this nulling inherently, and I used to call it annoying nulling. Now I'm calling it the beautiful nulling in the middle of my bandpass, and it works. But have I done the study of it? No, I haven't done the signal-to-noise ratio. I can go from a 1 angstrom bandpass to 2 nanometer bandpass.
And then what's your throughput like?
For exoplanets, that's going to be tricky. The reason is exoplanets are point sources, and we want to go to a very small field of view. The study that I did last year at JPL, I was feeding off the pointing accuracy of a small sat. My point of view to this thing was a small sat have about like 5 arc seconds point, about 5 arc seconds pointing accuracy, and I actually calculated what's the average time this small sat is missing my exoplanet. So if my field of view is about 10 arc seconds, I'm going to gain that photons, right? But then I'm going to add some other noises that's coming around it. So it's a trade-off between that. I know, it's hard to say. Yeah, we would love to.
We're going to have to stop it there.
Okay, thank you.
Thank you so much, Sona. Now, please welcome Greg Allen from MIT.
Hi, everyone. I know I'm the last talk before lunch, so I'll try to keep this short and let you get there. So I'm here representing the STAR Lab at MIT, my advisor, Carrie Cahoy, and our team at MIT Lincoln Lab, led by Bill Blackwell. And I'll be talking about a family of microwave radiometer satellites that we've been developing over the past few years. Let's see if the clicker works. So next slide, please. So I'll start with basically why we're undertaking this development program. Next slide. So the basic motivation is severe weather events. It's really important to the world economy and safety of all the people in the world to have precise predictions of severe weather events. Specifically, one of the ones we're looking at is tropical cyclones. As you can see, some damage that a tropical cyclone might cause. But the key to the accuracy of these weather models is a lot of atmospheric data, and specifically that data, a lot of it comes from satellites. And that data is on the temperature of the atmosphere, water vapor content, cloud ice, and things like that. Next slide. All right, so here you can see there's a wide array of data sources that feed into these weather models, and that a lot of them come from satellites, a large proportion, actually more than half. And then specifically, if you could click, the main source, or the source that most impacts the accuracy of these models, is microwave sounding data. Next slide, please. So microwave sounding is passive microwave passive measurements of the microwaves coming from the Earth's atmosphere. Next slide. Next slide. And so what is a microwave radiometer or microwave sounder? When the slide changes, you'll see an example. It's ATMS, the Advanced Technology Microwave Sounder, which is a traditional microwave sounding instrument on a big weather satellite, SWOMI NPP. You can see a person at the bottom of the image for scale, but it's about the size of a small refrigerator or something like that. It has rotating reflectors inside of it to scan across track. And it also has some large calibration targets at hot and cold temperatures. So there's been a lot of money put into development of smaller microwave sounders across NASA and NOAA and other government agencies. And so we were able to shrink down one of these sounders to fit in essentially a 1U by 1U cube. And so the first CubeSat that we launched to test this technology was MicroMass 1. You can see it on this slide. And MicroMass 1 kind of demonstrates why these technologies are pretty amenable to being miniaturized. So specifically, you can see that the data rate is actually not very high. It's something that you could actually deal with on a small satellite platform. And then also, the spatial resolution doesn't need to be very high either. So you really don't need very tight pointing requirements, and you also don't need a really large aperture, so we can actually fit it in this form factor. So the reasoning behind this miniaturization is what you should all be familiar with. Basically, decreased risk of technology development, but also in a more operational sense, the ability to have redundancy, that if one fails, you have backups, but also some reasons that are common to all Earth observing applications, specifically increased or decreased revisit rates, or increased revisit rates, sorry, and also increased coverage across the global surface. Next slide, please. And so in order to actually achieve these operational aspects, we're undertaking development of a series of CubeSats and a CubeSat constellation. So starting with MicroMass 1, which was deployed from the ISS in 2015 after sitting up there for quite a long time, some deployment issues. So we had a few successful contacts, but unfortunately we had a radio failure after a few contacts, and we were not able to fully validate our technology. So we have a follow-on, which is MicroMass 2, which is a really similar architecture, but with an upgraded radiometer. And then the follow-on to that, which will also be launching this year, is Murata. I'll go into more detail of each of these satellites later on. But Murata is a similar radiometer payload to MicroMass 2, but it also includes a co-located GPS radio occultation measurement. And then eventually, a lot of these technologies are going to feed into the Tropics mission, which was recently funded by NASA under the Earth Venture Instrument Call. And that's going to be a CubeSat constellation of 6 to 8 CubeSats targeting higher revisit rates and launch in a few years. Next slide, please. And next slide. So Murata mission is a microwave radiometer technology acceleration. The main payload is a microwave radiometer with 10 channels across 3 bands, measuring temperature, humidity, and cloud ice. And then also we have C-tags, which is a GPS radio occultation system provided by Aerospace Corporation. And the apertures for these 2 instruments are located on opposite sides of the spacecraft just due to the space constraints on a 3U form factor. And so our mission is to advance the TRL of some of these components of our payloads, and specifically to achieve co-located measurements of the GPS radio occultation and the radiometry data. And the way that we do that is with this complicated maneuver where the radiometer takes measurements of the atmosphere as it's flying over, and then the satellite pitches up to look back through that same slice of atmosphere or in the Earth's limb and take the GPS radio occultation measurement on a satellite on the other side of the limb. And that whole maneuver takes about 10 minutes. And basically the point of those that co-located measurement is to be able to calibrate the radiometer with the GPS radio occultation measurements. So those measurements you wouldn't get as often because basically you only have targets of opportunity when you have a GPS satellite in the right location. But when you do have them, you can use them to calibrate your radiometer data, which you can basically get the global coverage with. Next slide, please. So here's a look at the inside, an exploded view of the satellite. So down here we have the GPS RO antenna array, and you'll see a better view of that on the next slide. And then the other payload is the microwave radiometer up here, which, so you see the aperture and all the associated feeds and radio front end, as well as the IF processor and payload interface module down here. Avionics stack, pretty standard. We have actually 2 radios this time. We got burned with micromass, so we are going with a high rate cadet UHF radio, and then our own design for a lower rate UHF radio that we'll use for the day-to-day command and control. And then the attitude control system is a Maryland Aerospace MAI 400 with some additional Earth Horizon sensors. Next slide, please. So the current status of the spacecraft, first of all, so you can see the 3 patch antennas that make up the GPS RO system. Produces basically a fan beam, which allows us to get a higher gain, more directivity. So we currently completed integration and environmental testing. We put the payload itself through its own payload thermal vacuum calibration test with some microwave blackbody targets. And we're doing some continued work to prepare for launch, which will be later this year. It's launching on a Delta II out of Vandenberg with JPSS-1. And we're working on completing our own UHF ground station for that low rate radio at MIT on campus, and then installing some GSE at Wallops for the higher rate radio. Next slide, please. So this is our results for radiometer calibration. Basically, the way that the radiometer works, I mentioned before that in ATMS you have blackbody targets built into the actual instrument, and that makes up a large portion of the swap. So what we're doing is cold calibration with space. Basically, as the instrument scans, you get a cold calibration in deep space, and then we have a hot calibration, which is actually a noise diode, microwave noise diode built into the satellite itself. So our actual success criteria is mostly the noise equivalent delta temperature, or the NEDT, of the radiometer instrument. you can see in this plot here, basically we're trying to get an NEDT of under 1 Kelvin, and with a stretch goal of under 0.5 Kelvin. So you can see one of the channels is out of what we expected or what we shot for, but we're basically on target with the TRL advancement of the payload as a whole. We have some additional data processing for calibration to do with some of the other issues that came up in payload TVAC. Next slide, please. So we also have a few integration lessons learned, just sort of education if this comes up in your particular satellite. We had a solar panel tie down break during vibration. Basically, the staking on the tie down wasn't secure enough, so the tie down got loose, the actual cord itself got loose, and that allowed it to rub against the housing that houses the thermal knife that's actually inside the solar panel assembly. And so basically the fix there was to stake that a little bit better. But that's a key takeaway here is we probably won't make that mistake, that particular mistake again. And then the other thing was that we had a mismatch in our CAD model of the spacecraft, so a mismatch between the CAD model and the as-built spacecraft. So our CG location was a little bit out of spec, and we had to figure out how to attach a ballast plate to the end of the spacecraft, and we ended up going with some thermally conductive epoxy. Also, during kind of earlier in integration, we had some unresponsive channels in our radiometer that we actually never resolved, but we basically decided to go with it because we had still enough channels to validate the radiometer design as a whole, and then also the Micromass 2 satellites will be validating some of the same radiometer payload stuff. Next slide, please. Next slide. So here's a quick overview of Micromass and a little bit more in depth on the radiometer channels. So Micromass 2 has 10 channels. It's an upgrade from Micromass 1, and in that it also has more bands. So we get an additionally to temperature, we get water vapor measurement, also precipitation and pressure and different altitudes in the atmosphere. Here you can actually see our deployment series of photos from Micromass 1 as well as the Micromass 1 completed flight model. Next slide, please. So this is the operational mode of Micromass 1 and Micromass 2. You can see the spinning payload that gives you this cross-track swaths as you're moving across. Basically, the status of Micromass 2 right now, there's 2 flight units on their path to delivery. The first one should be delivered later this summer for launch in September, around the same time as Murata. And the second one is right behind it, a few months behind it. Next slide, please. And that brings us to TROPICS, which is the satellite. It's been funded by NASA ESTO. Basically, the goal here is to get high revisit rates across the tropical region. So we'll have a few satellites in 3 different planes, and those planes will be inclined mostly over the tropics. So we're aiming for 30-minute revisit rates overall. We're not expecting to get them with just our 6 CubeSats, but we're expecting to demonstrate that in some locations over the tropical regions. And the goal there is that higher revisit rates are especially important when you're looking at really severe and quickly developing weather events such as tropical cyclones, so and which develop in the tropical region. And so this is sort of a best bang for your buck as far as getting high revisit rates and impacting, basically getting economic value in predicting the severe weather events, giving people forward warning, and allowing the government to prepare for these events. Next slide, please. And where TROPICS is at right now, they're selecting a vendor for the bus, where they're going to use the same Lincoln Labs developed microwave payloads, but they're making some improvements to increase manufacturability and ease of calibration, which is important when we're talking about building a larger constellation eventually, even beyond these 6 to 8 CubeSats. And then that's expected to launch on its own dedicated small satellite launcher, which is a really cool thing. And that's a few years out, probably 2020. That's all I have, but happy to take any questions. Yeah, so the question was what was the cause of the CG offset between the CAD and the as-built flight model? Basically, there were some hidden components that weren't shown in the model, but were being factored into the CAD software's CG calculations. So when we actually built it, we didn't build it with those components, but they were in the model, so that threw off our CG. One more question? All right, in that case, you can all go to lunch.
I have one quick announcement before I let you guys go for lunch, actually. So just if you are interested in taking a tour of our CubeSat and PolySat lab, there are going to be tour groups meeting at 1 o'clock, 2 o'clock, and 4 o'clock at the registration booth up front. And that's all. So I'd like to thank Greg, and I would like to thank Clyde Space for this lunch break, and we are going to be meeting back here at 1:30. Thank you.
Well, thanks to all you guys for coming back from lunch. I promise not to put everybody to sleep, or at least I'll try not to put everybody to sleep. I want to give a status update of the Pathfinder Technology Demonstrator mission, which we're working through at NASA Ames. And this is a mission that is funded by the Satellite Technology Mission Directorate through the Small Satellite Technology Program Office. It's a series of 6U spacecraft that we're using to demonstrate new technologies, new CubeSat technologies. So what we're looking for here and what we're trying to do is something that we've done a lot with CubeSats in the past, which is to try and bridge that gap, that technology chasm that we always talk about. And at NASA and DoD, we always talk about TRLs, technology readiness levels, from 6 to 7. 6 meaning I've developed it, it works on the ground, but I haven't flown it. 7, 8, 9 meaning I've flown it to some degree. And then people are more apt to then use it as part of their mission, right? And so that's our objective here, is to demonstrate and characterize novel satellite technologies in low Earth orbit. Now, as part of this, we recognize that there's a lot of capability already built up within the CubeSat industry, and so we partner with both technologists who are bringing the technology that is to be demonstrated, but also with industry. And so we actually put out an RFP about a year and a half ago or so for the spacecraft bus. Okay, and that was recently announced maybe 6 months or so ago that we're working with TIVAC on the 6U bus. They're going to be providing the bus and integration capabilities and actually a ground data system. See if this works. There we go. So as part of this development, we wanted to have a standard spacecraft bus with a standard interface, as standard as we can get, because we are going to be trying to fly some different types of technologies. And so we developed some level 1 requirements. We developed some level 2 requirements for the payload. And as part of that, we developed actually an ICD that governs that payload to spacecraft interface, right? And so it tells you that you're going to be an RS-422 interface, that you can, let's see here, that you can cover a certain volume. And in fact, you can see here that the payload volume is about 2U in size, with the spacecraft avionics taking the rest of that. And actually, I think on the bus that we actually have, we have a little bit more volume available for the payload. But the point being that what we want to do is we want to try and separate the payload development work from the technology development work so that we can actually have a series of semi-standard buses, right? And I'll tell you, over the last, I won't tell you how many years I've been doing this, but over that time, I've seen lots of one-off standard buses. Everybody builds one, and then they get tailored exactly to the mission. So what we did here was we built this ICD, but we recognize that there are going to be some mission uniques, right? So we said as RS-422, somebody may come in and say, hey, actually I need a CAN bus. And so there can be modifications made to the interface on a mission-by-mission basis as we're flying these technologies. So the PTD bus solution actually is provided by TIVAC. You can see a picture of a rendering of the spacecraft down in the lower left. As an aside, later this afternoon, there's going to be a full-scale mock-up of this spacecraft at the Ames booth up here on the right-hand side. And I heard it's pretty big, so it's pretty cool. I recommend you guys go check it out. So TIVAC provided a solution that is based on their current capabilities, their hardware that has flown before. It is a 6U, roughly 12 kilogram spacecraft. It provides 45 watts of power orbit average to the payload. And different payloads have, some of them will require that full 45 watts, some of them won't. Let's see, TIVAC was selected to provide a full set of 5 buses. Our first mission is actually going to be to fly and demonstrate a BUSIC microelectrospray propulsion system. And that one, we received notice recently that we got a CSLI flight for sort of the second half, August, September timeframe of next year. So we're going to be moving forward with that. Let's see, we had the kickoff with TIVAC in January. And then we actually recently had, in March, we had a system requirements review. They're working with the first payload, being BUSIC, to get the interface just right and work with them for delivery in let's see, delivery in October from Busick for integration through and then delivery for launch in the end of July of next year. Yep. Well, you know what? I'll skip the schedule chart. It's boring anyway. Oh, no, there it is. So like I said, we're looking at delivery of the first mission in the first payload in October, the first mission flying next year, and then we're going to fly 4 more missions on 6-month centers. The technologies that are going to be flown right now are TBD, although we do have some different ones that we're working with and looking at. But the STMD and SSTP are going to be working out exactly which of the technologies we're working with right now are going to get slotted into which spot. As another part of this, the ground data system, when we went out with the RFP, we gave vendors the option of bidding either to work through the NEN, traditional ground data system, or to provide their own ground data system solution, because we knew that in addition to leveraging the capabilities that people have in building a full spacecraft bus, we also know that lots of people have ground data systems, right? I mean, there's lots of CubeSats flying and lots of data coming down. And so we wanted to give them that opportunity. TIVAC took that opportunity, and we'll be working with them. They've got a nice S-band and UHF radio solution that works with their ground data system. And so they'll be accessing the spacecraft and getting data and sending commands up. That information will be coming to Ames, and we will be working with the technology providers and with TIVAC to operate the spacecraft and such. And we're still working out the details of that right now. So operationally, it's a CubeSat, right? So it's a 90-day type of mission. So we launch powered off. When we get kicked out of the can, we take 30 minutes to 45 minutes of being still powered off, but survival heat on. We boot up. We deploy these large solar arrays. We get ourselves into a safe condition, and then we wait for ground command. We'll spend a week testing out the bus, making sure everything is good, getting the payloads ready to go, and then we'll have 90 days to have a really detailed characterization plan to run. And we're working with all the payload providers to develop that characterization plan. Because we're not just going to say, for example, at the thruster, we don't want to just turn it on, fire it, and say, look, it worked. We want to run it in different temperatures. We want to be able to change some voltages around. We want to be able to characterize it for the different types of missions that it might be flying. There we go. So as I said, we're testing a number of different technologies, and I'll get into some, the Busick PTD1, and then some other potential technologies that we're looking at, that we're working with. But STMD and SSTP are funding the Pathfinder Technology Demonstrator, which is being managed and run out of NASA Ames, to produce a 6U bus, which TIVAC is producing the bus, and they're doing the integration of the payload. The payloads come from a number of different sources. SBIRs and the CRP program, Commercial Readiness Program, are funding a lot of those and getting them up to TRL-6 so that we can then deliver them to us to integrate with the spacecraft. There's I'm sure a lot of you have heard about the Tipping Point program. Probably a number of you have been involved in that. That's another source of technology. And then internal NASA calls as well, as they look around the centers and they find other technologies that are interesting to fly. And so the first set of 5 of them they're sort of down the path of making those selections, and we're looking forward to that. As obviously we'll get them integrated with the payload, with the bus. We'll fly the mission, and then we're going to obviously, with successful missions, we're going to infuse that technology both into the missions that NASA wants to fly, but also into the general CubeSat world, right? That a lot of the commercial folks are interested in, I know, in propulsion technology, in some of the different types of technologies that we're using. Oh, there we go. Okay, so this is the Busick thruster. This thruster is a microfluidic electrospray thruster. It's on the order of 100 micronewtons. It's got a high ISP, EP type of characteristics. It's based on some technology that they developed for LISA Pathfinder, which has actually been successfully flying now for a while. It has a non-volatile propellant. It doesn't use pressure vessels or moving parts or valves. It's got a power that kind of matches up with the CubeSat kind of mission. So this is one that we're really excited about and interested in flying and characterizing and seeing how that can then help the next generation of CubeSat missions. We're also looking at, obviously, attitude control solutions. This is a Blue Canyon hyper-exact tipping point solution that they were looking at, where we want to, we need to take CubeSats from 30-day missions to, year, 3-year type of longer missions, and to fly in places other than just in low Earth orbit, right? We want to be able to get up to GEO, lots of opportunities to go into GTO, although pretty bad radiation environment, but that's what they're trying to do here. The Tether's Unlimited Hydros thruster system, right, is another nice one because it uses water as a propellant. That gets around a lot of concerns that people have with secondaries, with propulsion systems. And then we've been working with Aerojet Rocketdyne. This is a green prop, more like a hydrazine replacement type of a system, high thrust, good ISP, but not like an EP type of system. Oop. Okay. Oh, you know what? I forgot one other thing. PTD-1 is going to be demonstrating the Busick thruster, but we're also going to fly an experiment with the Global Star system. We're going to follow on with what the Shark missions have done. And TIVAC is actually working that out. And so we're going to run some experiments that are non-interfering with the main mission, but to see that we can command the spacecraft through the Global Star system, that we can get data down and characterize that as to how well we can move data around, and how reliably, and so on. So, in conclusion, the PTD mission is moving forward. We've had our kickoff for the spacecraft bus. We've had a system requirements review. We've got a PDR that's coming up in the summer. We've got delivery of the Busick. The first payload that we're going to demonstrate is going to be delivered in October, end of October. And we'll be flying next year. And then after that, like I said, it's going to be 6-month centers for this standard bus. It's going to get reproduced 5 times, and we'll fly 5 missions. And we're looking forward to the technology that we're going to be demonstrating with this. We're hopeful that it's going to motivate new classes of missions that can be flown with CubeSats. So, any questions? Thank you.
Thank you, John. Okay, next up, I'd like to introduce Travis Imkin from Jet Propulsion Laboratory, California Institute of Technology.
All right, I'll wait for, there we go. So I'm Travis, I'm from JPL. I'm in the Project Systems Engineering and Formulation section, and I'm here to give you guys a briefing on our radar and a CubeSat mission, where we've managed to stuff a Ka-band precipitation profiling radar into the 6U form factor. They claim this clicker works now. Bingo. All right, so RainCube is a technology demonstration mission. We kicked off in 2015 as part of a response to NASA's Earth Science Technology Office's Invest 15 solicitation. And what we have is a Ka-band radar. JPL had been developing this radar. It is about TRL-4, and then Invest is giving us the chance to then take that radar to flight, raise it up to TRL-7. Like mini CubeSats, we're a 6U CubeSat. We're going up on Alana 23, which I've heard dates anywhere between March and June of 2018 of next year. Once the astronauts then pop us out, we'll have a nominal 3-month mission while on orbit. The 2 key pieces that we're trying to demonstrate in space are both the radar electronics, which we call the mini CAR-C, as well as our half-meter deployable antenna, which we call the CARBTA, and I'll talk a little bit more about that later. Piecing both of those together is what makes us have the full profiling mission. And so, as we all know, as CubeSat developers, a lot of times we start in humble beginnings. So in the case of this picture, RainCube actually started off in a tent. So this is us outside demonstrating kind of the breadboard version of our radar. And that's when we actually faced one of the biggest challenges of our mission, which was trying to find precipitation over Los Angeles to prove that the radar worked. So, sorry, I have to get in the drought jokes while I can, because now it's raining again. So a little bit kind of high level about how our radar works is we are demonstrating a profiling radar, which means we'll basically shoot a pulse down and we'll measure the reflectance of that pulse as it comes back. Depending on how the pulse has changed and the timing in which we get it back, we can understand basically what's beneath us. RainCube is novel in a few ways, basically so we could actually fit it within the volume, mass, and power limits that we have on our platform. We use kind of a novel pulse compression technique, which reduces our transmit power. We actually use an order of magnitude fewer parts compared to other radars when we modulate up from baseband to Ka band, which both reduces our complexity and also additionally reduces our power. Then we also can take some advantages in digital signal processing, which helps us get a more optimal response both on the pulse out and on the pulse back. So we tested all of these elements together as close as we could get to space, which was an airborne demo back in July of 2015. And this is kind of what we would expect to see post-processing after flying our mission. So each of these vertical stripes would be a radar pulse. On kind of the left side of the screen, you can see when they flew over a storm, so they can see where the clouds are, what kind of precipitation they see. And that basically demonstrated that we had the sensitivity and resolution that we needed. Moving more towards the right, when we weren't flying over precipitation, we were able to demonstrate that when we aren't flying over anything, we can actually compress that pulse down and get a good, clean signal. So we are working with TIVAC. So JPL is building the instrument. The instrument is now complete, and we're getting set to deliver it to TIVAC here in a couple of months. Specifically on our radar, and I realized that I actually kind of lied on this slide, we made it even more difficult on TIVAC because the radar is actually 4.5U, which means the bus, the entire operating spacecraft is fit into that top kind of 1.5U piece. Specifically, our radar is tuned to look at any altitudes between 0 and 18 kilometers. Our footprint on the ground is governed by our antenna aperture and our altitude. It'll be better than 10 kilometers, probably about 8.5 kilometers at a 400 kilometer orbiting altitude. And then within there, we'll have a 250 meter vertical resolution. This is all enabled by that half-meter deployable antenna. Oops, oh boy, I really done broke it. I guess this isn't the laser pointer. Oh, it's right here. Anyways, so it's the half-meter antenna. You can't miss it on the screen. So the way this process worked is we created a bunch of level 3 requirements when out looking for a bus vendor. Some of the key requirements we imposed on TIVAC is we said, well, we want to operate the radar 25% of the time. And when the radar's operating in transmit mode, it wants 35 watts, is what we said. And they said, no problem. I said, yeah, but if you're going to operate it in transmit mode, you got to do it for a full 90-minute orbit. And suddenly, it's not quite as easy. So that basically means running at 35 watts for 90 minutes, and then you have the next 3 orbits to cool down, recharge your batteries, get all that data back down to the ground, and do any other housekeeping you need. So it's certainly driving the mission architecture. We don't spit out that much data. It comes out to be about 50 kilobits per second when we're operating in transmit mode. Comes down to about 12 gigabits in a week, which TIVAC will bring down for us over an S-band link. So really, I just have a bunch of pictures because those are the most fun things. Over here on the left is when we were assembling the flight unit of the radar. These are all the pieces put together with some ground support equipment tied in. Once we mounted all of the radar together onto its chassis, we then went into an ambient thermal chamber, which you can see up here in the top right. That was an important test for us because we needed to get some a priori knowledge as to how the radar would behave over temperatures. So we were able to do this in the kind of our ambient thermal chamber. From there, we then integrated the antenna, which you can see in its stowed cylinder there in the bottom right. And then we took it off to environmental testing. So we did vibe it. We passed vibe. That was a fun and exciting test. We've also done a TVAC on the radar system as a whole, including the antenna, as well as another test on the antenna alone. But here you can see the radar post-TVAC test. The antenna was deployed in the chamber. Unfortunately, we weren't able to radiate it in the chamber because we couldn't fit all that RF-absorbing material in there. So you can see here in the bottom left, we took the radar out, set it on a table, and then practiced radiating it in transmit mode post-TVAC to prove that everything had worked. So here's the video. I think I have a 50-50 chance that it'll work. Maybe somebody backstage can it play? There we go. All right, so this whole deployment process takes about 3 minutes. So here we are at 8 times speed. So we have a motor that's connected to gears and then connected to 4 screws that are essentially driving this up. So there is some sound. This is all of us talking in the background about how excited we are. This is a camera outside of the chamber. So as it begins to push up, there are springs, and so no longer constrained by the cylinder. Now here in real time, you can see that things are starting to bloom up. Right now, the tips are constrained by that center cylinder you see that's still moving up. And also notice that the subreflector is also on top of that center cylinder. So eventually we'll hit slow motion, and this is very dramatic. Here we are. So all the tips are tied together, and you'll see that in the deployment. There we go. And then as we continue to push the antenna up, you'll see the subreflector, which is in the middle, is spring-loaded, and then will pop up. So that's our one critical event on our mission. It's going to be very exciting, and TIVAC has been gracious enough to include a camera on the spacecraft just so we can make sure that this works. And we hope to get some really, really cool pictures out of it. All right, some of our upcoming milestones, like I mentioned, the radar is assembled. We'll be delivering that to TIVAC either in May or June of this year. A few months after that, once the system is put together in INT, we'll have our mission readiness review, and then unfortunately we will deliver to storage. We will have a several-month bathtub until our anticipated launch, kind of in the second quarter of next year, ultimately within popping out of the ISS, then completing our primary mission just a few months after that. We expect to be in orbit maybe 2 or 3 months longer than our nominal 3-month mission. So a question we often get is what's coming next after RainCube? And since we're all engineers, our answer is like, well, it's going to be RainCubes, duh, right? We're going to fly a constellation of it. So the idea of flying these radars, so we're demonstrating the technology, but imagine if you had many of these CubeSats all in a row in an orbiting plane. If they could all get time-varying measurements, you could basically see whether the evolution of these systems at kind of the scale that's important for forecasting on the order of minutes. Then take this kind of train of CubeSats and move them to a second orbital plane, and then you could understand kind of what are some of the variabilities we see in the diurnal cycles of weather. So GPL loves radar. This is a concept we're really interested in. I think we'd all like to get better weather forecasts. So I'll close out with just some pictures. This has been a really great process. The JPL radar team has worked really well to create a radar that performs even better than the requirements asked it to. We've come a long way from our little tent to making it all the way to the clean room where we assembled and then the environmental test labs. And that's all I have. So here's a picture of our JPL team, TIVAC team not included, but to be included in the small sat presentation on RainCube when the thing is built. So with that, I'll be happy to take any questions. Go ahead. Sure, so the requirement on the radar was that it needs to support a transmit mode of 35 watts. When it wasn't in transmit mode, it needed to be maintained in standby mode, which was 10 watts was the requirement. So per orbit, we're essentially in one orbit of 35 watts and then 3 orbits of 10 watts, plus whatever the bus needs on top of that. What was the second half of your question? That's right. So the radar is in transmit mode for 1 full orbit, and then within that orbit, I think it's actually got maybe, the radar should set up a pulse every, like a 10% duty cycle, but that's how the instrument operates. Oh, go ahead. Let's see. This is not the official answer since I'm not the radar engineer, but colloquially, it averages out to about 1 watt is radiated out for the 35 watts we were required to put in. No other questions? Well, thank you so much. Oh, wait, Tony has one. So that's actually a really interesting comment. Our level 1 requirement that we wrote, we wanted to prove that the technology worked, so we had to see precipitation sometime. And so we factored in our duty cycle, errors in getting the data down to the ground, and we proved that there was a 6 sigma chance that for operating for 2 days, cumulative, we would see precipitation somewhere on Earth. Earth is actually a very wet place. So there wasn't really a need to put a camera on there to see if there's a cloud because there's very good odds that we will see precipitation. You could. That's for ring cubes, though. That's not ring cube. All right, they're telling me to get off the stage, so thank you.
Thank you, Travis. I'd like to introduce Rick Doe from SRI International.
Today I'm going to talk about the ITSPIN's ionospheric imaging mission. This is an NSF Thomson spinner that will tomographically image the nighttime F-region ionosphere. And sometime between the first and second submission to NSF, our PI decided to make the acronym into a full sentence. So we're proud of that accomplishment. So I'm going to talk a little bit about the mission overview, the sensor that we have in place, some of the architecture associated with the attitude control system, and give a quick status on our flight systems. So the science goals are to make multiple ray path measurements through the ionosphere, which is glowing in the UV. And by spinning the spacecraft in plane, we're able to get multiple intersecting ray paths through that glowing ionosphere. So the purpose, of course, is to do some science, and we're interested in looking at the top side of the ionosphere where the predominantly O+ ions charge exchange with helium and hydrogen and drop away. So our Gary, our PI, was first to recognize that we should see a nice gradient drop-off in the night glow at the top side. And why do we want to study that? We just want to study charge exchange with protons. It's an important interaction in the upper part of the Earth's ionosphere. We also want to look at those pesky, naturally occurring ionospheric structures, bubbles and patches that are known to mess up our RF communication systems. So just in rough terms, the ionospheric F region at night is predominantly O+, and those oxygen ions want to recombine with ambient electrons. It's a fairly predictable process, and for every interaction, there is a certain yield of let's see, where's my laser? Oh, I just turned everything off. There's a certain yield of 1356 nanometer photons that are given off. And so if you think about it, you're measuring a column brightness through the ionosphere, which means you can actually treat the recovery of the signal as a total electron content measurement. And of course, if you can make enough measurements along a long track altitude versus latitude projection grid, you can recover structures. So that's the idea. We want to sample in plane with a photometer that's sensitive and is rotating so that we can reconstruct via a tomographic inversion those structures. We want to use our C-tip photometer that was developed on the Air Force Sense mission back in 2012. And our colleagues at Montana State University are providing these 3U spacecraft, which borrows, it leverages significant technological developments from the Firebird NSF mission, which we've heard about earlier today. And of course, the challenge here, the heavy lifting, is to figure out how to do the attitude control system so that we can maintain a constant pitch rate without inducing too much coning. The idea is, of course, if we pitch about orbit normal, then we're recovering multiple ray paths as we progress along the satellite orbit. And the challenge for using traditional ADCS systems that depend on star trackers is that you're smearing the star field. So the idea is to use enough sensors to give us information about the limb so we can maintain a constant pitch rate as well as correct any roll perturbations we might encounter. We've done extensive air glow simulations or night glow simulations for the ionosphere. This is a Poisson process. We're going to count single photons so we can well characterize our recovered SNR, and we've decided for science purposes we need it to be on the order of 5 to 8 to be able to recover the structures we're looking at. This is definitely a noise dominated measurement, so we're going to be integrating on the order of 1/4 to 1/2 of a second per look angle. And our colleagues at APL, Romina Nikokar and Gary Bust, have done a nice SNR simulation to show that for the places where we want to look at the top side of the ionosphere and the bottom side where the irregularities are forming, we have sufficient SNR to carry out and close on our science goals. The CubeSat tiny ionospheric photometer was a purpose-built sensor that we put together for Air Force SMC in 2012 for their SENSE missions. Now, SENSE mission was designed as an operational Air Force mission to provide space weather soundings. And we originally were working with Montana State University on a spinning idea that did not actually come to fruition until this NSF opportunity. But the Boeing solution used a nadir pointing C-tip photometer. So the idea was they just wanted to take total inventory of the ionosphere below the spacecraft. So instead of spinning, the Boeing system just needed to maintain an LVLH attitude orientation. It's a small unit. It occupies about 1 U. It's an F1 system and sees about 3 to 4 degrees field of view, field of regard. It's pretty sensitive when you're gathering that many photons and you're just supplying it to a single pixel. You can claim 20 times the sensitivity of our traditional spectrographs that we're used to seeing with the SUSY spectrograph and GUVI on the TIME satellite. The current status is that we've remembered how to build this after 5 years, and we've delivered the engineering model and the flight unit to Montana State University. So any good design process should start down with flow down requirements, and I want to credit Keith Mashburn for coming up with the review of the requirements for the attitude control system on its spins. There's a lot of words here, but basically we have to constrain all the rates and all the angles that we care about. So if you think about it, you want to make sure you have a nice, well-controlled spin rate in the orbit plane, and you want good knowledge. So our knowledge is 0.3 degrees currently, subject to review, and we want to minimize our coning. And any good attitude control system needs to talk about the elements. I don't believe there is an IMU on board its spins, but we certainly have accelerometers, and there's a miniature gyro on board. So this is an essential part of starting down the path of designing an ADCS. You want to have a well-configured control loop. You want to figure out where your sensitivities are and begin taking a first cut at a control law. And our Montana State University colleagues realized early on that we really needed to get an expert partner. So they have been working very, very closely with Maryland Aerospace Incorporated to implement design changes to their MAI 400. So in addition to the normal things you get, the reaction wheel, the microcontroller, the torque rods, and the magnetometer, we put a lot of emphasis on the infrared sensors. So the idea is that if you cant the sensors to measure the limb, you can get a well-configured pitch rate as well as deal with any roll perturbations that you might have, because you'd like to sample right down through nadir. The current status for the ADCS system, they're waiting on their final control software to come from Maryland. The hardware will soon follow. The flight computer that drives its spins, which is a Montana homebrew, will indeed be running the ADCS, and it's got 80% of its flight software complete. And they're doing a bunch of hardware in the loop simulations. The system integration is proceeding as we would expect. The CTIP is at one end of the satellite, the ADCS is at the other, and the avionics stack, heavily leveraged on the Firebird satellite, occupies the volume and provides functions that we're normally used to seeing. And I'm going to step through the flight subsystems and then probably take some questions. The flight computer is completely functional. The flight code is 90% complete. And it is speaking both to the attitude control engineering interface as well as the CTIP engineering model payload. The integration status for the electrical power system is completely functional. It's built up and the flight software is 100% complete. We do have to watch our power load on the CTIP photometer. We've got about 2 to 3 watt heater inside that's keeping one of our UV crystals at 100 degrees C. So we're doing smart things. That is, when the sun comes up and we're not making ionospheric measurements, we turn off that heater. So we're trying to shed some power power load as much as we can. This is a system that allows the watchdog timer to control the system power. And the ADCS, of course, you don't want to be doing a watchdog on something that's supposed to be operating in science mode 24/7. So if the ADCS goes pear-shaped, they have the ability to reset it externally, but it's not hardwired to the watchdog. And the electrical GSE connection to this electrical power system allows any of its processors to be reprogrammed. Communication system is a standard lithium radio from AstroDev, and our colleagues in Montana have a lot of experience with this radio. I didn't mention that the prime telemetry and TT&C node for the It Spins mission will be in Bozeman. They have got a stellar track record with their ConOps. The electrical ground support system is ready to go, and it can speak to any of the PIC on the satellite. And because we're using a PIC 18 on our payload, we can actually do late breaking payload uplinks. The full integration is at work. You see 2 views of the flat sat. The specific cutouts for the Pumpkin 3U structure are being sent out and worked on right now. You can obviously imagine that we have to have a lot of access ports to be able to see the Earth with our limb sensors. And there's a significant work going forward on the battery system, and the build-up of the flight system is expected at the end of May. We are currently manifested with ISAT-2 for a launch in late 2018, and we're on the critical path. Thanks. Any questions?
Thank you, Rick. We will now have Jaejin Lee from Korea Astronomy and Space Science Institution.
Good afternoon. My name is Jaejin Lee from Korea. It's my honor to introduce our new mission, SNIPE, that is specialized for space weather research. So, as you know, there are many small-scale structures in the low altitude orbit, and so this This figure shows the electron microburst observed by Korean scientific satellite STSat-1. Actually, sorry. The electron microburst is the very short duration electron precipitation. So just a single satellite has this some inherent problems resolving space and time ambiguity. So to solve these problems, we need multi-satellite formation flying. So CASI decided to launch its SNIPE missions that is consists of 4 nanosatellites, and that will be launched in 2020. SNIPE missions, that is a small-scale magnetosphere and ionosphere plasma experiment, will identify temporal and spatial variation of small-scale plasma structures in the ionosphere and magnetosphere. SNIPE mission consists of 4 6U nanosatellites, and they will do formation flying. So that means each satellite distance will be controlled from 10 kilometers to 100 kilometers for 6 months. The designed mission lifetime is 1 year, and so our targeted orbit is about 500 kilometers to 600 kilometers, and we prefer polar orbit. Actually, the sun-synchronous orbit would be better, and we hope to launch this mission in 2020. SNIPE mission is the science mission. So we selected 5 science targets. So not only electron microburst. Electron microburst is the short duration, short time duration electron precipitation near auroral region. So, however, there are many small-scale plasma structures. For example, plasma trough, that is the plasma density depletion region in the subauroral region, and the polar patchy, that is the plasma density enhancement structure on the polar cap, and plasma bubbles, that is the plasma cavity, and the blobs is the enhancement, electron density enhancement observed near equatorial region. And emic wave is also interesting science topic that is generated from high altitude equatorial region. And so it is believed that emic wave is a very important wave in the atmospheric physics. So, to observe these small-scale plasma structures, so our SNIPE mission will do formation flying like this. So the first 2 satellites, so that these 2 satellites moving parallel to the perpendicular to the moving direction would be would observe the spatial variation of the plasma structures, and so following 2 satellites, these 2 satellites would be aligned to the moving direction, and so they can measure the temporal variation. And so the right-hand side figure the formation, so on the polar region would be changes similar polar formations in the equatorial region. So I will explain more detail. So we call it T-shaped formations. So the first two satellites on the moving direction will measure spatial variations. However, if these two satellites have the same formations in on orbit, the distance between two satellites would be very close on the polar region. So, however, so we want to use a constant distance. So we change the shape of formation like this in the polar region. Then still we can measure temporal and spatial variation with the same distance. This is the main idea of our formation prime. And this video shows how our four satellites do formation prime. So and to do such kind of formation prime, so we need a proportional system. And so we calculated the requirement for proportional system. So to model the formation prime, so we considered gravitational model, JGM3, and so we considered air drag and third body interference. So, and we assumed this, the SNIPE has T-shaped formation with the accuracy of 10 degrees. And then the required delta V for 1 year is from 21 meter per sec to 31 meter per sec. We believe this total delta V is the achievable from the commercial propulsion system. Three identical scientific instruments will be aboard on each spacecraft. First, SST, solid-state telescope. This instrument will measure energetic electrons with very high temporal resolution. And flux gate magnetometer will measure geomagnetic field with a resolution of 0.1 nanotesla. And LP, Langmuir probe, will measure electron density and temperature. Also, the two instruments will be provided from our Japanese partners, search coil and electrostatic analyzers. The spacecraft platform will be developed by the Korean Aerospace Research Institute. And so the boost system has the high technology subsystems. So the spacecraft bus would be controlled by reaction wheel. The attitude would be controlled by reaction fields. So to measure the electron precipitation, so we install two telescopes. And so one is aligned to geomagnetic field, and the other one would be perpendicular to the geomagnetic field. And so our reaction wheel attitude control system will do such kind of operation. For scientific operations, the SNIPE mission will observe the small-scale plasma structures at the conjugate point with the largest missions, such as THEMIS, MMS, final length probes, ERG, NOAA GOES satellites. Also, our mission will do multi-point observation with the other similar low Earth orbit satellites like ICON, NOAA, DMSP, SWAM, or many other CubeSat. So our measured data will be analyzed with the ground observations like IceCat and inner magnet or Superdome, something like that. So now our SNIPE mission is under development by the leading of CASI, my institute. And so we cooperate with the CARI for both the system development, and also we cooperate with the Yonsei University for formation flying algorithm. And so we welcome international collaboration. Thank you. Yep. Fight me? No. So because the in the CubeSat, boom is very difficult technology. So instead of using boom, so we measure the bus system noise before launching and so analyze the data. Okay. No question? Thank you.
Thank you, Jaejin. We will now have, we'll now bring up Michael Fogel from Auburn University.
I'd like to thank the organizers for inviting me and for a very good first impression. This is my first time to this workshop. My colleague J.M. Wersinger has converted an experimental atomic physicist into doing CubeSat work, so it's surprising how many things actually map. So I want to talk to you a little bit today about our CubeSat mission called Terrestrial Rays Analysis and Detection, or TRIAD, funded by NSF. It's a joint project between Auburn University. Auburn is actually developing the bus for the CubeSat. And I'll tell you what, guys, I'm a pacer. Sorry, it's part of being a professor, I think. So Auburn University is building the bus of the CubeSat. The science PIs are actually at the University of Alabama in Huntsville. And we have some collaboration with Georgia Denofo at Goddard Space Flight Center, who's helping about the detector that I'll talk about. So what's the science of TRIAD? So TRIAD's mission is to look at terrestrial gamma ray flashes. And in particular, we want to make multi-point observation of terrestrial gamma ray flashes. I'll just use TGFs. And so what are TGFs first? So TGFs, if you have a thunderstorm, say in the tropics, which is where we're looking at, you have some form of electric field in a cloud, and let's say you have a lightning strike. You generate excess electrons, the electric field accelerates those electrons. If you can accelerate those electrons to significantly high enough energies, we say that that process can run away. What does that mean? It means there's not an atomic process that actually attenuates them from gaining further and further energy. And eventually those electrons will scatter on something and will create what's called Bremsstrahlung or breaking radiation in physics. And these can actually be high energy photons. And so in the gamma rays, even up into MeV range, that actually makes this if not the most, one of the most natural sources of high energy photons apart from nuclear processes. So the idea is to try to understand what's going on in these clouds. What's the models? What's the emission look like? Is it a wide profile of emission due to a lot of scattering? Is it a narrow beam? Are the beams tilted? Etc. These gamma ray pulses actually happen on very short timescales. So we're talking tens to hundreds of microseconds in time, and they can be very intense. And so the mission really is to make these multi-point observations, which no one has ever made, so that we can verify the models for the fields. And so a little bit of history for detecting TGFs. So a lot of these have been seen on larger satellite missions, specifically missions that have been designed for gamma ray astrophysics use. We have some detections back in the 90s on BATSI, and then some higher energies. And actually the folks we're working with at UAH in Huntsville are some of the scientists working on the gamma ray burst monitor, which is mounted on the Fermi Gamma Ray Space Telescope. They've now monitored thousands of these. So how is Triad unique? Triad is unique in terms of TGF measurements from the perspective of its multi-point. These guys have been wanting to do multi-point measurements for a long time. You can wait for 2 spacecraft that have the ability to detect to align, but I think there've been 3 or 4 of these in the past tens of years. And so the idea is to fly 2 spacecraft that can do this. Of course, you can't build large-scale spacecraft on the size of Fermi to do this. This is an exorbitant cost and would never fly. So here's an artist's representation of gamma ray emission, and it could be narrow, it could be widely distributed. There's also VLF lightning networks all over the Earth that can triangulate lightning generation. And it turns out that this TGF generation is coincidence mostly with lightning strikes. And so what the mission will do is fly 2 6Us in the same orbital plane in a tracking formation, where we can adjust the separation using differential drag. And we will measure and time tag detected gamma ray events in real time and correlate those to the lightning strike triangulation data. And then look for, is this a wide beam? Do I see coincidence measurements? Do I not? So this is just a quick snap of a worldwide lightning density map. I just went and grabbed any random 15 minutes worth of data. And so you can kind of see a trend in the equatorial regions. In the tropics, there's lots of thunderstorms. And so this is actually the region we want to focus on, because this is where you get really intense thunderstorms, you get a lot of TGF production. So on this map, I'm going to overlay some measurements that were already made by Fermi, and I'm going to give you an approximate 50-degree inclination orbit at about 500 kilometers for our Triad mission. And so you can see the region of interest where we want to be, South Atlantic anomaly. You might ask, well, why do we want to stray outside? It actually has to do with trading off. We would like to spend lots of time in the equatorial regions, but we need to calm. And it turns out our calm budget, or amount of time we need to spend in comms, we need to deviate from the tropics so that we can do that. You might ask, well, what about outside this region? This is actually the limits of the inclination of Fermi. There have been other spacecraft that have looked outside of this, and sure enough, the number of TGS falls off drastically. So we're really not going to target outside these regions. One of the things we are going to do is we're going to have live region of interest updating on the spacecraft. That'll be commanded. And so we can look at maps like this, weather forecasting, et cetera, and the science team is basically going to tell us, hey, I want you to look in that box next time you go over. And so we can live update those real-time regions of interest and take data. So here's an overview of one of the Triad CubeSats. It's a 6U CubeSat. You'll notice we're flying it in this dark configuration. we're not actually flying it for passive stabilization, although it does augment stabilization a little bit in the RAM direction. The idea is that we would have this face oriented to RAM. The bottom of the satellite would be nadir tracking. I'll talk a little bit more about why we're flying the DART in terms of being able to change the fin angles for station keeping. We have, well, I'll just point out a couple of things. We have an embedded Linux. We're actually using the BeagleBone Black system, and one of the reasons we're doing that is that comes married with the Globalstar comm system we're using. We're flying both full duplex comms. We're actually flying a new version of a radio that's coming from Globalstar. Andrew Santangelo from SciZone will talk about that later. So this is supposed to be in the range of 256 kilobits per orbit or per second. And when we're in this nominal 50-degree orbit, we get about 40% of the orbit coverage. We're also flying their simplex, which is basically just telemetry beacon. We can get about 90% of orbital coverage. This will probably just be used in the first few months, just for diagnostic purposes. This big gray box that's taking up a vast majority of a 6U is a science instrument. I'll talk more about that. We're building all the reaction units, which includes magnetorquers and reaction wheels in-house, sun sensors. This is the patch antenna for the Globalstar system. We're flying GPS. As I said, we're going to be able to change the angle of the panels on deployment. And one of the things I should point out is we have a very tight restraint on doing the time tagging for science. So as you remember, I said the TGFs can be very intense. So the gamma ray detector is probably going to see a couple thousand counts per second as background. And we can't actively distinguish what's a TGF and what's not. So we have to time tag everything. The problem is, since we're doing coincidence between two satellites and the ground lightning data, we have to time tag in some real time coordinate system, right? UTC or GPS or something like that. And we also have to be able to time tag to about 2 microseconds accuracy in real time. And during a burst, we may get up to about a megahertz, mega counts per second of real TGFs. And so we've got to time tag that at that rate. And we've actually worked out a solution where we can use the programmable real-time units. There's 2 programmable real-time units on the BeagleBone. You can program in assembly. It's basically a RISC processor, runs at 200 megahertz. And just recently, in the past couple of months, we've worked out a scheme where we can time tag a megahertz signal, random, almost continuously until we fill up the memory. So this is more than fast enough, and we can do it with half microsecond resolution. So how do we time that to actual time? And that's where the GPS comes in. We're actually going to use the mark event data loggers on the GPS, Novatel GPS that we're flying. So it's like clicking a stopwatch. We can click when it starts. Our time tagging system measures delta times to half microsecond accuracy, and then we're done. We can stop the stopwatch, and if we know the absolute and we know the deltas, we can figure out the timing. So here's the science payload. You can get a sense of the size here. So we're detecting gamma rays. So these are actually 4 individual bars. They're actually 5% lead-doped bars. So at the energies of in the tens of keV, if you guys know keV energies for photons, this is mostly a Compton scattering process. That means it's not photoelectric. You can't do very good spectroscopy with it, but you can say, yes, I saw one, I got one. And that's all we really want to do. We're going to do some very rudimentary pulse height analysis. I think 4 channels worth of pulse height analysis with a very simple comparator circuit, but in principle, we're more interested, did we get one or not? So we're going to have these huge plastic bars which take up a huge chunk of the space in the spacecraft. So how do you actually detect the light that they generate? So we're actually working with the guys at Goddard to develop silicon photomultiplier arrays that go at the ends of each of these bars. And so what you see here is a test prototype board of one of these arrays. And so these are 6 millimeter photomultipliers. You can think of these as avalanche photodiode arrays if you guys are familiar with those. This is 6, so it's 5 by 6. So there's 30 of these at the ends of each of these bars. So there's 240 of these little guys on every spacecraft. And Goddard's working with us because they're interested in TRL advancement for these arrays for various types of detectors. So this is kind of an overview of how we're running it. We have a science interface board that does pull type analysis. We also have to do temperature measuring and gain control because the gain of these detectors is temperature sensitive. This will feed into our basically flight computer, the PRU system that does the time tagging, sticks it in memory, and basically queues it for downlink. And we're using the GPS as kind of our start-stop, plus we're using it to check our position. As I said, we're using the Globalstar radios for data. This is a map of basically Globalstar's coverage. In case some of you aren't familiar, Globalstar is 32 satellites at a much higher orbit than we'll be at if we're at 500. So we have our patch antenna zenith facing, and we have to keep that aligned to about 30 degrees or so. We actually don't have a high pointing requirement for the science. It's actually more important that we know the attitude, say to 5 degrees or so, than to control it. But we do have some constraints that work into comms for pointing, attitude control, and of course we have power production and thermal issues in the design for pointing control. So we're trying to keep it in plus minus 20 degrees of ram direction. So you can see the coverage, and you can see about how much coverage we get on each orbit. We hope this data rate actually works out. We're gonna generate probably somewhere on the order of a gigabit of science data per day. In principle, that should be able to download it in a couple hundred seconds of real contact, but of course we won't get that entirely. The nice thing is that this system basically works around the concept of synchronizing a database. And so as long as this database is synchronized, we can actually pass a region of interest, say in here, and as soon as it's done, it queues that file for downlink, and as soon as it gets connected, it's gonna start streaming data to the ground. It is kind of odd, though, to start thinking about your CubeSat being able to be charged roaming rates, though. It's fairly strange. So we're developing a lot of the attitude determination and control systems in-house. I'll talk a little bit more about the student group at the end, but we're building reaction units to go in here. So we've made our own magnetorquers with built-in reaction wheels. You can kind of see, and actually that number, I think that's a 160, not a 180. Anyway, this is about 6 inches. This is a sun sensor that we're also building in-house. It's a pinhole design with a pin that's a position-sensitive Hamamatsu detector. You basically use a laser-drilled hole. It's about 80 micrometers, and you can calculate based on the current to the individual corners, what the angle is, et cetera. It's actually relatively simple to build. We have 4 of the sun sensors on the spacecraft. We have all 3 axes covered with reaction units. We're flying multiple magnetometers, rate gyros. And I pointed out the differential drag that we're going to use. So we're actually driving our external fins with motors so that we can change the angle dynamically. As I said, a lot of people use this orientation for passive stabilization, but at our orbit, it really only augments that. So why are we doing this? So we want to maintain the body of the spacecraft in its orientation so that we can take data even though we cause a separation. Because one of the things we want to do in the science is we want to measure these profiles or coincident detections in proportion to separation of the spacecraft on the scale of, say, hundreds of kilometers. And so the way we're going to change the separation is basically just changing this profile of the satellite. And at this orbit, with this change in area, we can change the separation, say, 100 kilometer over tens of days. And that's fine for us. We're not in a hurry, and as long as we're sampling over the whole region and keeping the spacecraft oriented, it should be fine. So this is just a rough timeline. We're here, we just did a CDR 5 days ago. We're building engineering models. this summer, flight models looking for launch sometime in maybe 2019, and then 12 to 18 months on mission. And then the last thing I'll say is we are doing this all with undergraduate students. So our Auburn University Small Satellite Program is about 30 to 50 undergraduates per semester. And it's kind of amazing, actually, what undergraduates can do. Some of them are better than others, but but their ingenuity is actually quite good sometimes in building different ways and thinking about testing and developing all these systems. And so with that, I'll stop and see if there's any questions.
Thank you, Michael. If you have any questions, you can find him in about 15 minutes at the break. I'd now like to bring on Alyssa Randall and Tom Giornelli from the U.S. Naval Academy.
Hi everyone, I'm Midshipman First Class Alyssa Randall.
And I'm Midshipman First Class Thomas Giornelli.
We're from the United States Naval Academy, and today we'll be talking about the design, development, and operation of CubeSat-based HF SATCOM. So this is our team. We're composed of 10 first class, so senior midshipmen at the U.S. Naval Academy. 9 of us are aerospace engineering majors, and 1's a general engineering major.
So a quick overview of what we're going to be talking about today. We're going to justify why we're using HF on our radio, on our satellite, excuse me, and our mission and motivation behind our satellite, as well as our concept of operations and our actual design. So the main objective for HFSat is to provide an alternate means of SATCOM using a new band of HF. It's going to be a 1.5U CubeSat, and it will utilize amateur radio operators to test and determine the useful range of our communication capabilities. And if we are successful, there's an opportunity to design a fleet of similar CubeSats to provide worldwide coverage.
So why do we want to use HF? Our intended uplink is on 21.4 megahertz and downlink on 29.4 megahertz. These are already allocated for amateur satellite use. And we want to use these because HF, it uses non-tracking antennas. It has lower noise in those upper satellite bands, and it's got a much better data link budget for low power satellites. Additionally, there's a lot of DoD assets out there that don't have SATCOM capability right now, but they do have HF radios, and so we want to provide in the future potentially if this works out, a way for them to reach SATCOM.
Next slide, please.
We're good. Can we go back, please? Sorry.
Okay, so the motivation for HFSat is to improve satellite communications using HF radio relay and through utilization of amateur radio operators, as well as, just as importantly, to educate Naval Academy midshipmen on the life cycle of satellite development to prepare them to be space cadre in the fleet. Next slide, please. So the mission of HFSat is to explore the potential for widespread implementation and use of SATCOM for HF radio relay. And like we said before, pretty much every DoD asset has HF capabilities, but they don't have SATCOM capabilities. So this would give them, utilizing what they already have, SATCOM capabilities.
So the objectives of our mission is to test out this HF radio satellite communication capability, specifically in the CubeSat format. There was a satellite a long time ago that was a Russian satellite that successfully used these bands, but it hasn't been reachable for over a decade. We want to utilize amateur radio band operators who are experienced in HF to test this capability out. And we're also, again, we're all about educating midshipmen on how we get satellites up into space. So our solution is to build CubeSats with HF Satcom, and we want to use these because they're inexpensive, they're quick, they're easy to build. All right, so our concept of operations is that amateur band operators and potentially midshipmen who are amateur operators can use YP craft and their home systems to interact with the HF transponder on HF to see our range of operations. Our command and control is on VHF. So that's where there's the data link is, and there's also a APRS digipeater included on our communications board, but the HF transponder is designed to be voice only.
Next slide, please. So a quick overview of our satellite. It's going to be 2.2 kilograms, 1.5 U. It can generate 2.75 watts in the sunlight. Its attitude is going to be controlled through a gravity gradient stabilization system as well as magnetotorquers. And these are the frequencies we plan on using. And I'd like to point out that the VHF frequencies are going to be specifically for command and control data. And this is our design for the satellite, how we're going to stack our boards. Something to note is that this doesn't include our ballast boards. This actually gave us a little bit of problem last week, so we are in the process of redesigning our stack.
All right, this is an overview of our power system. We built this power system in-house, so we decided to go with direct energy transfer because of the simplicity and the fact that it's worked on previous Naval Academy satellites pretty well. So the unique features of our satellite with the HF mission is that we're going to utilize a half-wavelength dipole HF radio antenna, so that's going to be over 16 feet long. It's going to also utilize tip masses on the end for that gravity gradient stabilization. For the HF transponder, it's going to be linear inverting. So with our 21.4 megahertz going uplink and 29.4 megahertz downlink, the mixer is going to be at 50.8 megahertz. We're going to use a 30 kilohertz passband, which should provide about 10 users the capability to use the satellite simultaneously. We're going with a linear inverting transponder in order to reduce the amount of Doppler shift that users have to deal with while they're trying to interact with the satellite.
So our power system is going to be utilizing solar panels we made in-house. There's going to be 6 solar panels, side panels, and in total they will generate 2.75 watts in the sunlight. They also have magnetic coils built into the panels that can act as magnetotorquers. Our battery board consists of 5 NiCad cells. We chose NiCad because they're proven space hardware, they're cheaper than lithium-ion cells, and their max capacity is 286 milliamp hours at 7 volts.
So our VHF communications board for that command and control element is for telemetry as well, and provides that if the HF mission does not end up working out, it will still be able to perform as an APRS digipeater. It uses a modified TinyTrack 4 communications controller, which is called the SATT4. This board is relatively inexpensive and could also be adapted by other programs who don't have really big budgets for their CubeSats. Our transmit and our receive is on 145.8 megahertz.
So this is our ADCS and CNDH board. Our attitude is going to be controlled by a gravity gradient stabilization system. We're going to be putting a 20-gram tip mass on the end of our 2.5-meter HF radio antenna. We also have magnetometers, which act as our control for the solar panel magneto-torquers. And I'd like to point out that the CNDH is done by that blue Arduino on the board. And this is also where our current sensors are located.
So the design and development of our antenna, we're using nitinol wire. So the VHF antenna is going to be wound up in those holes in the red thing that's on top of the PCB. And then the orange flaps are actually gates that will be closed and then surrounded by a nylon cord. That nylon cord, when the satellite's deployed, will then be severed by running the current through a burn resistor to release the antennas, and then with that nitinol wire, it'll snap right back into shape. The HF antenna, because it's longer, will be wound around the entire satellite, and then again, will be held together with a nylon cord. The burn resistor will let that go, and it will extend.
So just sum up, successfully completing our mission objectives means testing the HF radio for satellite communication capabilities, utilizing those amateur radio operators, and again, educating midshipmen on how to actually build a satellite.
At this point, we've done a successful test of our communications board. We've simulated and designed our gravity gradient, and we are planning for a launch somewhere in mid-2018.
Thank you for your attention. Are there any questions at this time?
Lots of questions. Oh, boy.
You in the back?
The Naval Academy has successfully used them in the past, but I'm unfamiliar with what those particular sources of error are, so I can't give you like a specific solution.
And we have tested our system in the lab 2 times at this point.
I think so. The intent is voice only. Does that answer your question? We had like, I think it was about 100 batteries that we went through and tested and tried to get them as close as possible. I can't remember, I'm sorry.
We have looked into that. Our conclusion has been we don't think it will. The tension from the gravity gradient from the gravity gradient effect should be pulling that taut, so it shouldn't be waggling around. Tip mass? 20 grams. 20. Grams.
We hadn't gotten that far on the constellation design. That was more of a concept of what could happen afterward, but that probably wouldn't be something that the Naval Academy would actually do. We're not entirely sure with this, and that's part of the reason we want to test it out. And that was also part of the reason we were going with the higher end of the HF frequency, because it would bounce off the ionosphere less.
Thank you, Tom and Alyssa. That's all the time we have right now. So we'll now take a short break for 30 minutes, and presentations will resume at 3:30.
Mike, you gonna take my picture? What's that? No, later. When more people are here, hopefully. Can you hear me okay?
Hello, everyone. So hope everyone had a good break. We will now continue our presentations with Scott Scher from NASA Goddard Space Flight Center.
Good afternoon. My name is Scott Scher. I'm from NASA's Goddard Space Flight Center, Wallops Flight Facility. I am the Near Earth Network Wallops Manager, and I'll be talking to you about the Near Earth Network support of lunar and L1, L2 CubeSats. Here's a picture of the Argo Moon CubeSat. It's an Italian space agency CubeSat, and it's important because it's going to take a picture of the deployment of the other 12 CubeSats that will be on the Exploration Mission 1. Every space launch system that NASA launches will have at least 13 CubeSats, so that's why this is an important topic. I hope that, that you could learn something that may apply to your future communication system, and I'd like you to contact me to let us know how the Near Earth Network, or NEN, could evolve better to meet the needs of the CubeSat community. So I'm going to give you a short overview of the Near Earth Network, or NEN, show you some upcoming CubeSat missions, talk about NEN L1, L2 CubeSat support, and then the evolution of NEN, and then a conclusion. The Near Earth Network, the scope of the Near Earth Network is from launch all the way out to low Earth orbit, a couple hundred miles from Earth, all the way out to GEO, which is 20,000 miles from Earth, all the way out to the Moon, which is 250,000 miles from Earth, all the way out to L1, L2, which is about 1 million miles from Earth. And so all of that in NASA speak is called the Near Earth Network. And part of my job for the Near Earth Network is to help it evolve to meet new missions such as CubeSats. I've been involved with CubeSats for about 10 years. I was involved with the very first launch of a CubeSat in the United States from Wallops in December 2006 on a Minotaur out of Wallops. It was an Ames mission. And I supported the National Science Foundation CubeSat program. And now I'm with the Near Earth Network. Here is a picture of about the 20 stations around the world that the Near Earth Network, that comprise the Near Earth Network. Some of them have multiple antennas. What drives multiple antennas at a site is not really how busy or how loaded an antenna is. It's more what is the probability of multiple NASA missions flying over that location and needing simultaneous support. And that's what drives the number of antennas that we have. Many of our missions are polar, some are equatorial, and some are mid-latitude. Many are S and X band antennas. We have one antenna in White Sands, which is Ka band, S band. We support about 150 contacts a day, roughly about 15 minutes of contact. For the Lunar Reconnaissance Orbiter, we're supporting about 4 hours of contact a day, about 16, the equivalent of 16 15-minute contacts out of White Sands. And so that's about 10% of the supports that we're providing. Half our supports are on NASA-owned stations, and half the Near Earth Network brokers from commercial stations. This is a chart of the frequencies that the Near Earth Network supports, and you'll see there's no UHF. There is a dish at Wallops that supports UHF, but it's outside NASA's space communication and navigation. The reason that UHF is not supported by SCAN or NASA's comm network is because for download, it's not a primary frequency. So the missions that are at Wallops that are downloading 3 megabits per second on an 18-meter dish, UHF, they're they're subject to interference. And that actually happened. There was a mission that launched in 2009, was flying for about a couple of years, 2 1.5U CubeSats. They tried to use an 18-meter dish out in California, and they ran into interference issues. They were using the Wallops dish. They ran into interference issues. We had an engineer go out to Wallops, find an area of no interference. Then they commanded their CubeSats to switch to that clean area with no interference. Everything was working great for a while. And then a local television station just decided to interfere. And then there's nothing that the FCC or the NTIA or NASA could do when that interference happens. You can't filter out a local interferer competing against 1 or 2 watts coming from hundreds of miles in space, going into an 18-meter dish. Just no easy way to do that. So we had to pay that television station to change their frequency. But some of these other frequencies, like there's S-band, X-band, as you go up in frequency, there's more bandwidth available. And it's kind of interesting that X-band, the bandwidth that you get depends on the science that you're flying. And so if you're an Earth science mission, you can get hundreds of megahertz of bandwidth, which could translate to a data rate of hundreds of megabits per second. But if you're some other science mission, then the bandwidth is only 50 megahertz. And so, 50 megahertz, but only 10 megahertz per transmitter. And so other sciences don't get to use the full X-band spectrum. But when it comes to Ka band, there's a very large spectrum available for all sciences. Here's a list of missions that may fly on the Near Earth network. Some are in the discussion stage, some are firmed up. CPOD is a Space Technology Mission Directorate mission. It may launch this year, may launch next year. SOCON is an Earth science mission. If you look at the Clyde Space booth, they have a little mention of SOCON. It's also known as Seahawk. That may be the very first CubeSat to fly on the Space Communication and Navigation Networks. When it comes to lunar and L1, L2, there's quite a few challenges. LEO, low Earth orbit, is really easy compared to lunar and L1, L2 distances. If you're 250 miles from Earth and you take that same communication system and you want the same data rate with the same ground station, the same comm system from the moon, 1,000 times the distance away, you're going from 250 miles to 250,000 miles. The efficiency of communication is 1 over distance squared. And so you need 1,000,000 times the power, or 60 dB, to get that same data rate with the same comm system with the same ground station. And so how do you get around that? Well, there's more efficient coatings, which require less energy per bit. There's better antennas that you could use on your CubeSat. There's larger dishes on the ground that could help increase gain. And then you have to sacrifice typically going to a lower data rate than you would get from low Earth orbit. And then another challenge is navigation. For low Earth orbit, CubeSats have the benefit of getting 2-line elements from NORAD. And so they can find out where they are. But when you go out to the moon, NORAD does not have radars which are tracking CubeSats out to the moon, and so you're not going to get your 2-line elements. In low Earth orbit, CubeSats could use GPS. Going out to moon, L1, L2, they're above GPS. And so these CubeSats that go out to lunar and L1, L2 distances, they need other ways of navigation, such as using the auto track angles from our dishes, using Doppler, using ranging. And then there's radiation. These, as you go out to those distances, the CubeSats have to survive a harsher radiation environment. So all of this makes it harder to find a radio and a comm system for CubeSats that are going out to those kinds of distances. If your CubeSat happens to get lost around the moon, it turns out that a smaller aperture dish, like an 11 meter compared to an 18 or 34 meter dish, can provide a wider beam width. And so to try and find your CubeSat, which is somewhere around the moon, you could paint the moon with a paintbrush rather than painting it with a pencil beam from a larger dish. And so that's one advantage of using a small dish like an 11 meter. We had a case when this CubeSat, which was looking for TGFs, we had a prior speaker talk about TGFs, and it was using our 18 meter dish at Wallops UHF, and it was released in a swarm of about 40 other CubeSats, and we attempted to find it from November through December, through Thanksgiving, through Christmas. Every day we're trying different two-line elements, saying hello, are you there, waiting for the CubeSat to respond. Any CubeSat, or hopefully that's the one, and nothing back. It didn't help that 10 of those other 40 CubeSats were also not responding, so we had to keep trying different two-line elements. And then finally, in January, a CubeSat answered after months of trying every day. And so in retrospect, it would have helped to have a smaller aperture dish with a wide beam that could go ask the host swarm at the same time, are you the CubeSat? Are you there? Are you alive? If you look at data rates, many of the CubeSats are using an Iris radio on the Space Launch System with EM1 that will launch in 2018 or 2019. And the Iris radio has discrete data rates that are factors of 2. It could be 32 kilobits per second, 64 kilobits per second, 128, 256. And the 11 meter at Wallops can get 32 kilobits per second out to the moon with a representative lunar mission using the Iris radio. And then 13 meter system from Hawaii and Australia can get 64 kilobits per second out to the moon. We looked at the Lunar Ice Cube mission. Is Ben Malfors here? Okay, there he is. So we've been working with Ben, and because we thought it'd be good to learn how the Near Earth Network could support a mission such as Lunar Ice Cube, and we appreciate Ben's time working with us. And so if you have any questions about Lunar Ice Cube, you can ask Ben. But we took a look at the different phases of the mission. There's the deployment phase where it's about 35,000 kilometers from Earth, and then it goes through a number of maneuvers, and then there's other phases. But that deployment phase, when it first gets released, Ben calls that the 12 hours of terror. As we analyze it further, it may be 48 hours of terror, because what's going on over those first 4 days is it comes out of the Space Launch System, it's spinning, has to stabilize, and then it does some maneuvers, and then it drifts for a while, and then it does other maneuvers. And then the Lunar Ice Cube is kind of unique, because when it has, when it's doing a maneuver, which could take a couple of hours, it has its own limitation that it cannot communicate. So it's not due to coverage, it's due to, is that power, Ben? Due to power constraints on the Lunar Ice Cube. And so they would really like to be able to assure that when they come out of a maneuver, that there's a dish available to command it, get Doppler, get ranging, and get data back. This is a video. There it goes. And so this is when it first deploys from the SLS. And it's showing that Wallops has coverage, then Hawaii kicks in. And those are the data rates possible because it's still pretty close to the Earth. You can get pretty high data rates. And then there's that period of the first maneuver. And that takes about a couple hours. And then afterwards, Hawaii and Dongara kick in. And then while we have Hawaii and Dongara coverage, there's only one Deep Space Network dish available to communicate with that CubeSat, to get data, to do ranging. And since the Deep Space Network CubeSat, oh, am I at the end already? Oh, so I'll just quickly go to the end, but I just wanted to tell you that in this presentation, you'll see other radios, and we trade them off for power efficiency, and be happy to talk to you some more about what's going on with New Earth Network and support CubeSats. So thank you.
I'll take that as well. Thank you, Scott. We will now have Bob Hannell come up from NASA Ames Research Center.
Good afternoon. This is pretty impressive out here. This is quite different than the other venue. My name is Bob Hannell. I'm the project manager for the BioSentinel project. As you can kind of see, we're a deep space radiation biosensor mission. Essentially what we're doing is we're using yeast as a model organism. So essentially we can take a look and gauge radiation sensitivity, genetic radiation sensitivity. Let's go forward here. So our project objectives are back in, I guess, the beginning of fiscal year 14, so just right around, just after the last government shutdown. We got started on this project, and AES, Advanced Exploration Systems, funded us along with several other projects to look at flying a deep space mission on the SLS EM-1 launch. At that time, I think it was December 2017. Now we're looking at delivering to TIVAC here in San Luis Obispo as they're the payload integrator for our, they're providing the dispenser and also doing the payload integrations in April of 2018. And the current launch readiness date for SLS is September 30th, 2018. Our science was picked out to sort of fulfill the HEOE strategic knowledge gap of essentially radiation effects on biology. The three main components or objectives are all kind of, I think, pretty good challenges, so we were a bit ambitious, but we essentially had a deep space nanosat. So you've heard a lot about the low Earth orbits, but we're kind of going to the next level, not having magnetic fields or the ability to use GPS as we're going to go into a heliocentric orbit. So there's a different additional subsystems that you might see on other spacecraft we need to kind of add in. We're also developing a radiation biosensor, as we talked about, and also, I think it was mentioned also by our keynote speaker this morning, again, interfacing with a newly developed launch vehicle can always be interesting because they have margins, and as they're building, they keep those rather conservative, and then as time kind of goes over, they give up some of those margins and make it easier for you. But up front, there's a lot of things that are unknown, and you need to work through those things. And then we're collaborating with a couple other spacecrafts that you may hear about also that AES is funding, Near Earth Asteroid, which is managed out at Marshall, and Lunar Flashlight at JPL. So again, our BioSentinel concept is essentially we want to quantify the damage of space radiation environment. And so what you can kind of see here, let's see if this is a picture of our yeast, and this is our little friendly yeast astronaut here. essentially, we've got two kinds of radiations coming. We have the galactic cosmic rays, which are the heavier ions, and then we're also very much interested in the solar particle events. So when we get sunspots and whatnot, those types of things, so much more protons. So that's kind of your characterization of your deep space radiation that you see. It turns out that we're actually, given where we're launching, we're sort of in the bottom of the solar cycle. So we're not expecting to see any big solar particle events while we're actually flying. There's still opportunities to see solar particle events, but not the bigger ones. And again, we're trying to correlate this damage to the yeast, and then we have a silicon detector, LET spectrometer, linear energy transfer spectrometer. It's built by JSC Radworks. They're providing it. They're actually building another instrument that goes on the Orion crew vehicle for their radiation caution and warning system for the Orion crew vehicle. So we're using that same technology, simplified a little bit, because we'll talk about it a little bit later. Our data rate is limited as we go further and further away from the Earth. So we have a spectrometer that measures energy, and we have bins it up into 256 bins. And essentially what we do is we just count up over an hour and fill all the bins, and then we send that data back. And that's kind of a way we kind of do our data reduction. And then the way we have the yeast assay, we'll talk about the payload a little bit more. But essentially, because we're going on EM1, there's a long pre-launch phase. I'll show it to you in a second. So we'll be up to 6 months, and to survive that, we've had to go into desiccate the yeast, so it's got to be dry. And then when we get on orbit, we run a series of these microfluidic cards, and we can fill them up, put them in a wet, give them essentially nutrients, which is essentially sugar water, and allow them to grow. And then we can do a series of these measurements sort of on a monthly basis, and then see how the integrated radiation affects the biology. So anyway, here's a little bit of concept for the SLS. You can kind of see the, wrong tool. This is SLS, and so we're up in this area. The Orion crew vehicle's on the top, and so again, the Orion crew vehicle's up here. We're in the MPCV, which is multi-purpose crew vehicle, which is Orion Stage Adapter. It's always great to have an acronym built within an acronym. So we've got the MSA. In this MSA, there's a ring in here, and there's shelves here, and then the dispensers associated with this, and this is the blow-up of the dispenser. So we fit in here. I believe there's 17 slots, but they're only flying 13, and one for the sequencer, but essentially 13 other payloads, and then we essentially are individually doors open, and we're ejected out of the second stage after Orion has left on its way to the moon and kind of do a DRO type orbit. So the main point, though, is that we're on the second stage, and that second stage disposal is by doing a lunar flyby and then going into a heliocentric orbit as its disposal orbit. And so here we go. In terms of the launch, we have the launch, and then we have the Orion crew vehicle takes off and goes to the moon. And then after that, there's maneuvers to essentially get rid of all the propellants on the second stage, put it in a direction where we're sort of going in the we're pointed in the anti-velocity direction. And so then we're dispensed backwards as the second stage is going on its way to the moon. We do a lunar flyby and go into a heliocentric orbit. So that's where we'll go. And our science essentially just needs to get into deep space. We just need to get outside of the Van Allen belts. And so we said this is kind of the way the trajectory was going with the SLS. So we thought heliocentric orbit would be a good orbit for us. We've looked at other places and things like that. And so we hope eventually to use the biosensor in other environments as well. Here's a kind of picture of the spacecraft. This is a little bit old in the sense, I haven't been able to update this chart yet, but we've added 2 more panels. But the spacecraft bus components, spacecraft bus components are kind of laid out here pretty well. In general, we have 2 panels. You see a lot of, it's just interesting to see other CubeSats going on. So we'll have sort of the cross or the X of the panels with two other panels here. We're using the MMA panels that are folded on the sides and then pop open. Here is our, let me say, we have our telecom system. We're working with JPL. We're getting the iris transponder, I think was also mentioned in the talk just beforehand. Also the antennas, we have a medium gain antenna for transmitting, low gain antenna patch for receive. On the other side, we have a receive and a low gain and a transmit, both low gains on one side. So essentially what we do is we use a gimbaled array in this configuration, and then we point our arrays to the sun, and then we actually kind of use the gimbal so we can keep the power on, and then can point the medium gain antenna back to Earth when we do communications. Inside, we've tried to carve up as much volume as we could for the payload. So this is our payload box here. We have other components, essentially. We have a coal gas propulsion system that we use essentially just for momentum dumping. We really don't have enough volume, nor from our ConOps we thought we weren't trying to allocate a lot of delta V associated with that. And then we have our ADCS unit, which is exact by Blue Canyon, and there's battery packs top and bottom. We have CNDH boards, and also the iris stack is over here. Those are the main things. Now kind of moving on to the biosensor. So here we can kind of see an updated drawing, at least with the 4-panel arrays. You can see the medium gain antenna here. The payload, if you open up the payload, you can see that there's these little cards here. There's 18 of these cards, and the original concept was we had a goal of trying to go for 18 months, and essentially to run each one of these cards every month. Since then, we've been shortening our mission, trying to essentially use the same design, but essentially try to get more statistics by having more samples. But each one of these cards, there's over here, it's microfluidic card. That's kind of the rendering, and then we have the actual picture of a development unit. And then what I want to do is sort of peel off the outside of that card, and you can see we have a detector board and an LED board, and in the middle of it is the fluidic card. So each one of those 16 wells is where we put yeast. They're suspended, they put in there, they dry, and they're desiccated, and then after we launch and we want to do it, we put fluids into them. And then the way we take our measurement is over here. We have a metabolic dye that we put into the wells. We fill all the wells at the same time, and essentially we then warm up the cards and we let them grow. And what we're able to do with the metabolic dye is take a measurement. We have a couple of different LEDs for different colors, and through absorption, the metabolic dye goes from blue to pink to clear. And by measuring that color transition, we can kind of determine what the growth of the biology is. So again, sort of at a snapshot, over time, by doing a card by card by card, and we see radiation that integrates over the time, the last sample will have seen more radiation than the first sample, and so hopefully what we'll expect to see is essentially a slowing of growth, essentially associated with damage to the radiation, radiation damage to the yeast. So I was trying to get away with, we're starting to build stuff and trying to get away with getting some pictures in here, so I'm just sneaking some stuff that we've got in so far. Here's another rendering of a 9-card manifold, so that's half of the biosensor payload. We have 18 cards total. Underneath here is this is the 9-card manifold. This is kind of an increase in our technology in the sense we had a lot more tubing. We're trying to, in terms of routing the fluids, both the input fluids and the waste fluids, using a manifold associated with that. And we're able to kind of get these in here. And then we've got 9 cards here and a calibration cell. We have pumps, and then here's again sort of a engineering development unit that's kind of in that situation there. Kind of move a little faster. We have an LET spectrometer, and that's what we talked about in terms of measuring the radiation and binning the energies so that we can then turn around and correlate what we have. Some of the bus components we've got a couple of pictures of. This is actually a still picture of partly of the deployment of the trifold, and also this is a gimbaled solar array, so we have sort of plus and minus 300 plus or minus 180 degrees rotation. So, and then here's a picture of our propulsion system. Again, it's a cold gas system, and we're using it just for momentum control. And then down here we have our exact unit and our battery packs associated with that. We get to sort of a picture. This is a relatively new picture where we're doing a fit check. We have the propulsion system. We had that exact unit with the battery pack. We also have a sun sensor here, and then also on the PSC canister, we have a separation connector that we can do battery charging at the just before launch. And the one thing I wanted to sort of bring up, this is thermal models, is thermal is, the more power, it's great to get more power, get more solar arrays, but also thermal adds to it. And so we have differences. We're trying to create a refrigerator for the E-cells, and then we have a hot bus essentially with that. So I noticed some other talks here on thermal, so I think that becomes more of a thing to do that. So I'll wrap it up there. All right, thank you.
Thank you, Bob. If you have questions for Bob, you can find him outside. Now I'd like to introduce Pamela Clark from Jet Propulsion Laboratory. Also give her a warm welcome. It is her birthday.
Okay. Hi. Thank you for clapping. Yes, it's nice. It's really a treat to be able to give a talk on something I love on my birthday. So, and today I'd like to talk about the Lunar Ice Cube mission. Actually, mostly the emphasis will be on the instrument and the kind of science that the instrument can do. But I will talk in general about the spacecraft and some of the challenges we face at all for the spacecraft development. This is a very good team, and I'm the only one at JPL, but the IRIS radio is being provided by JPL. And there's a very large group at Moorhead State. Moorhead basically is the PI, Ben Malfris, has been mentioned before, is at Moorhead. The ground communications system is at Moorhead, and of course the mission operations will be performed at Moorhead. Goddard is providing the payload. When we were selected, I was actually at Goddard. And we have a very good team at Goddard who are doing an instrument on a very slim budget. One of the things that we built into the instrument design from the beginning was a consideration of the thermal environment of the moon. So we're doing pretty well at meeting the thermal challenges for the instrument itself. And the flight dynamics team is also at Goddard. Of course, BUSEC is providing the propulsion system, which they're also providing for Luna H map. And the Vermont Technical College is providing the software for us. Could I have the next slide, please? This is really a technology demonstration mission, which was funded by NASA HUMD. But we do some very interesting science, of course, and one of the goals HUMD has is to fill the strategic knowledge gaps, as they call them, and those gaps really have to do with finding out where the water ice is on the moon, where the volatiles are on the moon, what the volatile cycles are, what the relationship is between latitude and time of day, basically illumination and thermal conditions, and how that affects what's there. And you know, the larger questions are, of course, to understand the physics and the dynamics of volatiles on the lunar surface, and that, of course, ultimately will tell us something about the whole space weathering process and the roles that volatiles play in that, and potentially also regolith formation and the origin of life. Could I have the next slide, please? Here are some of the technology demonstration goals, some of the technologies we're actually demonstrating. Primarily, this program was funded for those involved in SBIR studies. Moorhead and BUSEC were involved in a study, and they were looking at demonstrating micropropulsion systems. In this case, it was the BUSEC BIT-3 ion propulsion system with iodine. And also to look at possibilities that they could fly payloads, very compact payloads that would provide some information on water. There's where the Birches comes in. The basically broadband IR, compact high-resolution exploration spectrometer is what the acronym means. In addition to that, we are looking at radiation-tolerant, basically using radiation-tolerant parts and otherwise COTS systems, and that information, we've been able to get information from the NASA Electronic Parts and Packaging Study at Goddard that all of the people involved in building the spacecraft have had. Of course, the innovative use of low energy trajectories, which Goddard flight dynamics folks have been involved with for a very long time. The use of Spark Ada-based robust software is also being pioneered by Lunar IceCube. Next slide, please. Could I have the next slide, please? I'm not even going to bother to try to use the clicker. Okay, I'm challenged enough with using some technologies that don't work very well. So this slide basically shows the yellow lines on this slide are the water-related features that are in the neighborhood of the 3-micron band. And there are a number of them. There are these features, including hydroxyl or OH, water ice, are also found in other places, but there are quite a few around 3 microns. And what the plot on the right shows is that up until now, when we've flown these spectrometers in orbit around the moon that are IR spectrometers, they basically cut off near the 3-micron band. And so one of our goals from the beginning was to thoroughly cover it. When you get beyond 3 microns, there are some challenges with thermal emission, but we figure we can get out to about 3.5 microns without really being clobbered, and we're modeling the thermal emission as in an attempt to remove it. And it's, of course, been demonstrated by a number of serendipitous, because they really didn't anticipate finding the presence of water on the moon after many years of thinking there wasn't any, that there is not only water on the moon, but it appears to be related to temperature and illumination, and it should potentially be detectable even at noon, basically, near the subsolar point, potentially detectable because of the abundance of water. Could I have the next slide, please? This is a picture of the Birch's instrument. It is extremely compact. Think of an infrared spectrometer, which includes all of the electronics and the cryocooler in just over 1.5 U and just about 3 kilograms. It's really, really tiny. It's hard to imagine something that tiny with all those components, but so what we basically have is the optics box here, very simple optics, aluminum-based, 2 off-axis reflecting mirrors. We basically have an adjustable field stop, and we've got a detector system that's based on the H1RG, Teledyne H1RG, which is Mercad telluride detector. And that this is the electronics and microcryocooler assembly. Now compare this to this comes from a family of instruments developed by Dennis Reuter. The latest one is flying on OSIRIS-REx, it's called OVIRS. And we're comparing it here to Ralph, which flew on New Horizons. And as you can tell from the chart, we're considerably smaller in mass and volume. And the reason that we use more power is because we have a microcryocooler. Where New Horizons went, they didn't need a microcryocooler because it was very cold. But we need to keep the optics box about something like 210 K, which we do with a separate radiator. And the detector has to be at about 115 K or below, and we do that with a microcryocooler. And it is an AIM microcryocooler. Could I have the next slide, please? So we originally were flying a Rycor, and the problem with the Rycor cryocooler is that although it's very inexpensive, the electronics were so soft, basically, that we wouldn't have survived going to deep space at all. So we managed to leverage some resources and get the AIM microcryocooler, which advantageously also has a very compact controller. So that's why we were able to stay within a very small envelope for volume. And some of the other things, that is the H1RG detector and ROIC assembly. This is an illustration of the adjustable field stop, which can change the size of the window by a factor of 10. And so, that's the idea behind that was to adjust to keep the footprint on the surface the same regardless of altitude. And we go from about 100 kilometers at the subsolar, at the periapsis, equatorial periapsis, to about 1,000 kilometers at the terminator. So technically, we can adjust the field of view to be something on the order of 10 kilometers for the footprint. And that's the linear variable filter. That's basically how we do the wavelength separation. And we're really looking at a point spectrometer here. That's driven largely by bandwidth limitations that we have. So we're looking at point measurements essentially for that 10-kilometer footprint as opposed to an image. That somewhat alleviates any issues we might potentially have with pointing, because we're looking at a fairly large footprint when you compare it to an imager. Could I have the next slide, please? And this is a picture of the spacecraft itself. Solar panels. We have the BUSEC propulsion system down here. This is the Birch's spectrometer and the associated electronics and cryocooler assembly, a battery module, and over here, basically, we have the ADAC system over here provided by Blue Canyon Technology, additional support of UHF communication system, Beacon, command and data handling, which is Proton 400K Lite, which many of you are probably familiar with, and the X-band patch antennas, and the X-band transponder, Iris-2, basically, that's what we're using. Could I have the next slide, please? And these are basically models of the trajectory. So on the left-hand side, top corner, you can see that's basically a model of one of the possible low-energy trajectories. It'll take us about on the order of 8 or 9 months on that trajectory, with several relatively long burns along the trajectory to get into lunar capture. We're basically positioning ourselves with a minimal delta V to get into lunar capture in a way that minimizes the delta V we will need to get into the science orbit, which, as I said, is an equatorial periapsis, highly elliptical orbit. And it basically has a 7-hour period, and for 40 minutes out of that period we'll be in the over the illuminated hemisphere and taking data. On the right-hand side, you can see that the slide indicates this is basically our science orbit, so we will have a repeating pattern to go back over essentially the same terrain at a different time of day, basically once a month, so once a lunar cycle. And so we hope to be able to do that for 5 or 6 times, meaning that our mission will last about 6 months. And once we get into lunar capture, it'll take us something like 3 months with periapsis lowering to get into the final science orbit. So that's about a year to the science orbit after deployment from EM1, and then 6 months in orbit. Of all of the EM1 missions, I think we probably have the most operationally complex mission and the longest duration. Could I have the next slide, please? What we're basically doing is along a trajectory with these 10-kilometer footprints, integrating about every half second, so we've got a lot of overlapping coverage along the footprint. And this is good if in some cases, we're going to have to deal with the fact that since we're going from equator to polar, we're going to have some places where we could potentially saturate the detector, and other places where a signal will be relatively small as we approach the terminator. So because we have an adjustable field stop that can change its size by an order of magnitude, and we can also change the integration period, if we need to, we can use both of those things to allow ourselves to get sufficient signal. Could I have the next slide, please? Some of the challenges that we face. Well, thermal design, I think, for everyone who's flying the first time in deep space, not to mention people in orbit in many cases, is a real challenge. We're doing a 6U with components, as everyone in this room knows, that are about twice the density of a normal spacecraft. And that means that it's harder to remove heat. And then we're in a very difficult environment. Lunar orbit, although it's not as bad as lunar surface, is still a place where we have extreme heat and extreme cold. A lot of emission coming from the lunar surface when you're over the illuminated hemisphere. So we still have some real challenges for the whole spacecraft in terms of keeping the operational environment within the spacecraft within the normal limits for electronics. We also need, although we really have very limited margin in terms of mass at this point, we discover that we really do need to provide a cover for the instrument, so that that sun doesn't go into the instrument, because it could do a lot of damage. So that still has to be dealt with. Yeah, there are some challenges for flying on a human-rated vehicle, which is basically what SLS is. That's what EM1 is using. And there's still some issues with completely resolving the extremely high shock and vibration and very large range of temperatures that these folks normally have to deal with. For tiny little CubeSats with very limited mass and volume, those things are quite challenging. We think that the shock and vibration issue is solved, but we still have to negotiate for the temperature range. because when we are deployed, when Orion is deployed, which is ostensibly the purpose of VM1, to deploy the Orion capsule into an Apollo 8-like orbit, they don't want to rotate the second stage, which is where the ring of CubeSats is, which means one side will fry and one side will freeze. So we can't have it that way and have any CubeSat survive. The radiation issue is being dealt with because, as I said, we have access through Goddard to the NASA electronic parts and packaging information on the performance of various electronics components. The IRIS-2 radio has capabilities that allow us to get much improved bandwidth than we initially assumed when we actually proposed to do this mission. And data management is a major challenge because we are required to deliver data to the planetary data system. Normally that costs missions millions of dollars, and that's basically our entire budget. So we are basically leveraging everything we can to be able to deliver at least the experiment data records, and then leveraging other collegial relationships to do a lot of the processing. That wasn't something that we had as a requirement when we proposed to do the mission, but it was levied on us at PDR. So we're attempting to deal with that. Next slide, I think that's the last one. And am I done? Am I at 15? Okay. So yeah, we are, in fact, despite the fact this is a tech demo mission, we can do some very interesting science. This is a good example of basically taking a standardized platform approach with lots of COTS parts and creating very creatively a tailored solution to be able to meet science requirements. That's it. Thank you.
Thank you, Pamela. I'd now like to introduce Ross Bannatyne from Virago Technologies.
Good afternoon. My name is Ross Bannatyne, and I'm representing Virago Technologies. Let me give you some background about our company. We are a privately held, fabless semiconductor company based out of Austin, Texas. And we've actually been going since 2004, although we changed our name from Silicon Space Technology to Virago Technologies late 2015. Up until that time, we had been focused mainly on Department of Defense research type projects. And since 2015, with the name change, we've really become more focused on commercializing our technology. Those projects gave us the opportunity to develop our technology, which we call HardCell, which is a way of hardening standard CMOS devices against the effects of radiation. We've licensed our technology to a number of leading semiconductor companies who have developed space-grade products with those. And we've also developed what I think of as a modest portfolio of SRAM and more recently microcontrollers. So what kind of components can we use in CubeSats? The first choice is COTS, and COTS, commercially available off-the-shelf products, are easy to get hold of. You go into DigiKey and you get the part the next day, and you can access the latest state-of-the-art products, and they're cheap, but they're risky because they weren't developed to fly in space. And you can upscreen those products. Now, I think of upscreening like an insurance policy. It can get expensive. The more you want to pay, the less risky your choice is. And then at the other end of the spectrum, you have rad-hard products. And these are developed to use in space. They are typically older products, maybe that have been around for a few years, and they're expensive, but they're not so risky. The hard-cell product that the hard cell-based products that Virago have developed were designed for use in space, and they're rad hard by the processing that we apply. And because we use CMOS, which is really the industry standard driver for semiconductors, we're able to produce these hardened products at a more competitive price, because we can access any CMOS fab using any CMOS design rules. We've created some parts in different technology geometry nodes, and it's not a boutique type of process which is sometimes used in order to harden semiconductors. So let me tell you about our hard cell process. This here is a side view of a CMOS device, complementary metal oxide semiconductor, so-called because you have a PMOS device and an NMOS device, and that pair of devices is a good choice for optimizing performance and power consumption, and it's easy to manufacture. And this is what a CMOS device looks like. Those are 2 transistors. Now, when you manufacture a CMOS wafer, you get an unwanted byproduct that is a result of the processing and the CMOS architecture. And this byproduct is manifested as bipolar transistors underneath the active area of the CMOS devices. And you can see there's a structure that looks like a thyristor, and it acts like a thyristor. And typically, if you operate the device under a reasonable spec, under reasonable conditions below 125 degrees, and without being bombarded by high energy particles, it tends to behave itself. However, this structure can be triggered, and this is a condition that's very serious in CMOS technology known as latch-up. And this was the main issue that we had to address with developing the hard cell technology, was to prevent latch-up from occurring on these CMOS devices. So as you can see, as a particle strike, it leaves in its wake a bunch of electron hole pairs that ideally should recombine quickly, but if they don't, they can forward bias these bipolar parasitics, and when these become forward biased, you basically create a short from VDD to VSS. In most cases, you can reset the device in order to get out of latch-up. In some cases, the device will burn up. The way that we prevent latch-up is by putting in a series of implants, a horizontal and a vertical implant that we call a buried guard ring, and it creates a highly conductive area that is a path for unwanted stray charges to follow, rather than switching on the parasitics. So actually what it does is it reduces the RP well resistance, and it reduces the gain of the parasitic NPN. So that's possibly the most concerning failure mechanism due to radiation in CMOS devices, latch-up, because it can kill your part. Another condition that we should be concerned about is total ionizing dose. Less so in orbits like LEO, but what happens with TID is as you get the particle strikes and it creates the electron hole pairs, as I say, you want these things to recombine very quickly. Now, because of the nature of the biasing of these devices, what happens in the oxide areas is the electrons tend to flow out and leave a positive charge. So with TID, what happens is you get a buildup of positive charge in your oxide areas. And as you would imagine, that positive charge attracts electrons, and it creates a path between the N wells and the the N plus region in the NMOS transistor. So you've got this path of current will flow, and that's how you can see the onset of TID starting to occur as you'll get a leakage current. And eventually that leakage current will become significant. It'll bring down the transistor, the threshold voltage of a transistor, and it doesn't switch on. And that's how TID eventually will destroy a part, just the accumulation of that positive charge in the oxide areas. The hard cell technology, there is some IP associated with it that we dial in the TID to a level of 300K rad psi is how we specify our devices. What a fantastic venue, eh? Okay. Now, there's some other conditions that we need to be concerned about. We've looked at latch up, we've looked at TID, and there's also radiation strikes that can cause single event upsets. So in this case, it's not the process part of it, it's not the hard cell processing that we use to protect against SEUs. For memory, we've added EDAC error detection and correction system. And the way that works is as the CPU pulls, fetches a 32-bit word, the EDAC inspects the word on a byte level, so it has a 5-bit syndrome in the Hamming code that's used, and it can detect 2 bits and correct 1 bit per byte. So as the CPU fetches a 32-bit word, you can detect 8 and correct 4. Now, if you get 2 errors within a single byte, that's a problem because that's an uncorrectable error. So we seek to avoid that situation, and there's a couple of things we do in order to protect against that. One is that logically adjacent bits, when they're laid out in the memory, are not physically adjacent. And the other thing we do is we add what's known as a scrub engine. And a scrub engine operates independently of the EDAC and the CPU. And in the background, it sequentially steps through memory looking for flipped bits. And as it finds the flipped bits, it can correct it. So you can actually control the speed, the number of scrubs that you're doing. So if you're in an environment that you're detecting that your EDAC is correcting more bits, you can set your scrub engine to a higher speed in order to prevent the accumulation of errors. And another thing you've got to be concerned about is single event upsets in logic areas. And in order to address that in these devices, we replace latches with dual interlocked cell structures, which are basically 3 voting mechanisms to replace any single latches and to apply TMR to the internal registers. There's some other features like glitch filters that are used in the clock so that if there is a glitch, it doesn't propagate through the circuit. This is a block diagram of a microcontroller that we did last year. It's based on an ARM Cortex M0, runs at 50 megahertz. It has a typical set of microcontroller peripherals on board, such as UARTs and SPIs and I2Cs, and timer channels, GPIO and such like. As I mentioned, we made a big effort to start commercializing this technology and to actually sell some chips back at the end of 2015. So the explosion of CubeSat activity has been very favorable for us. I see these devices being used in 2 common configurations in CubeSats. The first one is as a standalone onboard controller chip. And I realized that in every case, 50 megahertz M0 doesn't have enough bandwidth to perform every type of OBC system. And the other configuration that I see is where the chip isn't powerful enough to be an OBC, and there's a much more powerful chip in the system. In this case, on the left-hand side, there is a Vertex 5 FPGA. This particular system is an X-ray event detector, and it uses actually a non-rad hard version of the Vertex 5 and uses the microcontroller as a watchdog or a safety monitor to load up the memory and monitor the heartbeat of the device. So these are really the two types of configurations I see these devices being used. We chose the ARM Cortex M0 for a number of reasons. There's a lot of software available for it. It's relatively easy to program. Inherently, it's low power consumption. We've done a lot of testing and zeroed in on the areas of the device that consume the most power. And there's an application note available that explains how you can really optimize the power consumption further on the device. Some of the things that we did was to put in clock gating mechanisms so that any peripherals that are not being used can effectively be switched off so they don't consume any power. But the Cortex M0 is really pretty favorable for power consumption. One last slide. We created a software development kit. We wanted to keep the cost of the kit down low, so when we originally done the chip, we made it available in ceramic packages and as die. We didn't anticipate that there would be a big demand for plastic packages. However, we did package a bunch of chips in plastic in order to put on the software development kit just to keep the cost down. And we were really quite surprised at the number of folks that came back to us and said, hey, I want to buy the plastic part because it's fine, I'm willing to fly that. So we recently added a plastic version of the device available. Thank you for your attention.
Thank you, Ross. We'll now bring on Catherine Conway from Space Micro.
Good afternoon. Today I'd like to share with you all some information on key features about Space Micro's CubeSat single board computer. The design combines industrial and space-grade parts together. Sorry. The design philosophy behind the CubeSat space processor is to take some extensively tested commercial components and surround them with radiation-hardened components. Through doing this, you get really the best of both worlds in performance and in reliability. We surround the commercial components with the radiation-hardened devices To overview the CubeSat space processor, it is a single board computer where it's the Xilinx Think 7020 is really the brain of the operations. It has dual ARM cores and reconfigurable FPGA fabric. DDR3 memory is also present on the design, as well as non-volatile NAND flash memory. These are really the three commercial components that are on this design. All of the other devices on this single board computer are radiation hardened, space qualified devices, such as the power management and watchdog devices. There's extensive software options available in open source fashion. Additionally, the CSP currently has heritage. It's flying on the International Space Station, and it's selected for an additional 5 missions. Next slide, please. Here are some of the key attributes of the CSP. You will find more details about this and all of the specifications on our website. So feel free to come by our booth and ask us more questions. We're on the 2nd floor. Otherwise, the data sheet is available online. To aid in development for this single board computer, we've provided a kit that has, for both the engineering and flight models, I would say a board support package as well as physical boards to support it. Comes with an evaluation board, which provides different interfaces, or provides some modes for common interfaces to be used. As well as we provide a USB to UART breakout board. There is access to a ton of open source software for this device itself, as well as the firmware repository. The CSP can support various operating systems, such as the ones shown above here. There are a large number of interfaces that are available on the CSP. However, 2 of them, being Ethernet and CAN, do need an external PHY. Like I said, there are multiple open source software applications available, as well as third-party IP. And as more missions are using this CSP, more of that software is uploaded to the open source regions where everyone can have that available to them. Additionally, NASA's Core Flight Executive and Core Flight System can be run on the CSP. Because the CSP has a dense, high-speed backplane connector, it's convenient for expanding the design to incorporate other printed circuit boards and their custom functions. For example, multiple CSPs have been tied together to create a supercomputer using this backplane with SpaceWire protocol for parallel processing purposes. Additionally, we've developed a modem board that, as the CSP, can really be used as a payload processor. SpaceMicro has also designed this modem expansion card that works with the CSP to create a software-defined radio. You can see here the block diagram for the modem board shown. The CSP with the modem expansion card is being used currently in a design for a transceiver in a CubeSat form factor that is manifested to fly in 2018. So what we've done is SpaceMicro has taken this product and licensed it from the University of Florida and the Schreck Centers. The Schreck Center and the University of Florida students have really done a fantastic job at designing, prototyping, and maturing the CSP itself. All that's left for us to do for SpaceMicro really is to productize it. And how do we do something like that when you have a student designed, a fantastic student design, but we need to apply the standard industry practices to it. So we do this in 2 ways. First, we apply the industry standard design practices, then we go into the manufacturing. So First step in applying the industry standard design practices is to ensure you have an appropriate configuration management system in place, as well as the documentation. Additionally, the relevant design analyses are performed, such as structural, thermal, mechanical analysis, as well as radiation analysis for total dose and various single event effects. As part of the design practice, the parts, materials, and process selection, we ensure that the parts selected do not have pure tin and that there are no counterfeit parts purchased or in the design. The second part of being able to productize the CSP involves applying the industry standard manufacturing processes. So this starts with the parts procurement, being that the appropriate quality clauses from that contract need to be flowed down on the purchase orders, and ensuring that you're purchasing from authorized distributors. It also involves the sub-tier management and acceptance testing for the manufacturing and test portion, as well as creating the documentation for the end item data package and certificate of conformance. We have a mission assurance group at Space Micro, and we are a ISO 9001 certified house. We abide by our own internal standard operating procedures, as well as workmanship standards that are typically that you would find in the aerospace industry. Discussing the quality and supply chain management, for the mission assurance manager's role in all of this is to ensure that the parts purchased are from the appropriate places so that we don't end up with the counterfeit parts issues, and that the appropriate quality clauses are added on. Additionally, the mission assurance manager is also responsible for providing the source inspection at the printed circuit board assembly house, as well as the staking and conformal coating vendor for workmanship verification. In addition, they also oversee all of our internal processes to make sure we are complying with all of the requirements from the customer. Our quality assurance group performs the appropriate inspections for workmanship requirements. These include the IPC standards, J standards, NASA standards, etc. Additionally, they provide the oversight for the facilities compliance to make sure that we have the appropriate ESD safeguarding in place, our equipment is calibrated, and we have the appropriate cleanliness levels in the clean rooms as well as the engineering labs. Another role of the quality department is for the manufacturing documentation to ensure that all of the travelers are signed off, all of the steps are followed properly, and that the end item data package is put together with the certificate of conformance. The point of being able to license this design from the university, it's been a successful example of taking something that the academic world has designed and being able to turn it into something that industry can manufacture, and that we can sell both the engineering and flight units in a way that our customers, both commercial and government, feel comfortable with the documentation as well as the product itself. That's all. Thank you. Do you have any questions? Yeah. It's the Zinc 7020. I'd have to look that up for you. But if you come by our booth later, I'll check up all the data sheet specs. Anything else? Okay, thank you.
Thank you, Catherine. We'd now like to bring Miguel Vasquez on from DHV Technology.
Thank you. Forward. Okay. Backwards. Okay. Hello. Good afternoon, everyone. In this presentation, we are going to present the development of the solar panel for TRISA mission. We are going to present quickly our company. We are going to comment the TRISA mission, and we are going to comment the design of solar panel, the test plant, and the simulation, and finally the conclusions. DHV Technology is a company focused on solar panels. We design and manufacture solar panels for CubeSat and small satellites. The company was founded in 2013. In these three years, we developed more than 20 projects in several architecture. We are based in Spain, in Malaga, and we have around 15 people, and we developed more than 330,000 euros of turnover last year, and we plan to develop more than 850,000 euros of turnover this year. The company was funded from 3 people, 2 PhD and 1 engineer and MBA with a long experience in international business and product development. We have 350 square meters of facilities with clean rooms, with 300 square meters of clean rooms to develop all the integration of solar panels and develop tests and so on. We have several equipment, furnace for thermal process, welding equipment for welding process, chemical lines, and sun simulator for electrical test. Our products are basically based on CubeSat, and we could develop a PCB solar panels based on PCB substrate for CubeSat, Pocket Q, and this type of architecture, and we could develop solar panels manufactured on honeycomb aluminum substrate for small satellites in general. Our first project on flight was on 2014. It was a Unisat 6. It was launched from Yasny, from Russia, in June 2014. It's a satellite developed by Gauss. It's an Italian company. Okay. After that, we developed more than 20 projects in 1U, 2U, 3U, and the small satellites. Okay. Talking about the TRISA mission, I like to comment the TRISA mission is an educational 3U CubeSat. It's led by Maribor University in Slovenia. It's a mission led by onboard data handling team. It's a OBDH team. It's a research and development team founded in 2009 as part of the Maribor University, and involved in a European student moon orbiter. Is the ESMO. It was a mission from ESA. The main target of the project is to develop several subsystems: the DPS, the communication module, and the onboard computer. Okay, This hardware will be developed by the university, and this platform will be used in further projects. The plan of this mission is develop this platform to use in this mission and in other future missions. All the subsystem will be developed by students. The payload of this mission is a short wavelength infrared spectrum camera with three main objectives. Detect vegetation patterns, to analyze a natural disaster, and detect volcanic dust. This is the main target of this mission. All the data will be available for educational and research purpose. And finally, the CubeSat mission will be developed in sun synchronous orbit, roughly 700 kilometers of height. Okay, move to the design of solar panels. I like to comment the mission is through you, as I commented before, and will be considering on 5 solar panels. 3 solar panels will be body mounting, and 2 solar panels will be deployable 90 degrees. The deployable solar panels, solar panel number 2 and number 3, will be with solar cells in both sides. Okay. Solar cell will be from outer space, 30% efficiency. The solar panel will be include a bypass diode, the protection diode for this string, and 5 thermal sensor. Will be include photodiodes, 2 thermal night circuits, several hinges with a spring and with integrated end stop at 90 degrees. Has been designed for hinges as guide without springs, and there are several end stops to assure the fall position. Finally, there are 4 thermal knives with a tie down, several connectors for the EPS. All the header and cable are included. Now the mechanical design has been designed from Maribor University. It's a custom design, and we adapt the solar panels to this mechanical design, this structure. The solar panels are manufactured on PCB substrate, on polyimide, with 2-side copper layers. The solar panel, the PCB, will be manufactured under ESA standard. And the 2 solar panels will be with the capability to release at 90 degrees. The solar panel, the CubeSat is comparable. The solar panel design has been comparable with IC's launcher, so the easy pod. This is the mechanical design in folding position and in deployable position. Sorry. Talking about the mechanical design, has been really hard to accommodate all the solar cells, to place 7 solar cells and in a 3U, deployable. So we need to design hinges completely customized to try to use the space of the solar panels as much as possible. So the hinge has been has been designed in aluminum with hard anodized, and the tie down is composed of aluminum and PTFE part to assure the low friction of the wire after cutting. The tie holder is the part where the resistor are held to band the wire. Several stopper has been designed to assure the right position in a stall position and to assure the well working in vibration environment. These are located in the center of the panel. You can see in this picture the difficult to place all the 7 solar cells in this solar panel, the polar solar panel of the rest of the element. Talking about the electrical design, each solar panels provide a little bit more 8 watts. The total power installed is basically nearly 60 watts, but the maximum power could be possible to supply in one time is a little bit more than 25 watts when the sun is coming the 3 solar panels. The projects consist in the design part, and we are manufacturing the engineering models. With the engineering model, we developed several tests, several mechanical and several vibration tests, following the NASA GIF standard. Sinusoidal vibration, random vibration, shock loads, and finally resonance survey could be done. And thermal and vacuum test will be done with the engineering model to assure the thermal cycling and to assure the open of the deployment in low and in high temperature. Finally, the engineering model will be electrical test to assure the electrical capabilities after the test. About the sinusoidal vibration, you can see the frequent range and the levels of the qualifications. This is the random vibration. We'll plan to develop a 14.1 G, and the frequencies in the slides. And finally, this is the shock loads and the resonance survey we apply after the test, before and after the test. The shock loads will be in the 3 axes, and the key factor will be 10. We develop a finite element model of the solar panels, quite detailed. We develop a finite element model of the hinges, of the tie down, and all the elements. We can show here some examples. This is some example of the model of the hinges, for example, and the solar panels. We are going to show some results of the simulations to show, for example, after the model analysis, we see the first model is in 220 Hz, and you can see the result of the 4 first mode. For example, in the random vibration response, you can see the response in terms of translations, in terms of accelerations and in terms of stress after the simulations of the levels shown before. In terms of job response, for example, this is the displacement, the movement, the acceleration, and the stress we get after the simulations. We like to review at this point the status of the project. CubeSat project was started last year in 2016, in the middle of 2016. The engineering phase has been finalized. Now is developing the manufacturing of the engineering models. The test will be developed. The engineering model will be developed during next month, during May, and in June will be manufactured and delivered to the customer. Okay, the flight, the launch is planned for 2018 in a Vega launcher. In this presentation, we show the design of the 3U solar panels, the model, the finite element model, and the results of the simulations. Finally, we'd like to say thank you to the national Spanish government, because part of the funding of this project has been developed in a DIPSA project. Is in a call from Ministerio de Economía and Competitividad. It's the Spanish part of the Spanish government. So thank you very much, and thanks for your attention.
Thank you, Miguel. I'd now like to welcome Amelia Gregg from Cal Poly onto the stage.
Okay, thank you everyone. I know it's coming close to the end of day, and I'm sure you're all wanting to get off to dinner, so I'm going to try and make this very short and quick for you. I am a relatively new faculty hire in the Aerospace Engineering Department here at Cal Poly. My background is in electric propulsion and micropropulsion, so I was brought in to try and build up a micropropulsion research and development sort of group here at Cal Poly. To complement the CubeSat activities that are currently already going on and build on the amazing knowledge that they have here. Because I've only been here a short time, I unfortunately don't have any real tangible great results yet for any of the work that I've done here. So today's presentation is going to be more the current projects I'm working on and future plans and things like that. Okay. Oops. Now it's working too much. Okay. So my current major project here at the moment is an electrothermal plasma thruster called Pocket Rocket. It's already been shown to be a viable option for micropropulsion for CubeSats, but it hasn't yet been actually integrated into a CubeSat and tested. So that's the current, or the next step that we're doing here. So I'm working on that at the moment. And as part of that, I'm also building a micronewton thrust balance. Well, when I say I am, my students are doing it, and I'm overseeing it, of course. Micronewton thrust balance that will be used to test not only Pocket Rocket, but any other micropropulsion system we end up developing, or any other micropropulsion system that might want to be tested here at Cal Poly. I'm also working to upgrade our testing and qualification facilities. So at the moment, Cal Poly has amazing facilities for testing and qualifying CubeSats, but some of them are not quite suitable for propulsion aspects, specifically the thermal vacuum chamber. It's a little bit small and we don't want to contaminate it with propellants. So I'm looking, in fact today actually, the new vacuum chamber got delivered, so I will be working to build on that and get it running in the next little while. In the future, these projects haven't started yet,
but we'll be starting them in the summer and fall of this year. Designing and building electrospray and colloid type thrusters, again for CubeSats. And then I'm also going to be doing a lot of electric propulsion simulation work, which is something I've done a lot of in the past and would like to continue doing. This is something that we can use to aid in the design process. The actual hands-on design process can be aided with these simulations. I'm not going to talk about either of the two future projects today, but if that is something that you have an interest in, please feel free to talk to me about it at some point. Okay, so I mentioned the main project I'm working on at the moment is Pocket Rocket. This is an electrothermal plasma thruster. So that means it uses electrical means to heat up a propellant to produce thrust. So similar in a way to something like a resistor jet, for example. It's been specifically designed for CubeSats. So it's small and it's as low power as we can get it. It's a very simple device, consists of just like a dielectric tube that's very, very small, like you can see it there sitting in my hand. And you flow a cold, inert propellant, like argon, for example, through that tube. There's a radio frequency electrode around the tube, and that, when you put even low amounts of power, like less than 10 watts, into the system, you create a weakly ionized plasma inside the tube. And so you now have a bunch of energetic ions in there as well. So the ions undergo what we call charge exchange collisions with the background neutral gas, and it heats it up. So I should stress, although I'm talking about plasma and ions in this system, the ions themselves contribute basically nothing to the overall thrust. The thrust is coming from the heated propellant. So to give you an example, if we run on argon at about 10 watts, we get a gas temperature at the exit of about 1,000 Kelvin. A couple of key design points for Pocket Rocket. The first one is that the heating that we're producing is occurring in the actual bulk propellant itself. So unlike, say, a resistor jet where you need to put in a heating element or heat up the walls, for example, because the heating comes from collision effects within the plasma, it's occurring in the main bulk. So with a nice choice of materials for the dielectric tube and the housing, we can actually contain most of the heat into the propellant itself rather than seeping through into the spacecraft structure. It can be operated in continuous or pulsed mode operation, so it has a wide variety of applications. And also, it can operate just as a cold gas thruster. If you don't turn on the RF power, then it's just a cold gas thruster, so it has a built-in intrinsic redundancy. To give you an idea of Pocket Rocket's current performance estimate, I've included a comparison here against a cold gas thruster and also an argon resistor jet. I chose these two because they're a similar style of propulsion to Pocket Rocket itself. So, cold gas thruster, I'll start with Pocket Rocket. So, Pocket Rocket, based on experimental temperature measurements, I should stress we haven't actually been able to directly measure the thrust yet. We have a specific impulse of 80 seconds, producing 2.6 millinewtons of thrust with 1 milligram per second of propellant flow rate and 10 watts of input power. Comparing that directly to a cold gas thruster with the same exact dimensions as Pocket Rocket, you get 40 seconds of ISP and about 1 millinewton of thrust. If we look at the argon resistor jet, which I took from the CDL-XR resistor jet range, they have some of their specifications published online. The specific impulse is the same. They claim 85 seconds, but can get 100 millinewtons of thrust for 50 watts input power. The reason they have a lot more thrust is because they have a much higher flow rate. The specific impulse is roughly the same. So Pocket Rocket is currently being worked on by 5 universities around the world. It was originally conceived of at the Australian National University, and since then the other 4 universities have come on board. So Tohoku University in Japan and the University of York in England work mostly on the actual physics of how Pocket Rocket works. Stanford is doing the electronic system for us, which I'll talk about in another few slides. And then here at Cal Poly, we are working with the Australian National University on the final design and integration and implementation of Pocket Rocket. So the integration that's currently going on here is being done by Cal Poly students, predominantly those in the PolySat group. It's a full integration, which means we're going to put everything inside of one new CubeSat, like the thruster, the electronics and the power system, the propellant storage and feed, and the control system. And then we're going to test it and run it. It's not going to be a flight model, but we will test it completely in vacuum. So we'll put it in a vacuum and then operate it remotely. We'll do some thermal testing on it to make sure it can withstand the thermal extremes. We will do direct thrust measurements of the integrated model. And when I say thrust measurements, also mean find like the specific impulse and the available delta V and all those other important performance parameters. And then because it's a bit of fun, we might throw a vibes test at it as well and see if it can stand up to that. I should point out that we are doing it into a 1U CubeSat. In theory, the Pocket Rocket system can completely fit into a half U, but we want to just, to start with, put it in a 1U, kind of make it a modular system, so you just buy a 1U and you strap it onto whatever your scientific payload is, thinking to the future, of course, this is. It's expected that the integration and complete testing will be done by March of next year, so stay tuned for results on that one. All right, so I mentioned the electronics that Stanford is working on for us. This is probably the most challenging part of getting Pocket Rocket into a CubeSat and getting it working. And that is because, as I mentioned, Pocket Rocket is a radio frequency device. So we need to get electronics into a CubeSat that is capable of converting the DC power to the required radio frequency. Stanford have produced the board that you can see on the slide there. And this is a working DC to RF driver. It's currently 10 centimeters square, so in theory fits in a CubeSat, but not quite, and requires 14 volts of DC input to operate. They will be looking, the next version of the board will be at least like maximum dimensions of 9.5 centimeters, so a little bit smaller, and they're going to try and decrease the required input voltage as well. I want to say 4 or 5 volts, but don't quote me on that. I may be misremembering what they told me. I should point out that this is the Stanford University Power Electronics Research Lab, or the Super Lab, which just has probably the best lab name I've ever heard of. Okay, so this is a short video of the latest test we did with Pocket Rocket, including the Super Lab DC to RF board. This is not the final thruster model that's going to go inside a CubeSat. Obviously, it looks quite big in that, and it is. This is our experimental housing. The actual thruster will be much smaller. So you can see about in the middle of the video, or in the middle of the screen there, there's the outlet to Pocket Rocket, and we've hung a Mylar strip in front of it so that you can sort of visualize the gas flow coming through and then the plasma and the thrust that you're getting out of it. So hopefully this works. Nope. Can someone backstage please play the video? There we go. Maybe not. Okay, it says it can't play. I'm not sure why, sorry. If anyone wants to see it, I can show it to you later, perhaps, but basically what it shows is we turn it on initially as a cold gas thruster, and you can see the Mylar strip start to move out because there's obviously some thrust being put against it. And then when we turn the plasma on in pulsed operation at 2.8 watts, you can see it running, and then you can see the Mylar coming out further every time it pulses. All right, so the last bit that I want to focus on today is our new micronewton thrust balance that we're building. This will be partly to test Pocket Rocket and partly to test other propulsion devices, like I mentioned. So it's a 4-arm pendulum. It's got at least 2 very thin foil sections in each of the arms, and this allows it to freely swing, or as freely as possible. You basically strap the thruster or a 1U or half-U CubeSat onto the bottom, and then turn on your propulsion system, and the entire pendulum will start to swing slightly. There's a non-contact displacement sensor with very high sensitivity on near one side of it, and that will measure how far it swings, and from that you can infer the thrust. Based on the current design, which is in the manufacturing process at the moment, so it hasn't fully been built yet, we expect the resolution to be about 20 micronewtons. We're hoping that in versions 2, 3, 4, and so on, we can slowly decrease that down to about 2 micronewtons of resolution. Okay, so that's all that I want to talk about today. So I've just put this up as a recap so you can remember what I talked about. If you are interested in knowing more about any of this stuff, I'd be happy to talk to you about it. And I'm also just going to unashamedly put it out there. I am just getting started here, and I'm open to any suggestions or collaborations that you think might be useful for the CubeSat world. So if you have anything like that, please also come and talk to me. Thank you. Questions? Are there any questions? Okay, so the question was what pressures are we running at, and what in the chamber, and what the nozzle diameter is. So the pressures we're running at the moment on the upstream side are between around 1 to 1.5 torr. So like 133 to 200 pascals. And that's when we run argon. Other gases will change it slightly, but it'll be around that. The nozzle, the final design for the nozzle is still being done at this point. The tube diameter for the final design will be about 1.5 millimeters. So the exit point will be that. I don't know what the nozzle throat diameter will be yet, but less than that.
And could you run it on water vapor?
Okay, running it on water vapor, in theory, yes, but I haven't tried it yet. Yes, it would. Thank you.
Thanks, Amelia. Okay, so for our next presentation, we had someone that could not make it, so there are pre-recorded videos that we are going to put up on the screen. So these are from Ifriki Tadaju, and hopefully our backstage tech guys can put up those videos for us in the coming moments. Okay, thank you.
Hello, everybody. Hello, California. Hello, Jordi. Wow, it's been a while. How many years now? How are you doing? Hello, everybody. Once again, it's a pity that I cannot be there. I would have loved to be there. There's so many of you that I would have loved to see again, and there's so many of you that I would have loved to meet. But unfortunately, I have to do the standard thing. Due to unfortunate circumstances beyond my control, it has been impossible for me to attend this event in person, but I do hope that this recording provides you with the information that I am hoping to transmit to you. Um, well, my title, I mean, you know how it is. You start off with the title, and then you go prepare your presentation. You see one of your other titles. You're like, this title is quite cool, and then you end up combining them both. But I will stick to the story about how we moved from bulletproof applications all the way to space radiation shielding applications uh, during the time I spent doing my doctorate work. And well, my name is Ifriki, and registered at the Cape Peninsula University of Technology in Cape Town, South Africa. Um, I worked in partnership with Itemba Labs and EFSATI, National Research Foundation, and I am very grateful for all their support, and I hereby acknowledge them and thank them for all what they have put in so that this good work could happen. Well, let's get right to it, shall we? So I am Ifriki, as I said. This is me over here. Uh, this work I did, I mean, the major contributors were, of course, Professor Ngom, Professor Maza, and Professor Fansale. Um, so, without further ado, um, what is this bulletproof materials? Yes, an overview. I'll tell you about it, how it moved, just a brief about how we got to bulletproof applications and moving, applying at least a shift in application from bulletproof to space radiation shielding. And then I'll tell you a little bit about my interest in terms of lasers, SEE, and machine learning. Um, so what happened was Professor Fansel decided that it's a good idea to look into space and in terms of space radiation environment, right? And Professor Maza had this pellet of bulletproof material. It is this ceramic composite of tungsten boride and boron carbide. And he said, well, can we investigate whether or not this can be used to synthesize coatings? Coatings that would make for great light shielding materials, or at least the light shielding solution for space purposes. So we asked ourselves, how can we make these specific coatings out of this very tough bulletproof material? And can these coatings offer any level of shielding against low energy protons specifically? Why low energy protons? Because we decided to focus on low Earth energy, where protons of energies less than 10 mega electron volts constitute the larger population. And also because high density semiconductor devices are sensitive to protons of energies less than 5 mega electron volts, with effects starting at half a mega electron volt through direct ionization. So we had that interest. We also had interest in solar panels, where you starting at half a mega electron volt all the way to 5 mega electron volts, protons can cause serious degradation. So, how do we get to have these coatings, or at least have an idea whether these coatings would be effective in space? These are the questions we're asking ourselves around this work. So why boron carbide, tungsten boride, ceramic composite? You know, it is a bulletproof material, therefore it exhibits lateral diffusion of energy. So we wanted to find out, can we observe this phenomenon at nanoscale? Will it still exhibit lateral diffusion of energy at nanoscale? In addition to that, because we reckon if it is the case, then for incident protons, uh, the energy will be dispersed laterally, therefore not leaving too much energy for the protons to go through on the other side, therefore protecting the devices on the other side of the coating. Furthermore, this coating contains tungsten that provides for a good material to absorb X-rays, and boron that has a good neutron absorption cross section. I know that those in the room who are aware of the content of semiconductor protective materials are going to may start firing the whole boron story, but stick with me a little longer. The truth is, the trade-off between protection and everything else that could happen. That's a discussion that hasn't happened yet because with this battery of tests that are yet to be done, we're just trying to discover whether this thing can shield to begin with or not. That's for a start. So we then set up to synthesize and characterize coatings made up of this boron carbide and tungsten boride ceramic composite. Then nuke the coatings that we synthesized and then see whether they offer any level of shielding. So here's the fun part. We use pulsed laser deposition to synthesize these coatings. Basically, in the vacuum chamber, you put the pellet target there, you fire lasers at it, it vaporizes the material into a plume that is transported towards the substrate, and on this substrate grows the coating. We started off with the target, which is the pellet of bulletproof material we had, and with X-ray diffraction, we could establish that indeed we had this boron carbide and tungsten boride ceramic composite, but we also saw through heavy ion ERDA that we had about 10% to give or take 1 or 2% oxygen impurity in the target. So we went ahead. After pulse laser deposition, we obtained coatings. You know what? You know what? This was one weird material. Actually, it still is a weird material. In fact, this is the only thing it did consistently being weird. So we start off with attempts of identifying what we had synthesized because we had a coating and we had to determine what it is because you can't take for granted that because you have a target, it's exactly what you have as a coating. Lo and behold, we didn't know what we had done. It showed X-ray diffraction characteristics like tungsten carbide, as if we had a tungsten carbide lattice, but it was not quite the tungsten carbide signature 2 theta degrees in XRD. And we could see through, I mean, there's AFM and other characterizations, we could see that there is a tungsten carbide like crystallography going on. But what exactly happened to it for it to be this weird? We couldn't tell. We knew for sure we had a solid solution, but what we had synthesized, we were not quite sure. I promise you, this was bizarre. With XPS, we got to have a sense of the bonding that's going on in there. We managed to propose um, that it is a tungsten carbide lattice where boron has occupied some carbon sites, and there has been therefore a shift. Um, all right, it seems my recording got interrupted for a second, but I was saying with this boron getting to the lattice, it would have shifted the lattice a little bit, and then that's what we went with in terms of experiment. At least that's what the characterization suggested at the time. Not that it has changed much now, but we had further results in the later paper. So we went ahead and irradiated this material with 900 kiloelectron volts of protons, and we observed the lateral diffusion of matter, which showed lateral diffusion of energy, which showed that through nanorod melting and subsequent regrowth, energy was indeed spent at the surface, which shows high evidence that this material can indeed be considered, at least further with further investigations, look into using it as a protective coating. As you can see, I mean, 4 reviews later, uh, I can promise you, this thing has. If I were there, you would have noticed the damage that this research has done. But it was well worth it. It was worth. we went for 1 mega electron volt protons under slightly position conditions, and again in a rather bizarre manner, where nanorods would break open, reveal nanospheres inside, melt the nanosphere. I mean, it spent energy on the surface, but in a rather strange manners. We went for UV vis transmittance, and we noticed that, well, you do lose about 10 to 15% transmittance through this 500 thick, about that 500 nanometers thick coating. But well, it's a design manner. Things that needs to be optimized can be optimized related to a specific space mission, and this still needs to be investigated to see if it can be used to protect solar panels. I did some stream simulations where I realized that it's actually quite cool because in terms of solar panel applications, for the same level of protection that a certain thickness of cover glass, commercial cover glass would offer, you only need about half the thickness for this material for the same level of protection. The question is, after investigating the optics, will we still get the same level of functionality of the solar panel in terms of generating power for the satellite? That we don't know yet. Um, but we're keen to find out. So, what's next for this material? A whole lot of characterization, quantifying solar panel applicability, quantifying memory cell applicability in terms of being a protective coating. We can't go with the Caesar type thumbs up or thumbs down because if you were going with fundamental science demonstrations all the way up to application. So it would require solid and rigorous testing. I imagine this is grounds for further, or maybe one or two PhD thesis for two lucky guys or girls or a mixture of both in the future. So, my space radiation engineering interest now over around, simple practical things like checking what thicknesses of tungsten would provide what levels of coatings. Can we tune material like tungsten in terms of its coating on a specific device for a specific mission in a specific orbit under specific radiation conditions? Can we do that? That's interesting because that's as targeted shielding as it gets, which would be very interesting. I promise, I mean, this is tungsten. I promise you, I went and made a pellet of lead, and then I was considering making coatings through PLD. I only stopped because of the health hazard, because it's difficult to enjoy the results of science from the grave. So I left it alone for a bit. I may return there maybe sometime. Maybe somebody should tie me and stuff me. Space applicability of new technologies. I mean, we do great work at CPUT. We just got patent granted on one of our RF filters, and I've already sent the boards for irradiation to see how it would respond to the space environment. This is the kind of thing I do in terms of engineering. I'm thinking, my interest as a postdoc, and as a postdoc also in terms of machine learning. I am wondering, can I have an intelligent machine that will tell me whether or not an untested device, and I'm not just an untested new device, new technology, will survive a specific space environment? So can a laser SEE setup help me gather data for this? What wavelengths, what pulse widths, what power, and what particles would these be emulating? And can I build such a machine, and would it be supervised or unsupervised learning? What kind of learning algorithms are we looking at? Hypothesis set, etc., etc. So the kind of questions I'm asking myself, and I mean, it's a great thing that Google, Facebook, Microsoft are opening their AI softwares for the mere mortals like us to have access. So I could turn to a tool like TensorFlow to see if I can channel some data that way and get some meaningful results on the other side. So that is the end of my story, and you know what? I am just realizing now that I didn't put my email address there, but please get it from Jordi. If you have questions or any suggestions or anything of the sort, don't hesitate to send it my way. I will be glad to collaborate with any of you who would be interested in having a chat or doing some useful work along these lines. Thank you very much for your attention. I hope I haven't eaten too much of your time. Keep well, enjoy the rest of the workshop, and yeah, hopefully I get to see you in person very soon. Bye bye, everybody. Ciao. Thanks for listening.
Okay, so that will conclude our presentations for today. Thank you all for coming, and we'll see you tomorrow for a 9 a.m. start, more presentations. Thank you.